let's get started, right? Everything is going to be completely handwritten today, okay? It's going to be completely handwritten. So let's get going then. And let's start the chapter with the basic terminologies. The basic terminologies involved in the chapter Thermodynamics. The basic terminologies which are involved in the chapter Thermodynamics. Let's get to know about these basic terminologies first. Okay. My dear students, we have got three basic terminologies over here in the chapter. Three basic terminologies. So first of all, I'll write the definition, then I'll make you understand what exactly it means also. Okay? Yeah? Let's have a look. Let's have a look. My dear students, the first terminology is what we call a system. The first terminology is what we call a system. The second terminology is what we call as surrounding. And the third terminology is what we call as boundary. Now, first of all, how do we define these terminologies? How do we exactly define these terminologies? Dear students, if you talk about the system, system is basically that part of the universe. It is basically that part of the universe which is under thermodynamic. Which is under thermodynamic investigation. What exactly it means, you'll get the idea in some time. The second terminology, that is surrounding. How do we exactly define the term surrounding? Surrounding is, it is defined as the part of the universe except the system. Part of the universe except the system is what you call a surrounding. And how do we exactly define the boundary? I would say anything that separates system from the surroundings. Anything that separates system from the surroundings is what you call as boundary, or you can call it as wall as well. So these are three basic terminologies which you must know, right, in the beginning itself. So my dear students, let's get to know exactly what is the meaning of these basic terminologies. Have a look exactly what I'm going to talk about. Understand properly. My dear students, just to make you understand what is system, what is surrounding, and what is boundary, let me just do one simple thing. For example, I'm taking one container over here. Let's say this is the container which is closed on all the sides, right? This container is closed on all the sides. Now, dear students, what exactly I'm going to do? I'm going to keep water inside this particular container. Let's assume I have kept water in this particular container. Okay? So we have got H2O liquid inside this particular container. Let's assume that we have to do one thermodynamic investigation related to the water in the container. Let's say I have to do one thermodynamic investigation for this water which is there in the container. What kind of investigation? For example, I need to check how much heat is required to raise the temperature of this water by 1 degree. Let's say I need to increase the temperature of water by 1 degree. And I have to do one investigation that how much heat is required to raise the temperature of water by 1 degree. So in order to raise the temperature of water by 1 degree, I need to check how much heat has to be supplied, right? So can I say this water in the container right now is under thermodynamic investigation? Absolutely. Yeah. Sir, please put a live session on the channel. What is this going on then? Is this recorded? Can't you see there is live mentioned somewhere? Okay. So my dear students, this water in the container, it is right now under thermodynamic investigation. I'm doing a thermodynamic investigation related to water. I'm checking that how much heat has to be supplied to water. in order to increase its temperature by 1 degree centigrade. So this particular water in the container is right now under thermodynamic investigation, and that part of the universe which will be under thermodynamic investigation, that is something which you call as system. So basically the water in the container right now is under investigation, so it is going to be your system. Okay, it is going to be your system. Number one. Number two, whatever is there in the universe except this water, except this system, whatever is there in the universe except this water, except this system, that is something which you will be calling as surrounding. That is something which you call as surrounding, right? Whatever is there in the universe except this water, except this system, right? That's something which I'll be calling as surrounding. Okay? And my dear students, as I told you, anything that separates system from the surroundings, that is something which you call as boundary. Do you see the walls of the container? They are basically separating system from the surroundings. So I'll be calling this wall over here as boundary. Perfect. I hope these three terminologies are clear to you. That part of the system which is under thermodynamic investigation, that's something which you call a system. Any other thing in the universe except your system is what you call a surrounding. And anything that separates system from the surroundings, that's what you call as boundary. I hope this is super clear to everyone. Right? Now, my dear students, understand few more things. Understand few more things. Now, you have got basically different types of boundaries which you have to remember basically. You have got different types of boundaries which I would want you all to remember. Number one. The first type of the boundary is what you call as the real boundary. Real boundary. One more is what you call as imaginary boundary. Then you have got diathermic boundary as well. And then you have got adiabatic boundary as well. You have got adiabatic boundary as well. Now, how do you define the real boundary? Real boundary is the one which you can see from your eyes. You can exactly see that there is something which is separating system from the surroundings. For example, this particular wall of the container, you can exactly see it, that it is separating system from the surroundings. And any such boundary which you can see by your eyes, right, which you can see by your eyes, that's what you call as a real boundary. Okay? Now, dear students, what is imaginary? Imaginary boundary cannot be seen. Cannot be seen by the eyes. It cannot be seen by the eyes. Let me make you understand what this imaginary boundary exactly is, right? How can you visualize it? For example, this is the container over here. Let's assume this is the container. This container is filled with water. This container is filled with liquid water. This is H2O liquid in the container. And this H2O liquid right now, it is under thermodynamic investigation, so it has to be my system, right? This is the topmost layer of the water. This is the topmost layer of the water, right? My dear students, apart from this container, can I say there'll be atmosphere basically from outside? And what does atmosphere contain? Atmosphere contains different gases. So there'll be different gas molecules present in the surroundings. These are different gas molecules which are present in the surroundings, right? These are different gas molecules which are present in the surroundings. So this water in the container, that is your system. That is your system. And apart from that, what do we have? Apart from that, we have got surrounding as well. Apart from water, we have got surrounding as well. Now, my dear students, if I ask you one simple thing, do you see this part of the container? Do you see this part of the container is separating system from the surroundings? Yes, you can see it by your eyes. So this is your real boundary. It's your real boundary. Do you see this part of the container separating system from the surroundings? Yes. So again, it's your real boundary. Do you see this part of the container separating system from the surroundings? Absolutely. It's a real boundary. Okay. Now, my dear students, look at the topmost layer of water. Just above the topmost layer of water, what do we have? We have got atmospheric gases just above the top of the water, because I have kept container open on one side, right? Can I say between the topmost layer of water and the atmospheric gases. Between the topmost layer of water and the atmospheric gases. Can I say one boundary will exist, one fine boundary will exist that will separate water from atmospheric gases? Can you see that boundary? You cannot see that boundary. But definitely there will be a fine line which will be separating atmospheric gases with water, which will be separating system from the surroundings. That boundary you cannot see by your eyes. And any such boundary which you cannot see by your eyes, that is something which you call as imaginary boundary. As simple as that. I hope this is clear. I hope this is clear, right? So I hope this particular scenario is clear to you, what this imaginary boundary is all about. Now, people, let's try to understand one more. Let's try to understand one more. What is that? That is diathermic boundary. What is diathermic boundary? Any boundary, any wall, any boundary, any wall, which allows the passage of heat, either from system to surroundings or from surrounding to system, right? Any boundary through which heat can pass, any boundary which allows the passage of heat either from surrounding to system or from system to surroundings. What do you call that boundary as? That's what you call as diathermic boundary, right? Which allows the passage of heat. Perfect. Now, my dear students, any such boundary which does not allow the passage of heat, either from system to surroundings or from surrounding to system, you'll be calling that boundary as diathermic boundary. Yeah, perfect. So, my dear students, a real boundary is the one which you can see by your eyes. Imaginary boundary cannot be seen by the eyes. Diathermic boundary allows the passage of heat either from system to surroundings or from surrounding to system. And at the same time, your adiabatic boundary, it does not allow the passage of heat either from system to surroundings or from surrounding to system. Right? Perfect. I hope this is clear to you. It's again complete basics. Moving on to different types of systems. How many different types of systems do we have? My dear students, the first type of the system is what you call as open system. Open system is the first type. Second is a closed system. And the third is, that is isolated system. Open system, closed system, isolated system. Right? What exactly this open system does? Let me tell you, open system, it allows the exchange of energy. It allows the exchange of energy as well as matter. Open system allows the exchange of energy as well as matter. With what? With the surroundings. Whereas closed system, it only allows the exchange of energy with the surroundings. Whereas if I talk about the isolated system, it neither allows the exchange of energy nor it allows the exchange of matter with the surroundings. Right? Very simple and basic. For example, just to make you understand. Let's say this is the container which you have taken. The container is open on one side. I'm keeping liquid water inside this container. This is liquid water inside the container. This is your H2O liquid, right? Let's assume that the walls over here are diathermic. If the walls are diathermic, they will allow the passage of heat. Now, my dear students, for example, this water is my system right now. It is under thermodynamic investigation. Okay? What exactly I'm doing? I'm supplying some heat to this water. When I supply heat to the water, after some time, what is going to happen? Can I say evaporation will start? Evaporation will start. The water will start getting evaporated, and those vapors will go into the atmosphere, right? What is heat basically? The heat which I'm supplying. What is heat? Heat is the mode of transfer of energy basically, right? Can I say this particular system is exchanging energy as well as matter with the surroundings, right? As you can see, energy is coming from surrounding to the system, and matter is going from system to surroundings. So this is one clear-cut example of what? Open system. It allows the exchange of energy as well as matter with the surroundings. Yeah? Perfect. At the same time, any such system which allows only the exchange of energy with the surroundings. Just to make you understand, for example, if I close this container, when I close this container, will there be any exchange of matter between system and surroundings? There will be no exchange of matter with the surroundings. Then I'll be calling this particular system as closed system. And any such system which neither allows the exchange of energy nor the matter with the surroundings, that's what you call as isolated system. Right? That's what you call as isolated system. What is the example of isolated system? If you consider entire universe as your system, if you consider entire universe as the system, if you take entire universe into investigation, right? That becomes the perfect example of what? That becomes the perfect example of isolated system, right? So open system, it allows the exchange of energy as well as matter with the surroundings. Closed system, it only allows the exchange of energy with the surroundings, not the matter. And isolated system, it neither allows the exchange of energy nor the matter with the surroundings. I hope it is super clear to you. Yeah? Now, my dear students, let's get to know about some important things now, right? Let's get to know about some important things now. There is something called as extensive property. There is something called as extensive properties. Extensive properties and intensive properties. Now, what these extensive and intensive properties are all about? What these extensive and intensive properties are all about? I'm straight away going to write the definition of extensive properties. Then I'll make you understand what they exactly mean. Right? This is something which is important. Okay? Understand. Extensive properties, let me tell you, these are the properties of system basically. These are the properties of system whose value changes on changing the size of the system. Whose value changes, or let me write it like this. These are the properties of the system whose value changes on changing the amount of substance. Whose value changes on changing the amount of substance present in the system. Present in the system. Right? And over here, I'm writing otherwise intensive. Otherwise intensive. Now let's get to know exactly what it means. Try to understand it carefully. Okay? Try to understand carefully. Okay, have a look, guys. So for example, imagine that you have got an object. Let's say this is one object. This is one block. This is one block of iron, right? This is an object, block of iron. For example, this iron block is right now under investigation. So this complete iron block is my system right now. This complete iron block is my system right now. Let's assume that the mass of this whole system is capital M, its volume is V, and its temperature is T. Let me assume that. The mass of this whole system, the mass of this block, it's M, volume is V, temperature is T, right? Now, dear students, if I just do one thing, if I divide the block into two parts, I divided the block into two equal parts, right? Now I'm taking only this part. So this part of the block is now under investigation. This part of the block is now under investigation. Can you let me know what is going to be the mass of this part of the block now? Is it going to be m or m by 2? It's going to be m by 2. Is its volume going to be V or V by 2? It's going to be V by 2. Is its temperature going to be T or T by 2? Its temperature will remain T only, right? Temperature won't change. So my dear students, first this whole block was under investigation. Now only half of the block is under investigation. You tell me, am I changing the size of the system? Absolutely, I'm changing the size of the system. And when I'm changing the size of the system, is the mass of the system changing? Mass of the system is changing from m to m by 2. Volume of the system is also changing from V to V by 2. But temperature of the system is not changing. Any such property whose value changes on changing the size of the system, any such property whose value changes on changing the amount of substance present in the system, you'll be calling that property as extensive property. So initially I defined 3 properties here. And out of 3 properties, 2 properties we have which are changing their values on changing the size of the system, right? So out of 3 properties, 2 properties are going to be extensive, right? 2 properties are going to be extensive. Whereas 1 property, which is temperature, it's not changing on changing the size. So temperature is going to be the example of intensive property. Is it clear? Is this part clear to everyone? Temperature is your intensive property, right? And my dear students, there are a lot of examples which you need to remember about extensive and intensive properties, which we'll discuss also in this chapter only, but not now. But not now, right? Because we have to understand those terminologies in the chapter first, then only you can get to know why those properties are extensive and intensive. So right now I would want you guys to just take a note of these properties. So first of all, the examples of extensive properties. Examples of extensive properties. Now you tell me, what are the examples of extensive properties? First of all, mass is going to be extensive. Volume is going to be extensive. Number of moles of a substance, it's going to be extensive. There's a term which we have to discuss in some time, that's heat capacity. Heat capacity is extensive, right? There's a term which we have to discuss in some time, internal energy. Internal energy is extensive. Enthalpy. Enthalpy is extensive. Entropy. Entropy is extensive. Gibbs free energy. It's again extensive. These are some very important properties which you have to remember, right? These are the examples of what? Extensive properties. Now, you must be thinking, what are the examples of intensive properties? There are many examples of intensive properties as well. There's students, temperature. Temperature. It is the perfect example of intensive property. Number 1. Number 2. Number 2. Density of a substance. Density of the substance is the perfect example of intensive property, right? Pressure. Pressure of the gas. It is the perfect example of intensive property. There is something called as specific heat capacity. There is something called as specific heat capacity. It is again one example of intensive property. There is something called as molar heat capacity. There is something called as molar heat capacity. Again one of the example of intensive property. There is something called as molar volume. Molar volume. Intensive property. Molar entropy. Molar entropy. Intensive property. Right? Concentration. Concentration. Intensive property. pH. Intensive property. Boiling point. Intensive property. EMF. Intensive property. These are all the examples of basically intensive properties. My dear students, I would want all of you to remember these intensive properties. Because question is asked, which of the following is extensive and which of the following is intensive? Perfect. You'll be given with 4 options. You have to select one. Yeah? Perfectly done. Now, there are some important features of these extensive and intensive properties. Some very, very, very important features. Number 1. The first important feature of extensive property. My dear students, when we talk about the extensive properties, let me tell you, extensive properties are additive in nature. They are additive in nature. What does that mean? That means the extensive properties, they can be added or subtracted directly. Intensive properties cannot be added or subtracted directly. So I'll say intensive properties are non-additive. Now, what exactly it means? What exactly it means? Have a look. For example, this is one container which I took. Okay. This is one more container which I took. Right? And this is one more container which I took over here. Yeah? Simple. I'm taking 3 containers. This container is, for example, filled with water. There is water inside the container. This container is also filled with water. It is also filled with water. Let me assume mass of this water is m, its volume is v, and its temperature is T. Let me assume mass of this water is m, its volume is v, its temperature is T. Perfect. Now, my dear students, this container contains water. Even this container contains water. If I pour the water inside both the containers into this final container, this final container will be completely filled with water, right? I'm pouring the water in both the containers into this final container. Now tell me, what is the mass of the water present in the final container? It's going to be 2m. Volume of water over is going to be 2v, but its temperature will remain as such. It's going to be T only. Yeah, it's going to remain T only. So first of all, how many properties of system did I define? I defined 3 properties: mass, volume, temperature. I defined 3 properties: mass, volume, temperature. Out of these 3 properties, how many are extensive? This is extensive, this is extensive. Whereas temperature is intensive. My dear students, do you see, when we are pouring the water in both the containers, in this final container, what is happening to mass? Mass of this water was m, this was m, so m plus m makes it 2m, right? Similarly, my dear students, v plus v, it makes it 2v, correct? T plus T, it is not making it as 2T. It is not making it as 2T, right? So my dear students, we had 2 extensive properties, and extensive properties are directly being added. Extensive properties are directly being added. Whereas, do you see intensive properties being added? No. If intensive properties were additive, then over here temperature should have been 2 times T. But that's not the case. That's not the case, right? Someone is saying, why not 2T? Let's say I have a glass filled with water. Its temperature is 25 degrees centigrade. One more glass filled with water. Its temperature is also 25 degrees centigrade. Pour them into a tub. What will be the temperature of the final water? Is it going to be 50 degrees centigrade? Are you saying something like that? Yeah. So you can see, out of these 3 properties, 2 were extensive. And extensive properties are straight away being added, whereas intensive properties are not. This is one important statement. Because from this particular statement, a particular type of question is asked in electrochemistry chapter, which is most probably going to be our next chapter, right? I cannot show that right now. I'll show it in electrochemistry. Perfect. So remember this. Extensive properties are additive, whereas intensive properties are non-additive in nature. Now, my dear students, one more important thing. Let me tell you, division of 2 extensive properties. Division of 2 extensive properties makes the new property as intensive. Makes the new property as intensive. What does that mean? Have a look. For example, I have got the object whose mass is m. Right? Volume of the same object is v. I've taken an object whose mass is m, whose volume is v. Now tell me whether mass is extensive or intensive. This is extensive. Volume, it is extensive. If I divide the two, mass by volume, it will be density. And density is the example of what? Density is the example of intensive property. So basically, when you divide 2 extensive properties, the new property that comes into play, that new property will be intensive in nature. Simple. Yeah. Is this clear to everyone quickly in the charts? At the same time, there is one more important thing. Okay, let me summarize it. So it is extensive property divided by extensive property. It makes the new property as intensive. This is something which you have to remember. Extensive by extensive is intensive. Yeah? Extensive by extensive is basically intensive, right? So this was the second feature. This was basically the second feature of your extensive property. Now, my dear students, talking about the third important feature. What is that? Have a look. I'm writing a statement. When an extensive property is expressed, per unit mass, comma, per unit mole, or per unit volume, the new property becomes intensive. Now, what that exactly means? Have a look. There is a term basically which we have to discuss in some time. That's called as heat capacity, which is represented by C. Let me tell you, heat capacity represented by C, it is one of the example of extensive property. Yeah. Now, my dear students, if I define heat capacity per unit mass, this is now called as specific heat capacity. Specific heat capacity. Again, this is something which we have to discuss in some time. And let me tell you, the specific heat capacity, it is the example of intensive property. So, when an extensive property is expressed per unit mass or per unit mole, for example, C divided by N, heat capacity per unit mole is called as molar heat capacity. Right? It's called as molar heat capacity. Since heat capacity was extensive in nature, therefore molar heat capacity will be intensive in nature. Right? Simple and basics. Yeah. Similarly, my dear students, there are other things as well. For example, V stands for volume. If I divide it with number of moles per unit mole, V by N is something which we call as molar volume. Volume was the example of extensive, and molar volume will be the example of intensive. For example, you have got entropy, S, which is the example of extensive. Per unit mole, it's called as molar entropy. Molar entropy is the example of intensive property. So do remember these particular things as well. Whenever an extensive property is expressed per unit mass, per unit mole, or per unit volume, the new property becomes intensive. Right? So quickly, give me some thumbs ups in the chats if you got this particular concept properly. Quickly, people. Let me know in the chats quickly if all the things are clear till here. Someone is asking, sir, please do previous year questions as well. In every session, we do PYQs as well. You need not to worry about that. I exactly know what to do and what not to do. Okay? You just follow what I'm teaching. Nothing else. Yeah? I hope these three statements are clear regarding extensive and intensive properties. Now, my dear students, there is one more thing. Just a second. There is one more important thing. And what is that important thing? Let's have a look. Just a second. Let me add up some blank slides so that it will be easy to understand, basically. All right, let's move on. My dear students, there is something called as state parameters. How do you exactly define these state parameters? Let me tell you. State parameters are basically These are the variables. These are the variables which actually defines the state of the system. These are the variables which actually defines the state of the system. For example, pressure, volume, moles, temperature. These are the variables basically which actually defines the state of the system. Number one. Number two, in order to change the state of the system, in order to change the state of the system, in order to change the state of the system, the value of state parameters needs to be changed. The value of state parameters needs to be changed. If you want to change the state of the system, you will have to change the value of state parameter. Right? And my dear students, if you change one of the state parameter of the system, if you change one of the state parameter of the system, the state of the system will automatically change. Minimum, in order to change the state of the system, minimum you have to change one state parameter. Maximum, you can change many. Yeah? Right? Yes, Divya, this is absolutely free. All the sessions are happening on YouTube only. Absolutely, it's for 2024, even 2025 students can also watch it. Yeah? Okay. So my dear students, let me just make you understand this particular statement. Understand. For example, this is the container. And for example, I have got an ideal gas inside this container. These are the ideal gas molecules which are present inside the container. This ideal gas right now is my system. I'm assuming the pressure of this gas is P1, volume of this gas is V1, temperature of this gas is T1, moles of this gas are N1, right? So I can categorically say when the pressure of the gas is P1, when the volume of the gas is V1, temperature T1, moles N1, I can say the gas is present at its initial state. I can say the gas is present at its initial state. So these are basically the parameters, these are the variables which actually define the state of the system. They actually define the state of the system. And people, at the same time, if you want to change the state of the system, if you want to change the state of the system, you have to change the value of state parameters. Minimum, you can change one state parameter, maximum, you can change many, right? For example, I'm changing the pressure of the gas. Let's say I'm changing the pressure of the gas from P1 to P2. Volume, I'm changing from V1 to V2. Moles, I'm changing from N1 to N2. Temperature, I'm changing from N1 to T1 to T2. So, I think I changed all the state parameters. And when you change the state parameters, what happens to the state? State of the system automatically changes. Now, you cannot say that this system, you cannot say that this gas, you cannot say it's present at initial state now. Let's call this as the final state. This is going to be the final state of the gas. So in short, what I want to convey at this particular point of time. Yes, Monish, you can do that. What I want to convey over here, what is that? When you want to change the state of the system, you will have to change the value of state parameters. Minimum, if you change one state parameter, the state of the system automatically will change. As simple as that. Yeah, as simple as that. And what are these state parameters? These are basically some variables which actually defines the state of the system. Through these variables only you get to know where the system, through these variables only you get to know that whether the system is present at its initial state, at its final state, at the intermediate state, or wherever. Yeah, through these state parameters. This is again one basic thing which you need to know. I hope this is clear. My dear students, there is something called as state function and path function. There is something called as state function and path function. State function and path function. What are state functions and what are path functions? Let me write their definition and some important points so that there won't be any doubt afterwards. Okay? My dear students, state functions are the ones whose value depends only on, whose value depends only on the initial and the final state of the system. State functions are the ones whose value only depends on the initial and final state of the system. Let me tell you, these state functions, these are path independent. These are path independent. These are path independent. Well, if the value of a state function only depends on the initial and final state, what do we do then? Therefore, we calculate change in the value of state function. And change in the value of state function is always equal to the final value of state function minus the initial value of state function. Final value of state function minus the initial value of state function. What are the examples of state functions? There are basically a lot of examples, which we are going to discuss in some time. Internal energy, that is the example of state function. Enthalpy, state function. Entropy, state function. Gibbs free energy, state function. Right? Right, people? So, I can say the examples of state functions are internal energy. That's why I'm calculating change in it. Enthalpy, delta H. That's why I'm calculating change in it. Gibbs free energy, delta G. Entropy, delta S. Right? These are the common examples of what? These are the common examples of state functions, basically. Now, guys, there is one important point which I would want you guys to remember from now onwards. What is that? For example, A is a state function. A is a state function. A is a state function, for example. Achha, do you remember one thing? Have you studied distance and displacement? Displacement only depends on initial and final. Distance is path dependent. Displacement is not path dependent. Right? Whenever you get confused with state functions or path functions, you can relate it with distance displacement so that you can memorize it properly. Yeah? Perfect. Now, people, for example, A is a state function. This A can be internal energy, this A can be enthalpy, it can be Gibbs free energy, it can be entropy, right? Now, my dear students, if I multiply this A by D, if I write dA, what this dA indicates? It indicates small change in A. It indicates small change in A, right? It indicates small change in A. Now, if I integrate this dA, what is dA? Small change. You're integrating it. Now it becomes large change. Now it gives you the large change, or you can say the total change. Large change in A. This is one simple thing which I would want you guys to remember. One simple thing which I would want you guys to remember. For example, U stands for internal energy. U stands for internal energy, right? U stands for internal energy. My dear students, if I ask you whether the internal energy is the example of state function or path function, it is the example of state function. It is the example of state function. Dear students, if you multiply this internal energy by D, it becomes du. Now, how should I pronounce this du? What should I call this du? This du is going to be small change in internal energy. I'll be calling this as small change in internal energy. Now, if I integrate this small change, it gives me the large change in internal energy. It gives me the large change, or you can say the total change. The large change or total change in internal energy. This is one more important point which I would want every one of you to remember. Right? Perfecto. Now, my dear students, one more thing. Since these were state functions, that's all. That's all. Nothing else to remember about it. Okay? Nothing else to remember about it. Now, guys, there is something called as path function. There is something called as path function. How do you exactly define the path functions? Let me tell you, these path functions, they also depend upon the initial and final state. They also depend upon initial and final state. They also depend upon the initial and final state. And apart from that, they are path dependent as well. They are path dependent as well. What are the common examples of path functions? It's going to be heat and work. heat and work, these are basically the common examples of the path functions. Why they are the path functions? You'll get the idea when I'll teach you the PV work, area under PV curve, right? Afterwards, there only you'll understand exactly how come this work and heat, they exactly are the path function, right? Their value depends on initial state, final state. Apart from that, they'll be path dependent. They're path dependent functions. And my dear students, whenever you get confused with state or path functions, just try to relate it with distance, displacement. Displacement, initial, final state. Distance, initial, final state, and path dependent. Try to relate it with it. Yeah? Okay? Now guys, there is one more thing. This heat is represented by Q and work is represented by W. This is something you must remember from now onwards. Point number one. And point number two. Point number two. My dear students, for example, A is the path function. For example, A is a path function. This A can be heat, it can be work. Okay, for example, A is a path function. If I multiply this A by D, it becomes dA. dA, I won't be calling it as small change in A. No, dA is the path function. I'll be calling it as small amount of A. I'll be calling it as small amount of A. And if I integrate it, if I integrate it, small amount integration, I won't represent it with delta A. I'll just represent it with A. And A denotes large amount or total amount of A. For example, what is Q? Q is heat. Heat is the example of path function. If I multiply dQ, since Q is the path function, heat is the path function, so I won't be calling this dQ as small change in heat. Does not make any significance. This I'll be calling a small amount of heat. This I'll be calling a small amount of heat. And my dear students, if I integrate it, it becomes Q. It becomes Q, which represents total amount of heat. It represents total amount of heat. I hope you guys are going to remember all these things. Yeah? Perfect. Is it clear till here? Say yes or no in the chats quickly. All these things should be clear till here, I believe. I believe all these things should be clear till here. Yeah? Okay. Now, my dear students, till now we were only talking about the basics. I'm just giving you the idea about different things which we have to discuss in the chapter. Okay? I'm just giving you the idea of the things. Later on, we'll be discussing about all these things in detail. Heat, work, internal energy, enthalpy, Gibbs free energy, everything. Right? Now understand what I'm going to do. There is something called as thermodynamic process. I'm right now just going to give you the idea about thermodynamic process. I'm not going to teach you in detail right now. In detail, we'll discuss it after some time. I'm just giving you the idea what thermodynamic process is all about. What thermodynamic process is all about. My dear students, if you want to define the thermodynamic process, it is basically defined as the path followed. It is defined as the path followed to change. The path followed to change the state of the system. Path followed to change the state of the system. Now you must be thinking what it means. Path followed to change the state of the system. What does that mean? Try to understand this. For example, you have got an ideal gas in the container. Let's say these are the ideal gas molecules which are present in the container. Right? These are the ideal gas molecules. And this ideal gas is my system right now. It is under thermodynamic investigation. Right? Let's assume the pressure of the gas is P1, volume is V1, temperature is T1, moles are N1. For example. And I'm assuming when the pressure is P1, volume V1, temperature T1, moles N1. I'm assuming that the gas is present at its initial state. So right now, this gas is present at its initial state. Correct? Now guys, as I told you a few minutes back, if you want to change the state of the system, what you exactly need to do. In order to change the state of the system, we need to change the value of state parameters, right? We need to change the value of state parameters. Minimum, if you change one state parameter, the state of the system will automatically change, right? For example, I'm going to change the value of state parameters of this gas. I'm going to change the value of state parameters of this gas. For example, the number of moles present in the container initially were N1. Now, for example, the number of moles are N2. Let's say the temperature of this gas now is T2. Volume is V2. But pressure, I'm keeping the same, P1. Have I changed the state parameters? Yes, I have changed the state parameter. When you change the state parameters, the state of the system automatically changes. Let me call this as the final state of the system. Let me call this as the final state of the system. My dear students, if you analyze one simple thing, did I change the state of the system? Yes, I changed the state of the system. But the pressure of the gas initially was P1, finally also it's P1. What does that mean? That means I changed the state of the system without changing the pressure of the gas. I changed the state of the system without changing the pressure of the gas. Right? I made sure that the state of the system changes without changing the pressure of the gas. So what I did exactly? I kept the pressure of the gas constant. I kept the pressure of the gas constant. Since I changed, no doubt, I changed the state of the system. But when I was changing the state of the system, I made sure that pressure of the system should not change. My dear students, can I say, I could have changed the state of the system by keeping the volume of the system constant as well. I could have changed the state of the system by keeping temperature of the system constant as well. Right? So can I say, I have got many paths available. I have got many paths available to change the state of the system. I can change the state of the system by keeping the pressure of the system constant. I can change the state of the system by keeping the volume of the system constant. I can change the state of the system by keeping the temperature of the system constant. So I have got many paths available, right, to change the state of the system. And the path followed out of these paths, that path which you are following, the path followed to change the state of the system, that's something which you call as thermodynamic process. So what is thermodynamic process? It is the path followed to change the state of the system. You have got different paths available to change the state of the system. Now, out of those paths, which path you are following to change the state, that defines the thermodynamic process, right? Now, dear students, understand. The first thermodynamic process whose idea I'm giving you, that's isochoric process. In isochoric process, what happens? In isochoric process, you will be changing the state of the system by keeping the volume of the system constant. You won't let the volume of the system change while changing the state of the system. Right? Number one. Number two, if volume of the system is constant, change in volume, which is V final minus V initial, that has to be zero. Change in volume has to be zero, right? And my dear students, if you just want to plot a graph, or leave graph aside, tell me one thing. Have you studied gas laws? Right? In which gas law, volume of the gas is kept constant? In which gas law, volume of the gas is kept constant? You call that gas law as Gay-Lussac's law. I'm changing the state of the gas by keeping the volume of the gas constant. So can I say, the gas which is under investigation right now, that will be straight away following the Gay-Lussac's law? That will be following the Gay-Lussac's law. And as far as the Gay-Lussac's law is concerned, P1 divided by P2 has to be equal to P1 divided by T2. So whenever you'll be having an ideal gas undergoing isochoric process, that ideal gas will be following this particular equation, right? That will be following this particular equation. At the same time, if I ask you, plot the graph. Plot the graph between pressure and volume. Plot the graph between pressure and volume. Since you are keeping volume constant, so volume is not supposed to change. Volume is not supposed to change. Volume you have to keep constant. So it has to be a straight line, right? It has to be a straight line. And you call this graph as isochore. You call this graph as isochore. I hope this is clear to everyone. I'm just giving you the idea of the things. I'm not teaching in detail right now. I'm just giving you the idea. All these processes we have to discuss in detail afterwards. Okay? Perfect. So number one was your isochoric process. Now similarly, you have got isobaric process as well. Tell me what happens in isobaric process. When do we say that the gas is undergoing isobaric process? When can we say that the ideal gas is undergoing isobaric process? First of all, let me tell you one thing. Med talks, I did not talk about work yet. I'm not involving work right now. We have to discuss that as well. Just try to understand what I'm telling. That's it. Okay, we'll go to work as well. Just wait. Okay. So let me just remind you one thing. From now onwards, whenever I talk about ideal gas, whenever I talk about system, whenever I say that I have got a system with me, understand that I have taken an ideal gas in the container and that ideal gas is under investigation. Because in this chapter, we have to deal with only the thermodynamics of ideal gases. Perfect. So from now onwards, whenever I'll be using the term system, understand that we have got a container which contains the ideal gas and that ideal gas is under thermodynamic investigation, right? Now, my dear students, when do we say that the ideal gas, that the system is undergoing isobaric process? If during the change in the state of the system, if during the change in the state of the gas, pressure of the gas does not change at all. Pressure of the gas does not change at all. You're changing the state of the gas. You're changing the state of the system. But during the change in the state of the system, pressure is not changing. You'll be calling that process isobaric process. You can say that the gas is undergoing isobaric process. Right? So my dear students, what will be change in pressure? Change in pressure absolutely zero. Now, if you remember in states of matter, which gas law we introduce at constant pressure? It is Charles' law, which is used at constant pressure. So my dear students, Charles' law equation used to be like this: V1 divided by V2 is equal T1 divided by T2. So whenever the ideal gas undergoes isobaric process, you can use this particular equation for the ideal gas. Yeah, right? And by chance, if you want to plot a graph between pressure and volume, how the graph looks like? Pressure you have to keep constant. You'll be calling this curve as isobar. I hope this is again clear to everyone. Now, my dear students, one more thing. There is something called as isothermal process. What happens in isothermal process? When do we say that the ideal gas is undergoing isothermal process? My dear students, if you will be changing the state of the gas, if you will be changing the state of the system without doing anything to its temperature, without letting its temperature to change, that means you are changing the state of the gas by keeping the temperature of the gas constant, then only I can say that the system is undergoing isothermal process, right? So change in temperature over here has to be zero, right? In which gas law? Temperature is kept constant. That's Boyle's law. So when the gas undergoes isothermal process, it has to follow the Boyle's law. And what was the basic equation of Boyle's law? P1V1 is equal to P2V2. So when the ideal gas undergoes isothermal process, it will be following this equation, right? And my dear students, or you can say something like this. You can say P is equal to K by V. This is the equation as far as the Boyle's law, right? And if you want to plot the graph between pressure and volume, can you let me know what will be the nature of the graph? Pressure and volume, they are inversely proportional to each other. So the nature of the curve has to be rectangular hyperbola. And you call this particular curve as isotherm. You call this particular curve as isotherm, right? Whenever you need to plot a curve between two variables which are inversely proportional to each other, the nature of the curve has to be rectangular hyperbola. So this curve is rectangular hyperbola, and you will be calling it as the isotherm. Yeah? Correct? And my dear students, this particular equation, you call this as the equation of state. This is called as equation of state for isothermal processes. Equation of state for isothermal processes. Right? Now, similarly, there is one more thermodynamic process which we have to discuss in detail. But right now, I'm just giving the idea of the things. Right? I'm not teaching these processes in detail now. Giving you just the idea of the things. Right? All these processes we have to discuss in detail. I'm writing adiabatic process. When do we say that the system is undergoing adiabatic process? When do we say that the system is undergoing adiabatic process? If there will be no heat exchange. If there will be no heat exchange between the system and surroundings. During the change in the state of the system. So basically, Q value has to be 0. So whenever the system undergoes a change in state, whenever you will be changing the state of the system, but you will make sure during the change in the state, there should be no heat exchange. There should be no heat exchange between the system and surroundings. Heat should not enter into the system or should not leave the system, right? Then only I can say that the system is undergoing adiabatic process. My dear students, I told you the equation of state for isothermal process. Similarly, there is one more equation of state here. That is PV raised power gamma is equal to constant, right? This is the equation of state. This is what you call as equation of state for a reversible adiabatic process. What is reversible? You will get the idea in some time. Okay? This is something which you call as a reversible adiabatic. Equation of state for reversible adiabatic process. Right? There are basically two types of adiabatic processes: reversible adiabatic, irreversible. I'll discuss about that afterwards. Okay? Now, first of all, you can write the same equation in this format. P is equal to K divided by V raised power gamma. Absolutely. Now tell me whether pressure and volume, they are directly proportional or inversely. They are again inversely proportional. If they are inversely proportional to each other, tell me the nature of the curve. This has to be again the hyperbola. They are inversely proportional. The nature of the curve is hyperbola, right? And you'll be calling it as adiabat. You'll be calling this curve as adiabat. Now you tell me one thing. In case of isothermal process, PV graph was hyperbola, right? And in case of adiabatic process also, PV graph is hyperbola. Now, how can you distinguish between two hyperbolas, whether it's for adiabatic or isothermal? How do you do that? Let me tell you one simple trick, right? Or let me write the concept first of all. I'm not going to derive the concept because that's of no use to you. Just remember it. And later on, like after 1-2 minutes, I'll be giving you one trick as well. That trick is important, right? Leave the trick aside right now. Let me write the concept. Do remember slope of the tangent. Slope of the tangent at a point. slope of the tangent at a point on PV curve for adiabatic process is equal to gamma times the slope of tangent at a point on PV curve for isothermal process. And do remember one more thing, gamma, that's something which you call as Poisson's ratio. We'll be discussing that also in some time. Do remember its value is always greater than 1. If gamma value is greater than 1, can I say the slope of adiabatic in general will be greater than that of slope of isotherm, right? If you do not want to remember this, then do remember one simple trick. See guys, for example, this is pressure and this is volume, right? I'm going to draw two hyperbolas. This is one hyperbola. This is one more hyperbola, for example. I'm putting the arrow on the right. Now tell me, towards right, whether the volume is increasing or decreasing. Towards right, the volume is increasing. Increase in the volume is something which you call as expansion. So basically, both these graphs, they represent expansion. Right? How do you justify, leave the justification aside. How do you differentiate which curve is isotherm and which curve is adiabat? What you need to do exactly is just one simple thing. Select the common point. This is the common point, right? Place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches the fingers first, that has to be your isotherm always. The other one is going to be adiabat. The other one automatically is going to be adiabat. As simple as, right? For example, you have got two graphs like this. This is pressure and this is volume, right? Let's say I'm starting from this point. And I'm making two hyperbolas like this. These are the two hyperbolas which I made. I'm keeping the arrow towards left. Tell me first of all, towards left, whether volume is increasing or decreasing. Towards left, volume is decreasing. Decrease in the volume is something which we call as compression. Right? Now, tell me which one is isotherm, which one is adiabat. Again, do same thing. Place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches the fingers first, that has to be your isotherm. So this is going to be your isotherm, and the other one automatically, that is your adiabat. I hope this is clear. Yeah? Very simple and basic. You are going to remember it like this from now onwards. Yeah? Quickly let me know in the chats with the thumbs ups. Sir, would you teach atomic structure? Surely, why not? I'll teach everything, chill. Quickly guys, let me know in the chats with the thumbs ups if all the things are clear till here. Yeah? I'm not teaching these processes in detail now. I'm just giving you the idea of some basic things. I did not teach them yet. Okay? Just keep that thing in mind. I did not teach them in detail yet. This is just the basic introduction of the thing. Perfecto. Moving ahead, guys. There is something called a cyclic process. I'm just giving you the definition of it. Cyclic process. When do we say that the system is undergoing cyclic process? When do we say that the gas is undergoing a cyclic process? How do we define the cyclic process? In cyclic process, what happens basically? System returns system returns to its initial state. System returns to its initial state after going through a lot of steps. After going through a lot of steps. This is again one very important topic which we have to discuss in detail. There are a lot of questions which are based on this. Yeah, a lot of questions which are based on this. But I'm just giving you the idea of the things, right? I'm not teaching it. I'm just giving the idea. Cyclic process. In cyclic process, what happens? System returns to its initial state. Let me give you an analogy. One analogy is enough. For example, you're starting from this point. You're starting from this point. This is your initial state, for example. You're going from point A to point B. Then you're going from point B to point C. Then from C, you're going again to A. You're going again to A, right? Can I say your initial state and final state is same? Can I say your initial state and final state is same? And my dear students, whenever system returns to its initial state after going through a lot of steps, what do we call this process? Cyclic process, right? So I can say the system is undergoing cyclic process, right? The system is undergoing cyclic process, right? One simple thing. Is the initial and final state of the system same? Absolutely. If the initial and final state of the system is same, can I say the initial value of state function and final value of state function will also be same? Because state function only depends on initial and final state. State function changes. State function only depends on initial and final state. If the initial and final state is same, so the final value of state function will be equal to the initial value of state function. And change in the value of state function will be equal to final value of state function minus initial value of state function. That has to be 0, right? That has to be 0. Perfect. So for a cyclic process, delta U value will be U, internal energy. Internal energy is state function. Change in the value of state function for a cyclic process, that is 0. So delta U for the cyclic process is 0. Delta H for a cyclic process is 0. Why? Because enthalpy is a state function. Entropy change for the cyclic process, that has to be 0. Gibbs free energy for the cyclic process, that has to be 0. All these things, again, we have to discuss in detail only. Right now, just the basic idea I'm giving, right? So change in the value of state function for a cyclic process, that is absolutely going to be 0. Is this clear? Is this clear to you? Is this clear to you, people? Yeah? Now, there is something called as heat, which is represented by Q. There is something called as heat represented by Q, right? What is heat exactly? What is heat? Can you define heat? My dear students, heat, when we talk about heat in particular, heat is defined as the mode of transfer of energy. It is defined as the mode of transfer of energy between the system and surroundings. Mode of transfer of energy between system and surroundings. Whenever exchange of energy has to take place between system and surroundings. Whenever exchange of energy has to take place between system and surroundings. The exchange of energy between system and surroundings. The transfer of energy between system and surroundings can be done via heat. So what is heat? It is just the mode of transfer of energy between system and surroundings. For example, if energy is to be sent from system to surroundings, or if the energy is to be sent from surrounding to system, this transfer of energy, this exchange of energy between system and surroundings can be done via heat. So heat is just the mode of transfer of energy between system and surroundings. Right? Why does heat flow? Why does heat flow? You know it, heat flows due to temperature difference. Heat flows due to temperature difference. And heat always flows from higher temperature to lower temperature. It always flows from higher temperature to lower temperature. For example, this is the container which we have. Let's say this is the container which we have. And in this container, what do I have? I've got gas. The gas is my system. The gas is my system, right? T system represents the temperature of system. And outside the system, there is surrounding. And T surrounding represent the temperature of surroundings. Temperature of system is represented by T system. Temperature of surrounding is represented by T surrounding, right? One thing. If, for example, if T surrounding is greater than T system, if the temperature of surrounding is more than that of temperature of system, can I say there will be temperature difference between system surroundings? And whenever there is temperature difference, heat automatically flows from higher temperature to lower temperature. Right now, surrounding it has higher temperature. System is at lower temperature. So heat will flow from surrounding to system. If heat is flowing from surrounding to system, can I say it means system is absorbing heat? Absolutely, system will be absorbing heat. Absolutely, system will be absorbing heat. And do remember, whenever system absorbs heat, Q value as per sign convention is taken to be positive. Whenever system absorbs heat, Q value as per sign convention is taken to be positive, right? And my dear students, one more important thing. For example, if temperature of system is greater than temperature of surroundings, if temperature of system is greater than temperature of surroundings, again there is temperature difference. Again heat will flow from higher temperature to lower temperature. That means heat will be moving from system to surroundings. So at that point of time, I can say system releases heat. I can say system releases heat. And do remember from now onwards, whenever system releases heat, Q value as per sign convention is taken to be negative. As per sign convention, it's taken to be negative. Yeah? These are the two basic things which you have to remember about heat, nothing else. Basic things which you need to remember about heat, nothing else. Heat, it is the mode of transfer of energy, right? Whenever the exchange of energy has to happen between system and surroundings, this exchange of energy can happen via heat. So heat is nothing, it is just the mode of transfer of energy, which flows due to temperature difference, always from higher temperature to lower temperature. Whenever system absorbs heat, Q value positive. Whenever system releases heat, Q value negative. That's all. Yeah? Point number one. At the same time, I have told you in the beginning itself, heat is the example of what? It is the example of path function. Heat is the example of what? It is the example of path function. Something which I already mentioned in the beginning. Yo? I hope this is clear. Moving ahead. There is one more thing that's called as work. Work is represented by W. Work is represented by W. Now the point is, how do we define work? How do we define work? Again, the similar thing, guys. Work is again, it is again the mode of. It is again the mode of. It is again the mode of transfer of energy. Mode of transfer of energy between the system and surroundings. Between the system and surroundings. Work, it is again the mode of transfer of energy between the system and surroundings. Whenever exchange of energy has to happen between system and surroundings, whenever energy has to go outside the system, or whenever energy has to enter into the system, this exchange of energy between system and surroundings, it can happen via work as well. It can happen via heat as well. It can happen via work as well. So work is again what? It is again the mode of transfer of energy between system and surrounding. Yeah? Now there are some very important points which you need to understand. Have a look, guys. Understand this particular thing. For example, this is the container. Let's say this is the container. And this container, over here, you have got a piston. The piston can go out, it can come inside as well. Piston can go out, it can come inside as well. For example, you have got the gas inside the container. This is the ideal gas in the container. So this ideal gas is my system right now. It is my system right now, yeah? When the piston is, for example, at point A, volume of the container is, for example, V1. And you know, an ideal gas occupies the volume of container in which it is kept. So right now, volume of the ideal gas is V1. Correct? Yeah? Right now, volume of the ideal gas is V1. Now, guys, try to understand few things. If you analyze this piston over here, right? Can I say these gas molecules which are present in the container, they'll be colliding with the piston? Absolutely. So in this particular direction, I'll be saying there will be pressure of gas, right? In this direction, there will be pressure of internal gas, right? Now, my dear students, outside this piston, there is atmosphere. And you know, atmosphere contains gases as well, right? So those gas molecules will be also colliding with the piston from outside. So on this particular side, there will be one more pressure. That's something which you call as P external. So on the piston, how many pressures are there? There are two pressures acting on the piston. One is P gas due to the internal gas. One is P external due to the atmosphere, right? Now you tell me one thing. Case number 1. My dear students, if P gas is greater than P external, you tell me, if P gas is greater than P external, will the piston come inside or will the piston go outside? If P gas is greater, the piston will go outside. And when the piston goes outside, let's say the piston goes outside and finally it stops here at point B. When the piston goes outside from A to B, is the volume of container increasing? Absolutely. The volume of container is increasing, right? If the volume of container is increasing, we know the ideal gas occupies the volume of container. That means the volume of gas will be increasing as well. Perfect. So can I say, if P gas is greater than P external, can I say V2 will be greater than V1? Final volume of gas will be greater than that of initial volume of the gas. Now, if final volume of the gas is greater than initial volume, does that mean the volume of the gas is increasing? Yes, absolutely. The volume of the gas is increasing. And increase in the volume of the gas is something which we call as expansion. Increase in the volume of the gas is something which we call as expansion. And whenever there is expansion, we always say work is done. Whenever there is expansion, we always say work is done by the system. We always say work is done by the system, right? Except in case of free expansion. That's something which I'll be teaching you separately, okay? Whenever there is expansion, we always say work is done by the system. And whenever work is done by the system, W value is taken to be negative as per sign conventions in chemistry. In physics, you take it positive. This was case number 1. Now, let me talk about case number 2. Now, you are going to decide what is going to happen. And keep on telling me in the chats continuously. For example, if P external is greater than P gas, the piston will come inside. Volume of the container will decrease. That means volume of the gas is decreasing. So V2 will be less than V1. Decrease in the volume of the gas is something which you call as compression. The gas is undergoing compression. Whenever there is compression, we always say work is done on the gas. And whenever work is done on the gas, W value as per sign convention is taken to be positive in chemistry. is taken to be positive in chemistry. Right? Is this clear? Now you tell me one more thing. Case number 3. If by chance P gas is equal to P external, if P gas and P external both are equal, will the piston move? Will the piston move? The piston is not going to show any movement at all. If the piston is not showing any movement, that means there will be no exchange of energy via work. There will be no exchange of energy via work. There will be no exchange of energy between system and surroundings via work. So W value will be 0. W value will be 0. Right? And my dear students, one more important thing. Talking about this work, as I told you already, work is the example of path function. It depends on initial final state as well as the path followed. Now, till now, what you observed one thing. You observed one thing. Whenever the piston is showing any movement, whether it's going outside or inside, exchange of energy between system and surrounding is happening via work. Except the free expansion, leave that part aside. Right? So whenever basically the piston is showing any sort of movement going outside or inside, work is either done by the system or is done on the system. If there is expansion, work is done by the system, W value negative. If there is compression, work is done on the system, W value positive. Yeah? Now comes the point. The point is, how do you calculate the work? How do you calculate the work? What is the general expression to calculate work? What is the general expression to calculate work? My dear students, I'm not going to derive this expression because derivation is of no use at this point. We'll see the expression, we'll try to use it in questions, nothing else. Yeah? Okay? General expression to calculate work. My dear students, there is one general expression by means of which we can calculate work. It is minus integral initial volume of the gas to final volume of the gas. This is P external multiplied by dV. This is the general expression by means of which you can calculate the work done. This is the general expression by means of which you can calculate the work done. Understand and remember, this is P external here. This is P external here. Okay? Now, in this chapter only, we have to discuss two things basically. In this chapter only, we have to discuss two things. We have to discuss two things. What are those two things? What are those two things? What are those two things? My dear students, later on, I'll be letting you know that we classify processes into two types. Later on, I'll let you know that we classify processes into two types. One is called as a reversible process. One is called as irreversible process. One is reversible, one is irreversible. What are these irreversible? You'll get the idea afterwards, okay? Just remember right now. In case of reversible processes, what you'll observe? We'll observe in reversible processes, P gas will be almost equal to P external. And in case of irreversible processes, what you'll observe? You'll observe external pressure is constant. You'll observe that external pressure will be constant in irreversible process. Now people, if in reversible process P gas is almost equal to P external, that means when I need to calculate work done in reversible process, when I need to calculate work done in reversible process, when I need to calculate work done in reversible process, what is going to be the expression? Minus integral V1 to V2. V1 to V2. Instead of P external, I'll be writing P gas multiplied by dV. This is the general expression which I'll be using to calculate work in case of what? In case of reversible processes. In case of reversible process. I told you in irreversible processes, P external is constant. If P external is constant, take it out of integral. Integral of dV is V, upper limit, lower limit. So you get the final expression. Work done in irreversible processes is equal to minus P external. It's going to be V2 minus V1. Or you can write it as W irreversible is equal to minus P external delta V. This particular expression, which you'll be using here, this particular expression, which you'll be using here, it is valid only for irreversible process, not reversible process. In reversible process, how do we calculate work? This is how you calculate work in reversible process. This is how you calculate work in reversible process. You have to remember these two expressions for now. I did not derive them because I do not need them. I do not need the derivation. I do not need the derivation. Is this clear? You have to remember them. Their application part you will get to know in some time. Okay, you will get to know how do we solve questions on the basis of them. Okay, let me give you one simple example so that you won't feel bad. Okay, a system means ideal gas. A system undergoes an expansion. A system undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube. System undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure. One of the simplest formula-based question. Against a constant external pressure of 1 Newton per meter square, or let's not call it as 1, just a second. Against a constant external pressure of 10 raised power 5 Newton per meter square. Calculate work done in joules. Calculate work done in joules. One thing which I would want you guys to analyze at this point. MedTalks is saying lab process is reversible. What do we mean by that? I'm unable to get you. Yeah, lab process equal to reversible? Who has told you lab processes are reversible? I'll be discussing reversible, irreversible in detail. Just wait for that, right? There are a lot of things. It's a very big debate, basically. This reversible, irreversible, it's a very tough thing to understand, actually, right? In book, there is a simple line given related to reversible, irreversible, but actually it's a vast topic. It's a very big, huge topic. A system undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure of 10 raised power 5 Newton per meter square. Calculate work. So first of all, try to analyze one thing. Try to understand one thing. It is mentioning that expansion is happening against constant external pressure. Expansion is happening against constant external pressure. When external pressure is constant, the process is supposed to be irreversible. So first of all, the process is irreversible. So we understood the process is irreversible. And in case of irreversible processes, how do we calculate work? In case of irreversible processes, we do not use the integration. So it's going to be minus P external, V2 minus V1. So W irreversible has to be equal to minus P external. P external is 10 raised power 5 Newton per meter square as per SI system. V2 minus V1. V2 is final volume minus initial volume. Minus initial volume, right? Since I have used pressure as per SI system, I have used volume as per SI system. So work, its units will be also there in SI system. Its units will come as per SI system. That means joules. I've used pressure as per SI system. I've used volume as per SI system. So that means the value of W will come as per SI system. That's joules. Agreed? Now tell me one thing. This is going to be 10 raised power 5. Now, if I take 10 raised power minus 3 common, for example, if I take 10 raised power minus 3 common, it's going to be 10 raised power minus 1 divided by 10 raised power minus 3, minus 1, correct? I took 10 raised power minus 3 common. That's all, right? Now, guys, 10 raised power minus 3, 10 raised power 5 makes it 10 raised power 2, correct? 10 raised power 2. 10 raised power minus 3 will go up. It becomes 10 raised power 3. 10 raised power 3 into 10 raised power minus 1 becomes 10 raised power 2, that is 100. 100 minus 1 is 99. So this is the final answer. 99 into 10 raised power 2 joules. This is the work. This is the work. And the sign in the beginning is minus. And this minus sign indicates that it is expansion. Right? Expansion is happening. This minus sign indicates that expansion is happening. Perfect. This is just one simple example. This is a simple example. It's the very basic example which I gave you. So that you can understand how do we use that formula for irreversible. You have to discuss it in detail. Again, I'm telling you, right? Right? I'm just teaching you basic things. Perfecto. Now, guys, try to understand few more things. Just a second. Let me use one slide, which will be already made. That's a prepaid slide, right? Sorry, pre-made, I have to say. I said prepaid. Wow. Just a second. Since, as I told you, the heat and work, they are the mode of transfer of energy. Do remember the units of energy as well. The SI unit of energy is joule. The SI unit of energy is joule. Number one. Number two, the CGS unit of energy is erg. Right? Heat and work, they are the modes of transfer of energy. Perfect. So SI unit of energy is joule. CGS unit is erg. 1 joule is 10 raised per 7 erg. The other units of energy which we shall be using in this chapter, they are ATM liter, bar liter, or calories. These are the other 3 units which we shall be using in this chapter. ATM liter, bar liter, calories. Right? These are the other units of work. Now we have to remember their relationship. Do remember, this is important. 1 ATM liter is equal to 101.3 joules. Something you need to remember. 1 bar liter is equal to 100 joules. Again important. 1 calorie is equal to 4.2 joules. And 1 ATM liter is equal to 24.2 calories. This conversion is very important. So remember it. This conversion is very important. So remember it, guys. Right? This is the relationship between the different units of energy which we shall be frequently using in this chapter. Yeah? Now, guys, I am going to ask you a question. Let me ask you a question. This is not one question, these are 4 questions. These are 4 questions. These are 4 questions. Understand? My dear students, look at the first example. The first example is something like this. 4 times NH3. 4 times NH3 gas plus 7 times O2 gas. It gives what? It gives 4 times NO2 gas plus 6 times H2O gas. Correct? This is the reaction. First of all, as you can see in the reaction, all the reactants and products, they are in gaseous phase. Agreed? They are in complete gaseous phase. They are completely in gaseous phase. Okay? And it's mentioned that all these reactions are happening at STP. That means this particular reaction, it is happening at constant pressure and temperature. It is happening at constant pressure and temperature. Right? As per your ideal gas equation, PV is equal to nRT. Since pressure and temperature is constant, R is already constant. Can I say volume is directly proportional to moles? Absolutely. Volume will be directly proportional to moles. So that means if moles will be increasing, volume will be increasing. If moles will be decreasing, volume will be decreasing. Now look at this particular reaction. Look at this particular reaction. 4 plus 7 makes it 11. So on reactant side, we have got 11 moles. On product side, we have got 10 moles. So when this process is happening, when this reaction is taking place, are the moles increasing or decreasing? The moles are decreasing. If the moles are decreasing, that means the volume will decrease. Decrease in the volume of the system is what we call as compression. And we already know, whenever there is compression, work is done on the system. And whenever work is done on the system, W value, as per sign convention, has to be taken as positive. So in the first process, during the first process, W value is positive. Work is done on the system. Agreed? Agreed? Okay. And this particular concept you'll only use when all the reactants products will be in gaseous state. When all the reactants products will be in gaseous state. And when the reaction will be happening at constant pressure and temperature. This concept you'll use there. Right? The second concept. First concept is done. Second. Gas, liquid. Now state has been changed. It's not a homogeneous reaction. State has been changed. It's liquid now. How do we check it now? My dear students, understand one thing. On reactant side, we have got gases. On product side, we have got liquid. On reactant side, we have got gases. On product side, we have got liquid. So, during the process, gas is getting converted into liquid. During the process, gases are getting converted into liquid. Conversion of gas into liquid. That means molecules will be coming closer. Volume of the system will decrease. Decrease in the volume of the system is what you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W value is taken to be positive. Clear? Clear, guys? Because gases are getting converted into liquid. Yeah? Perfect. All right. One more thing. One more thing. Solid is getting converted into liquid. Whenever a general question comes, a solid is getting converted into liquid. Solid is getting converted into liquid. It is the case of expansion, right? Volume will be increasing basically, right? And increase in the volume is what we call as expansion. Whenever there's expansion, work is done by the system, W value negative. But this is ice here. Ice is getting converted into liquid water. It is not the general case. It is a particular case. It is a particular case. Ice is getting converted into liquid water. My dear students, tell me whether ice has more volume or liquid water has more volume. Ice has got a special cage-like structure. Ice has got a special cage-like structure due to which its volume is more than that of liquid water. Due to which its volume is more than that of liquid water. So ice will have more volume, liquid water will have less volume. So during the process, is the volume increasing or decreasing? Decreasing. Decrease in the volume, compression. Whenever there is compression, work is done on the system. W value, again positive. Correct? Right? Solid is getting converted into gas. Now it's genuine. It's understood. Solid is getting converted into gas. So this is clear cut, the case of expansion. Whenever there is expansion, work is done by the system, W value negative. Perfecto. Is this clear, guys? Quickly in the chats. Is this clear to everyone? Let me know once, quickly. So this was not a single question. These were 4 concepts basically, right? These were 4 concepts. These were 4 concepts basically. I hope you got to know how to use these different concepts to check whether work is done by the system or on the system. Right? I can see not everyone has liked the session yet. What is going on? Don't I deserve a like? Yeah. Okay. Perfecto. Just a second. Let's try to understand one more concept. Let's start with heat capacity, which is denoted by C. Let's start with heat capacity, which is denoted by C. Okay? Heat capacity denoted by C. We discussed a lot of basic stuff, right? And now it's the time to enter into the thermodynamics properly. Okay? A lot of basic things we discussed, and I hope you remember all these basic things. These are very, very, very important. Like whatever we have discussed till now, all the things are equally important. Understand this chapter in depth. Yeah? Perfect, guys. So let's get going with something called as heat capacity. So what is heat capacity all about? Let me first of all write its definition, then I'll make you understand what exactly it means. Yeah? All right, guys. So heat capacity, which is denoted with C. Heat capacity, which is denoted with C. How do you define it? It is defined as the amount of heat. The amount of heat required. The amount of heat required to raise the temperature of the substance. To raise the temperature of the substance by 1 degree. By 1 degree. What it means, you'll get the idea in some time. Before that, this heat capacity, as I told you already, it is the example of extensive property. It is the example of extensive property. Now let's try to understand what this heat capacity is all about, right? Understand, guys, properly understand. For example, imagine that this is the object. Imagine this is the object, right? My dear students, this object right now is under thermodynamic investigation, for example. So this object is my system. It is my system. For example, I want to increase the temperature of this system. I want to increase the temperature of this system. I want to increase the temperature of this object, right? So what do I need to do? I need to give some heat to this object. I need to supply some heat to this object to increase its temperature. For example, in order to increase the temperature by dT units, let's say in order to increase the temperature by dT units, for example, I have to supply dQ amount of heat. I'm supplying dQ amount of heat to increase the temperature, by dT units, right? Okay. I'm going to write the same thing in the form of a statement. I'll say, in order to increase the temperature by dT units, how much heat is required? How much heat is required? As I told you, in order to increase the temperature by dT units, heat required is dQ. Heat required is dQ. Now, my dear students, use the unitary method. In order to increase the temperature by dT units, dQ amount of heat is required. So, in order to increase the temperature by 1 unit, how much heat is required? It has to be dQ upon dt. It has to be dQ upon dt. So, what is this dQ upon dt over here? This is the amount of heat which is required to raise the temperature of the substance by 1 unit. And the amount of heat which is required to raise the temperature of the substance by 1 unit, 1 degree, 1 Kelvin, whatever, right? That's something which you call as heat capacity. So your heat capacity, which is denoted with C, that is equal dQ upon dt. This is the amount of heat which is required to raise the temperature of the substance by 1 unit. Okay. Now, people, if I ask you, what should be the possible units of heat capacity? What should be the possible units of heat capacity? It's simple. In the numerator, you have got heat. In the denominator, you have got temperature. So, one of the units can be joules per Kelvin. One more unit can be joule per degree centigrade. One more unit can be, take the unit of heat in calories, for example. It's going to be calorie per degree centigrade, calorie per Kelvin. The choice is all yours to select the unit, right? It is just in the numerator, you have to keep the unit of heat. In the denominator, you have to keep the unit of temperature. Okay, number one. Number two, try to understand what I'm going to say. Let's assume this is the object whose heat capacity is C. This is the object whose heat capacity is C. Now, my dear students, I want to increase the temperature of this object from T1 to T2. I want to increase the temperature of this object from T1 to T2, right? I want to increase the temperature of this substance from T1 to T2. And I am asking you, how much total amount of heat is required? How much total amount of heat is required to raise the temperature of this object from T1 to T2 if its heat capacity is C. How do we do that? See guys, from this particular equation, I can say dq is equal to C dt. I can say dq is equal to C dt. Perfect. dq is the small amount of heat to raise the temperature by dt units. I want to calculate the total amount of heat. This is small amount. I need to calculate total amount. What do I need to do? I just need to integrate. Just integrate. Over here, you are integrating with respect to temperature, and you are changing the temperature from T1 to T2. You are changing the temperature from T1 to T2. Right? So, my dear students, integral of dq is q is equal to, if c is constant, it comes out, integral of dt is t, upper limit, lower limit, it's going to be c, t2 minus t1, and t2 minus t1 you can represent by delta t. So, what is the significance of this particular equation? What is the significance of this particular equation? Q stands for total heat exchanged between system and surroundings. Q stands for total heat exchanged between system and surroundings. Delta T is the total change in temperature. It is a change in temperature. By supplying Q amount of heat, whatever is the change in temperature, that is delta T, where C is the heat capacity of this object. I hope this is clear. So, for example, I'm giving you a question. Let's say you've got an object. You want to increase its temperature from 5 degree to 50 degree. You have got the object. You want to increase its temperature from 5 degree to 50 degree. Heat capacity is given. How much heat is required? You'll be using this equation. T is given. Temperature difference, delta T, T2 minus T1, right? Simple and basic. So understand this particular thing as well. Remember this particular thing as well. Yeah? Perfect. Now, people, there is one more term. There is one more term. That's called as specific heat capacity. That's called as specific heat capacity. Specific heat capacity is represented by S. And how do we define this specific heat capacity? Let me define it in a very, very simple words. It is defined as heat capacity per unit mass. It is defined as heat capacity per unit mass of the system. Heat capacity per unit mass of the system, right? So specific heat capacity, it is equal to heat capacity per unit mass of the system, right? Now, my dear students, you already know that if you got the relation, you can just let me know the units. Or before talking about the units, you can write it like this as well. What is C? Heat capacity, which is dq upon dt. So it becomes dq upon mdt. It becomes dq upon mdt. Now you can talk about the units of specific heat capacity. It is just, you have to keep one thing in mind, that in the numerator there is heat. So in the numerator you have to write the unit of heat, and in the denominator it's mass as well as temperature, right? So one of the unit, for example, one of the unit is going to be joule per, let's say mass I'm taking in kg and temperature I'm taking in Kelvin, for example. So this can be one of the unit. You can make a lot of other units as well. Yeah, simple and basic. Now, dear students, S is equal to dq upon m dt. So can I say dq will be equal to ms dt? dq is equal to ms dt. Now imagine that this is the object whose mass is m, whose specific heat capacity is S, and you want to change its temperature from T1 to T2. For example, you want to increase its temperature from T1 to T2. And I'm asking you to calculate the total amount of heat, required to raise the temperature of this object, whose mass is m, whose specific heat capacity is S, from T1 to T2. What again you'll be doing? Again, you'll be integrating under the limits T1 to T2. So this is going to be Q, this is going to be ms will come outside. Integral of dt is t, upper limit, lower limit. So it's going to be ms delta t. Ms delta t. This is one more way. This is one more way of calculating the heat absorbed or heat released by the system. This is one more way of calculating the heat absorbed or heat released by the system. Right? First formula is Q is equal to C delta T. If the heat capacity of the object is given, you have to use the relation Q is equal to C delta T. If the specific heat is given, then you have to use the object ms delta T. Right? Now, at the same time, Heat capacity is extensive. Whenever an extensive property is expressed per unit mass, what do you call it as? The new property becomes intensive. So specific heat capacity, it is the example of what? It is the example of intensive property. I hope you remember that. I've already discussed that with you. Right? Now, similarly, the third parameter, what is that? That is the molar heat capacity. Molar heat capacity, right? Which is denoted by Cm. Molar heat capacity, which is denoted by Cm. How do you define this molar heat capacity? Again, let's try to define it in a very simplified manner, right? Yeah. My dear students, molar heat capacity is defined as, it is defined as the heat capacity. It is defined as the heat capacity per unit mole of the substance, right? Heat capacity per unit mole. How do you write it? How do you write it? Cm, molar heat capacity. It is heat capacity per unit mole. Heat capacity is dq upon dt. So it becomes dq upon n dt. Now, dear students, you can talk about its units as well. You can talk about its units as well. Yeah. For example, heat is joules. In the numerator, you have got mole, and temperature, for example, that's Kelvin. So it can be one of the possible units of molar heat capacity, right? Now look at this particular equation. Cm is equal to dq upon n dt. So can I say dq is equal to n Cm dt? dq is equal to n Cm dt. Now imagine that you have got a container, and this particular container, for example, it contains n moles of ideal gas. It contains n moles of ideal gas. I'm assuming that the molar heat capacity of the ideal gas is Cm. I want to increase the temperature of this ideal gas from T1 to T2. I want to increase the temperature of this ideal gas from T1 to T2. If I ask you how much heat is required, to raise the temperature of n moles of ideal gas from T1 to T2, if its molar heat capacity is Cm, how do you do that? You'll be integrating it with respect to temperature, T1 to T2. Integral of dq is q. N comes out, Cm comes out. Integral of dt is t, upper limit, lower limit. So it's T2 minus T1, which comes out be delta T. Right? This is one more way of calculating the heat exchange between system and surroundings. This is one more way of calculating the heat exchange between system and surroundings. Yeah? Is it clear, guys? Is it clear? This is one more way of calculating the heat exchange between system and surroundings. Like how much heat is absorbed or released by the system. How much heat is absorbed or released by the system if its temperature is changed by delta T units, right? If the molar heat capacity of the system is Cm. This is the relation which you'll be using. Now there'll be one more thing. Heat capacity is extensive. Whenever extensive property is expressed per unit mole, the new property that comes into existence, that's going to be intensive, right? Something which we already discussed. Extensive property expressed per unit mass, per unit mole, or per unit volume. The new property becomes intensive in nature. So my dear students, why I am telling you all these things? All these things, there's a motive for that. Why is that? Have a look. I'm writing the heading as heat exchange. What is meant by heat exchange? That means the amount of heat absorbed or released by the system to change its temperature. Let's say you want to change the temperature of the system. Either you want to increase the temperature or you want to decrease the temperature. If you want to increase the temperature of the system, then heat has to be absorbed by the system. If temperature of the system has to be decreased, then heat has to be released by the system. Now, how do we calculate the amount of heat absorbed or released by the system? How do we calculate the amount of heat absorbed or released by the system? Either to increase its temperature or decrease its temperature. There are many ways to do that. There are many ways to do that. First way. If heat capacity of the system is given, then how do we calculate Q? It is equal to C delta T. If specific heat capacity is given, then Q has to be equal to Ms delta T. And by chance, if molar heat capacity is given, then Q is to be calculated by this result, Ncm delta T. Whenever you are asked to calculate the amount of heat absorbed or released by the system, whenever you are supposed to calculate the amount of heat absorbed or released by the system, you have to use one of the result from these three, depending on what parameter is given. If C is given, use this result. If S is given, use this result. If Cm is given, use this result. Right? Now, people, over here, there are two things. Over here, there are two things. I'll write at constant volume, and here I'm writing at constant pressure. At constant pressure. Molar heat capacity when defined at constant volume. Molar heat capacity per unit mole, when defined at constant volume. At that point of time, you'll be representing it with CV. Molar heat capacity defined at constant pressure. At that point of time, you'll be representing it with CP. Now, at constant volume, you are not going to write Q. You'll be writing QV. QV will be equal to NCV delta T. And over here, you'll be writing QP. QP will be equal to NCP delta T. These are two very, very, very important results which I would want you guys to remember. Now, let me just tell you the significance of these two results. My dear students, first thing, what is CV? How do you define the CV? What is CV? CV is basically molar heat capacity. Molar heat capacity at constant volume. It is molar heat capacity at constant volume. What about CP? CP is molar heat capacity at constant pressure. At constant pressure. At constant pressure. Now, if you are asked to calculate the heat absorbed or the heat released by the system at constant volume, whenever this kind of question comes, calculate the heat absorbed or heat released by the system at constant volume. Understand, you have to calculate the value of QV. And QV, as for the result, it's equal to NCV delta. And whenever you are supposed to calculate the heat absorbed by the system or the heat released by the system at constant pressure, then you have to use this particular result to calculate QP. So two questions can be asked. Calculate the heat absorbed or released by the system at constant pressure. That means QP you have to calculate. Calculate the heat absorbed or released by the system at constant volume. That means QV you have to calculate. One is NCV delta T, one is NCP delta T. I hope this is clear. I hope this is clear. Right? I hope this is clear. Guys, there are few points which I would want you guys to remember directly from now onwards. Right? Let's not go into the details. Let's remember them directly and try to apply them in the questions. Right? Do remember a few important parameters. For a particular gas, CP value is always greater than CV. For a particular gas, CP value is always greater than CV. What is CP? Molar heat capacity at constant pressure. Molar heat capacity at constant volume. For a particular gas, its CP will be always greater than CV. What is CP actually? What is CP actually? How do you define CP actually? I'm telling you it's molar heat capacity at constant pressure. What does that mean? It is basically the amount of heat required to raise the temperature of 1 mole of the substance by 1 degree, keeping its pressure constant. And my dear students, what is CV? It is the amount of heat. It is the amount of heat required to raise the temperature of 1 mole of the substance by 1 degree, keeping its volume constant. I hope you are getting the difference between the two. I hope you are getting the difference between the two. I'm telling you for a particular gas, CP is greater than CV. for a particular gas, Cp is greater than Cv. Why is that? If I ask you why is that, what should be your logic behind this? Try to understand what I'm going to say. Try to understand what I'm going to say. I just did not want to teach this in so much of detail, but okay, let's go for it. For example, these are two containers. Understand what I'm going to say. Okay, this is important. For example, I've got two containers. Over here, I'm using a movable piston, the piston which can move upwards, downwards. Over here, the piston is non-movable. Non-movable. That means the piston cannot move. It cannot go up or down, right? Let's assume you have got 1 mole of ideal gas here. Let's assume you have got 1 mole of ideal gas here as well. Okay, 1 mole of ideal gas here, 1 mole of ideal gas here as well. Perfect. Try to understand what I'm going to say. You have got 1 mole of ideal gas in both the containers. Now, my dear students, this piston is non-movable. That means volume of this container is not going to change. That means volume of the gas is not going to change. So I'm keeping the volume constant over here. And here, I'm going to keep the pressure constant. I'm not going to let the pressure of the gas to change. And here, I'm not going to let the volume of the gas to change. Here, I'm not going to let the pressure of the gas to change. Here, I'm not going to let the volume of the gas to change. We have got 1 mole of ideal gas in both the containers. Okay. Over here, 1 mole of ideal gas is present at constant pressure. Over here, 1 mole of ideal gas is present at constant volume. For example, I want to increase the temperature of 1 mole of ideal gas by 1 degree. I want to increase the temperature of 1 mole of ideal gas by 1 degree. Provided when I increase the temperature of the gas, volume of the gas should not change. Piston should not move. Let's assume in order to increase the temperature of 1 mole of the ideal gas by 1 degree, keeping its volume constant, let's assume I have to supply 100 joules of heat. Let's say I have to supply 100 joules of heat. For example, 100 joules of heat are enough to increase the temperature of 1 mole of ideal gas by 1 degree at constant volume. And you know the amount of heat required. The amount of heat required to raise the temperature of 1 mole of ideal gas by 1 degree at constant volume. You call that as Cv, right? You call it as Cv. Perfect? Right? Yeah? My dear students, since the piston is not moving at all, when you are supplying this much of heat, this entire heat which you are supplying, it is used to increase the temperature of the gas only. The piston is not moving at all. But when you start to raise the temperature of this gas, when you start to supply heat, what is going to happen? The piston is movable. The piston is movable. My dear students, when you start to supply heat here to raise the temperature by 1 degree, you want to raise the temperature by 1 degree. So what you'll be doing? You'll be supplying heat. But when you'll be supplying heat, the kinetic energy of molecules will increase. Kinetic energy of molecules will increase. And when the kinetic energy of molecules will increase, what will happen? Collisions in the container will increase. The pressure will start to increase. But do I have to let the pressure to change? I do not have to let the pressure of the gas to change. I do not have to let the pressure of the gas to change. Perfect? So I'm supplying heat basically. I just wanted to increase the temperature of this gas by 1 degree. So I'm supplying heat for that. But what is happening? When I'm supplying heat, the kinetic energy of molecules is increasing. The pressure starts to increase. But I do not have to let the pressure of the gas to increase. So what should happen? What should happen? Since I'm supplying heat, collisions are increasing. So can I say, in order to keep the pressure same, in order to not, if you do not want to increase the pressure of the gas, what should happen? The piston should go up so that molecules will go far and pressure will remain constant. It will remain fixed. So again, I'm repeating the same thing. Just understand what I'm trying to say. You have got 1 mole of ideal gas. You want to increase its temperature by 1 degree. So you're supplying heat. You're supplying heat. Whatever heat you are supplying, due to that, what is happening? Kinetic energy of molecules is increasing, due to which pressure will start to increase. But I do not have to let the pressure of the gas to increase. So what should happen? Piston should go up so that molecules will again go far, due to which the pressure will remain the same. It won't change. It won't increase. So my dear students, the amount of heat which I'm supplying, it is basically divided in two parts over here. Some part of heat some part of heat is used to increase the temperature, and the remaining part of heat is used to take the piston up. If the piston is going up, that means volume of the system is increasing. If the volume of system is increasing, that means this is the case of expansion. Whenever there is expansion, work is done by the system. So basically, whatever heat you are supplying here, some part of heat is used to increase the temperature, and the remaining part of heat is used for the work so that the pressure remains constant. Perfect. Imagine that you were expecting that you will have to supply 100 joules here also to increase the temperature by 1 degree. But let's imagine that out of 100, 20 joules is used for work so that pressure remains constant. Other 80 joules are used to increase the temperature. Are 80 joules enough to increase the temperature by 1 degree? No. 100 joules are enough to increase the temperature by 1 degree. So can I say from outside only, I won't have to supply 100 only. I'll have to supply 120 joules. So that, for example, 20 joules are used for work and rest 100 joules are used to increase the temperature by 1 degree. And whatever amount of heat you are supplying at constant pressure, that's what you call a CP. So CP and CV, which one is more? For a particular gas, CP value is always more than CV. Because some part of heat supplied during the constant pressure is used for work. Let me write it. I hope this statement is clear to you. Yeah? So let me once know in the chats if it is clear. As I told you, CP for a gas is always greater than CV. Why? Because some amount of heat is used for work to keep the pressure constant. To keep the pressure of the gas constant, fixed. I hope this is clear, right? I hope this is clear. So CP is always greater than CV. If CP is greater than CV, if I take the difference between the two, CP minus CV, this is more, this is less. So the difference has to be positive. And this is equal to R. CP minus CV is equal to R. And it's valid for 1 mole of ideal gas. It is valid for 1 mole of ideal gas. CP minus CV is R. And here I'm defining a term, gamma, which stands for Poisson's ratio. Poisson's ratio. It is equal to CP divided by CV. Gamma is equal to CP divided by CV. We got to know CP is greater than CV. So CP divided by CV, its value has to be greater than 1. So gamma value will be greater than 1. For 1 mole of ideal gas, CP minus CV is R. For 2 moles of ideal gas, CP minus CV will be 2R. For n moles of ideal gas, CP minus CV will be NR. CP minus CV will be NR, right? There is one more result which you need to remember directly. There is derivation as well, but I'm not deriving it. It's of no use for us, right? Do remember CV is equal to R divided by gamma minus 1. This is one more result, which we'll use frequently in this chapter, right? These are few results which I would want all of you to remember from now onwards. These are all very, very, very important results. These are all very, very, very important results. Okay? And my dear students, there is a particular table which I'm going to give you, and you have to remember the values as well. So over here, I'm mentioning CV, over here, I'm mentioning CP, and over here, I'm mentioning gamma, which is CP divided by CV. Now, imagine that you have got a monoatomic gas. Imagine that you have got a monoatomic gas, like helium. Like helium, it is monoatomic. Do remember, CV for monoatomic gases, it's always equal to 3 by 2R. CP for monoatomic gases, it's always equal to 5 by 2R. And gamma value, which is CP by CV, this divided by this, so it comes out to be 5 by 3. 5 by 3 is just 1.66, right? Now, for example, you will be having a diatomic gas. Diatomic gas, like O2. Or for example, you have got triatomic linear gas. Let's say you have got triatomic linear gas. For example, carbon dioxide. Carbon dioxide is triatomic and at the same time it's linear as well, right? Its CV is going to be 5 by 2R. CP is going to be 7 by 2R. and its gamma is going to be Cp by Cv, so it comes out to be 7 by 5, which is 1 point, right? Similarly, if you will be having a triatomic non-linear gas like SO2, it is triatomic and at the same time it's bent, it's not linear, it's Cv. Okay, or I'll write polyatomic gases. Their Cv will be equal to 3R, this is equal to 4R, and this will be equal to 4 by 3. The value comes out to be 1.33. Okay, this is the table which you have to remember because we are going to use these values frequently in this chapter. Okay, tell me one thing. First gas was monoatomic, the second is diatomic, triatomic. So as you go from top to bottom, what is happening to the atomicity? What is happening to the atomicity? This is monoatomic, atomicity 1, diatomic, atomicity 2, triatomic, atomicity 3. So on moving from top to the bottom, atomicity is increasing. And as the atomicity is in a value, it tries to decrease, right? So do remember this particular point as well. This is again important. I hope this is super clear to you. Now, my dear students, before doing the questions, before talking about the actual stuff, there are a few more things. What is that? See, I'm writing Cv for a mixture of non-reacting gases. All these concepts I'll be using in the questions. Cv for a mixture of non-reacting gas. Cv for a mixture of non-reacting gas. So for example, imagine this is a container. And this container contains two gases, gas 1 and gas 2. It contains two gases, gas 1 and gas 2. By chance, these gases are chemically non-reacting gases. These are chemically non-reacting gases. So can I say I have got a gaseous mixture containing chemically non-reacting gases? Absolutely. Let's assume molar heat capacity at constant volume for gas 1 is Cv1. For gas 2 it is Cv2. Let's assume molar heat capacity at constant pressure for gas 1 is Cp1. And over here it's Cp2. Let's assume moles of gas 1 in the container are N1. Moles of gas 2 in the container are N2. Now, my dear students, if you have to define Cv for the mixture, Cv for the gaseous mixture, there is a simple result which you'll be using. N1 Cv1 plus N2 Cv2 plus N3 Cv3 plus dash 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 divided by N1 plus N2. Divided by N1 plus N2 plus dash. This is the result by means of which we can calculate molar heat capacity at constant volume for a mixture of chemically non-reacting gases. Similarly, if you are supposed to calculate Cp for the mixture, Cp for the gaseous mixture, it's going to be equal to N1 Cp1 plus N2 Cp2 plus N3 Cp3 divided by N1 plus N2 plus dash dash. This is the formula by means of which we can calculate the molar heat capacity at constant pressure for a mixture of gas. Yeah. And dear students, already you know Cp minus Cv is R. So Cp mixture minus Cv mixture. That has to be equal to R. Right? If I ask you, what about the value of gamma for the mixture? The value of gamma for the mixture has to be equal to Cp mixture divided by Cv mixture. Cp mixture divided by Cv mixture. These are some very, very, very important results which you have to remember. And all these results I'll be utilizing in the questions afterwards. Okay? Yeah? And now guys, if all these things are clear, now it is the time to discuss one of the most important topics of the chapter. That is what you call as internal energy. Internal energy. So till now, I used the term internal energy many a times, right? Okay. And I used to tell you we have to discuss this in detail. Now it is the time to discuss the internal energy in detail. Internal energy, it is represented by U, or you can represent it by E. So understand logically what this internal energy is all about. How do you define the internal energy? My dear students, in simpler words, In simpler words, I can say internal energy, it is basically the sum of kinetic and potential energy present in the system. Internal energy is actually the sum of kinetic and potential energy present in the system. The total kinetic energy and the total potential energy present in the system, that gives you the internal energy. For example, what does that mean? For example, let's say this is the container. Let's say this is the container, okay? Let's assume in this container we have got a real gas. There's a real gas in the container, right? These are the real gas molecules. Now, my dear students, if I ask you, let's assume that the container is at rest. Container is at rest, right? This is something which I'm assuming. Now, you tell me, these real gas molecules, whether they'll be in motion or they'll be at rest. These real gas molecules, they'll be in constant random motion. They'll be showing translational motion, rotational motion, vibrational motion, etc. And due to motion, which energy arise? Right? Due to motion, which energy arise? It's kinetic energy, right? So can I say these molecules, they'll be in random motion, due to which I can say these molecules will have kinetic energy. These molecules will have kinetic energy. It can be translational kinetic energy, rotational kinetic energy, right? Anything. And apart from that, since it's a real gas, between the real gas molecules, there will be interactions. There are interactions between real gas molecules. And due to interactions, which energy comes into play? Due to interactions, potential energy comes into play. Due to interactions, potential energy comes into play. So if it is the real gas, due to motion, kinetic energy will come into play. Due to interactions, potential energy will come into play. If you will take the sum of all the kinetic energies and all the potential energy present in the system, you'll be getting the value of internal energy of the system. In short, you are getting the total energy of the system. You are getting the total energy of the system, which is the sum of total kinetic and total potential. Kinetic is due to motion and potential is due to interaction. It is due to interaction. So this is how you define internal energy for a real gas. For a real gas. Now, for the ideal gas, just tell me one thing. Just tell me one thing. If this was the ideal gas, will there be any interactions between the ideal gas molecules? There are no interactions. If there are no interactions, what will be the value of this potential energy for the ideal gas? It will be zero. Potential energy comes into play due to interactions. If in ideal gas there are no interactions, so PE value will be zero. So U is equal to total kinetic energy for the ideal gas. For the ideal gas. Perfect. Perfect. Right? For the ideal gas, internal energy is basically the sum of all the kinetic energies present in the system. For the real gas, it is the sum of all kinetic energies and potential energies present in the system. I hope you're getting it. Point number one. Point number two. If I talk about internal energy now, if I want to define the internal energy, if I want to write the definition of internal energy, how do I write it? Internal energy is basically the sum total of all the possible kinds of energies present in the system. And the system has to be at rest. The container has to be at the rest in which the gas is present. Okay? Now, people, you tell me one thing. Whether this internal energy is going to be a extensive or intensive property. What is internal energy basically? The total energy in the system. If you change the amount of substance, if you increase or decrease the molecules of gas in the container, the total energy automatically will change. That means internal energy is changing. So internal energy, it is the example of what? Extensive property. Its value changes on changing the amount of substance present in the container, amount of substance present in the system. Now the same internal energy, it is a state function as well. Its value only depends on initial and final state. It is path independent. If internal energy is a state function, you'll be calculating its change, and change in the value of internal energy is equal to U final minus U initial. Okay? Now you tell me one more thing. Tell me one more thing. For a cyclic process, change in internal energy has to be 0, because we know for a cyclic process, change in the value of a state function is always 0. Change in the value of state function for a cyclic process is always 0. Yeah? Okay. One more thing. Internal energy, it is the function of volume and temperature. Internal energy depends on two parameters. Internal energy of the gas, it depends on volume as well as temperature. But for a real gas, for an ideal gas, internal energy only depends on temperature. For an ideal gas, internal energy only depends on temperature. It only depends on temperature. Now, my dear students, here I have to teach you a bit of mathematics so that you can understand this internal energy in detail. Understand what I'm exactly going to do. Understand what exactly I'm going to do. Whenever you write y is equal to f of x, what does it mean? It means that y depends on x. X is the independent variable, y is the dependent variable. If you change the value of x, the value of y will automatically change. If you change the value of x, the value of y will automatically change. And that change in the value of y due to the change in x, that is represented by dy by dx. Change in the value of y due to change in x, that is represented by dy by dx. Correct? Now, my dear students, just try to understand what I'm going to say. For example, you have got a function in this format. Let's say I'm writing z is equal to f of x comma y. Z is equal to f of x comma y. What does it mean? It means that z depends on two variables. It depends on x as well as y. So if you change x, z will change. If you change y, z will change. Z is depending on two variables. So if you change x, z will change. If you change y, z will change. Correct? So if I want to calculate the total change in z, how do I do that? Over here, I'm not going to use the normal differentiation which you do. Over here, I'll be using the partial differentiation. And try to understand what I'm going to say. My dear students, I'll be writing. What I'll be doing? I'll try to keep y constant. First, I'll try to keep y constant. I'll try to change x. If x changes, there will be change in z. So that change in z due to change in x, I'll calculate. Right? How do I represent it? Change in z due to change in x. Keeping what constant? Keeping y constant. So first of all, my first step is I kept y constant. I changed x. And I saw the change in the value of z due to change in x, keeping y constant. So from here, I can get the dz value. Dz is going to be equal to dou z upon dou x at constant y multiplied by this dx. This was my first step. Now look at my second step. Now I'm going to keep x constant. And change the value of y. And when y changes, z will automatically change. I'm going to keep x constant. We'll try to change y. And on changing y, z will change. And then I'll try to calculate change in the value of z due to change in y. How do I represent it? Change in z due to change in y, keeping what constant? Keeping x constant. And from here, I can get the value of dz. Dz is going to be equal to dou z upon dou y, keeping x constant, multiplied by dy. I got two things. Change in z due to change in x, keeping y constant. Change in z due to change in y, keeping x constant. So if I want to calculate the total change in z, that means I have to take the sum of these two. So the total change in z is going to be dou z upon dou x, keeping y constant, multiplied by dx, plus dou z upon dou y, keeping x constant, multiplied by dy. Right? So this equation gives me the total change in z. Right? Change in Z due to change in X, keeping Y constant, and change in Z due to change in Y, keeping X constant. Take the sum of both, you'll be getting the total change in Y. Total change in Z. I hope you got this. Did you get this? Say yes or no in the chats once. Then only I can move ahead. Did you get this? Did you get this quickly? Yeah? Okay, do you know why did I do this? Do you know why did I do all this stuff? There is a reason for that. There is a reason for that, my dear students. Try to understand what I'm going to say. I told you for a real gas, internal energy is the function of volume and temperature. For a real gas, internal energy is the function of volume and temperature. So internal energy depends on two variables, volume as well as temperature. So if I want to calculate the total change in internal energy, what will be the total change in internal energy, which I'm representing by du? First, it's going to be change in internal energy due to change in volume, keeping what constant? Keeping temperature constant, multiplied by dV, right? And then I'm going to write change in internal energy due to change in temperature, keeping what constant? Volume constant, multiplied by dt, right? And I hope you now know exactly how this equation comes. I hope you exactly know how this particular equation comes. Okay, so this particular equation, it gives me the total internal energy change, right? It gives me the total internal energy change. But this is the equation for which gas? Real gas. I don't have to talk in terms of real gas. I have to talk only about the ideal gas, right? So what exactly I'll be doing? For an ideal gas, if I want to write the same equation for an ideal gas, how do I write it? See, in this particular equation, you have got two terms. Can you let me know which term will be zero for ideal gas? Which term will be zero for an ideal gas? Ideal gas internal energy only depends on temperature. It does not depend on volume. Ideal gas internal energy, it depends only on temperature. It does not depend on volume. So change in internal energy due to change in volume for the ideal gas, that has to be zero, right? If you change the volume of the ideal gas, will its internal energy change? Its internal energy won't change. So this particular term for the ideal gas, it has to be zero. That means for the ideal gas, du will be equal to dou u upon dou t at constant volume multiplied by dt. And this particular equation, it's actually valid for 1 mole of ideal gas. It's actually valid for 1 mole of ideal gas. And my dear students, this particular term, change in internal energy due to change in temperature, keeping volume constant. Change in internal energy due to change in temperature, keeping volume constant. It is actually called as CV. So du comes out to be CV dt. And this equation is valid for 1 mole of ideal gas. If you will be having 2 moles of ideal gas, it's going to be 2 times CV dt. 3 moles, 3 times CV dt. N moles of ideal gas, it's going to be du is equal to NCV dt. du is equal to NCV dt. Tell me the significance of this particular equation. Tell me the significance of this particular equation. For example, you have got N moles of ideal gas in the container. You have got N moles of ideal gas in the container. You are changing the temperature of the ideal gas by small dt. By small dt. If you are changing the temperature of ideal gas, definitely its internal energy will change. How much? du. du is the small change in internal energy due to small change in temperature of N moles of ideal gas whose molar heat capacity at constant volume is CV. Correct? Right? So you got to know du is equal to NCV dt. Try to understand one important thing now. Try to understand one important thing. Imagine that you have got ideal gas. Imagine that you have got ideal gas in the container. For example, this is the container. It contains N moles of ideal gas. N moles of ideal gas. Molar heat capacity of ideal gas is CV. Now you want to change the temperature of the ideal gas from T1 to T2. If you are changing the temperature of the ideal gas, definitely its internal energy will change. And I'm asking you to calculate that change in internal energy. How you're going to do that? You're simply going to integrate. With respect to temperature, you are changing from T1 to T2. Integral of du has to be delta u. So delta u is equal to integral T1 to T2. It's going to be N CV and it's going to be dt. So this is the general result by means of which you can calculate the internal energy change of the ideal gas when you'll be changing its temperature from T1 to T2. From T1 to T2. Now, dear students, this is first of all important equation. Now, for example, if CV was temperature independent, if CV does not depend on temperature, if CV is constant, take CV out, N already out, so delta U will be equal to N CV. Integral of dt is T, upper limit, lower limit, so it's T2 minus T1. T2 minus T1, right? Or you can write it like this, delta U is equal to N CV delta T. So this particular equation is used when CV for the gas is temperature independent. Temperature independent CV, temperature dependent CV, right? If in the equation they mention that CV depends on temperature, then how do you calculate delta U? Through this result, right? Perfect. And if they say that CV is constant, then this particular result you'll be using. I hope this is clear. Now we will try to understand one more thing. Try to understand one more. See guys, imagine that you have got an ideal gas. For an ideal gas undergoing isothermal process. For an ideal gas undergoing isothermal process. What does that mean? That means you are changing the state of the gas. You are changing the state of the gas without changing its temperature, right? So temperature of the gas is kept constant. If temperature is constant, delta T has to be 0. If delta T is 0, that means delta U has to be 0. So do remember that particular ideal gas, right? When the ideal gas undergoes isothermal process, its delta U has to be 0. But this is particularly valid for ideal gas, right? One more thing. I told you delta U is equal to NCV delta T, correct? Right? Now, my dear students, it's evident. If delta U is positive, that means T2 minus T1 should be positive. T2 minus T1, when it's going to be positive? I'm telling you something like this. If delta U for the ideal gas comes out to be positive, what does that mean? That means U2 minus U1 is coming out to be positive for the gas. So what does that mean? That means U2 is greater than U1. What does that mean? That means the internal energy of the gas is increasing. If delta U is positive, that means the gas's internal energy is increasing. Now simple, right? If delta U is positive, that means T2 minus T1 has to be positive. So T2 has to be greater than T1. So it clearly tells you T2 has to be greater than T1. Perfect. So what does this mean? This means that on increasing the temperature of the gas, internal energy of the gas increases. Right? On increasing the temperature of the gas, internal energy of the gas increases. So you can categorically say U is directly proportional to T. Internal energy is directly proportional to temperature. And it's evident also, when you increase the temperature, what will happen? The internal energy, the total energy present in the system, that will increase. As simple as that. Right? Now, my dear students, one simple thing if I ask you, please see if you can solve this one or not. One simple thing I'm asking. One simple thing. For example, I'm giving you a graph. Or let's not go to the graph yet. Let's try to understand one. Few minutes back, I told you du is equal to NCV dt. Correct? du is equal to NCV dt. For 1 mole of ideal gas. If say du will be equal to Cv dt, absolutely. So can you calculate Cv from here? It's going to be du upon dt. Cv is equal to du upon dt. What is the meaning of this du upon dt? It gives you the slope of tangent. It gives you the slope of tangent at a point. Slope of tangent at a point on internal energy versus temperature curve. It gives you the slope of tangent at a point on internal energy versus temperature curve. Now, my dear students, you can say more the slope, more the CV. For example, I'm giving you a question like this. Let's say this is the graph. For example, hypothetical question. Internal energy versus temperature for 1 mole of gas or 1 mole of ideal gas. The graph is, for example, like this. And for example, what exactly I'm doing, I'm selecting 2 points. This is point A and this is point B. I'm asking you at which point CV value is more. Is CV at A more than that of CV at B or less than that of CV at B or equal to that of CV at B? What do you think? What exactly you'll be doing? You'll be extending this line. You'll be drawing a tangent here. You'll be drawing one more tangent here. Correct? Now measure the angle. This is theta A and this is theta B. Now you are going to tell me which theta is more. Theta A is more than that of theta B. So can I say tan of theta A will be also greater than that of tan of theta B? Absolutely. So can I say slope at A is greater than that of slope at B? And wherever slope is more, CV value has to be more. So CV at A will be greater than that of CV at B. If this is clear, let me know in the chats quickly. Every one of you. This was all about your internal energy, my dear students. Quickly, everyone. Everyone in the chats. Is this clear? Okay, if this is clear, can you solve one simple question if I give you? Just try to solve this question. Let me see if you can solve this one or not. The question is, just wait a second. Before doing the question, few minutes back, we discussed one thing. We discussed how to calculate QV. QV was equal to NCV delta T. And few minutes back, you saw one more thing. NCV delta T is basically the value of delta U for the ideal gas. NCV delta T is basically the value of delta U for the ideal gas. So take a note of one important thing. What is QV? QV is basically heat absorbed or released by the system. Heat absorbed or released by the system at constant volume. Is always equal to internal energy change. So question can be asked in 2 ways. My dear students, either they'll ask you directly calculate the internal energy change delta U, NCV delta T, or they can ask you calculate the heat absorbed or heat released by the system at constant volume. Whenever they ask you calculate the heat absorbed or released by the gas at constant volume, understand you have to calculate delta U only. And delta U is nothing, that's NCV delta T for the ideal gas. Okay, so do remember this particular thing as well. So question can be asked in 2 ways. Either they'll ask directly the value of delta U, or they can ask you calculate the heat absorbed or released by the gas at constant volume. Okay. Now, if I give you one question like this, calculate delta U in joules. When 10 decimeter cube of helium gas at STP is heated to 100 degrees centigrade, assuming ideal gas conditions. Can you give it a try? Can you give this question a try? Can you solve it? Can you give it a try? See guys, how to solve this. As far as the question is concerned, you have got 10 decimeter cube of gas. 10 decimeter cube means 10 liters because 1 decimeter cube is equal to 1 liter. So 10 decimeter cube of helium gas you have. Helium gas you have. Where at STP. At STP. That means the temperature of the gas is 0 degrees centigrade. The pressure of the gas is equal to 1 atm. So we have got a gas. Basically, we have got a gas whose volume is 10 decimeter cube, whose temperature is 0 degrees centigrade, pressure is 1 atm. Now, what exactly you are doing? You are changing the temperature of the gas from 0 degree till 100 degree. Till 100 degrees centigrade. Since you are changing the temperature of the ideal gas, on changing the temperature, what is going to happen? On changing the temperature, internal energy will change. Since you are increasing the temperature, so internal energy will increase. And we have to calculate that change in internal energy. We have to calculate that change in internal energy. So delta U we have to calculate. Delta U we have to calculate. My dear students, how do we calculate delta U? First of all, try to understand whether it's mentioned in the question where that CV is temperature dependent. It's not mentioned anywhere. CV is temperature dependent. It's not mentioned, right? So you'll be taking the value of CV as constant. You'll be taking the value of CV as constant. And when CV is constant, delta U has to be equal to NCV delta T. NCV delta T means NCV T2 minus T1. NCV T2 minus T1. So delta U will be equal to N stands for number of moles of gas. You had 10 liters of gas at STP. 10 liters of gas at STP means how many moles? Given volume divided by 22.4. So these many moles we have. CV for helium. Helium is monoatomic. For monoatomic, CV is 3 by 2 R. 3 by 2 R. T2 minus T1. T2 minus T1. T2 is T2 minus T1. The difference of the temperature is going to come as 100. Now you have to get the answer in joules. If you have to get the answer in joules, which value of R you'll be using? If you need to get the value of delta U in joules, you'll be using the value of R as 8.314 and multiplied by 100. You need to solve this particular term and get the answer of delta U, particularly in joules. That's how you solve it. I hope this is clear. Let me know once in the chats if it's clear, people, quickly. Is this clear to everyone? Is this clear to everyone quickly in the chats? Guys, thermodynamics cannot be done in one shot. I don't know. The thumbnail is wrong. It's not one shot. It will be done in 2 sessions. One is today's session. Another session will happen on Saturday, day after tomorrow at 5 p.m. Okay? Because it's a huge chapter. No way it's going to complete it in like one session. I mean, it can be completed if the session duration was 10 hours. Okay, is it clear to you? All right, guys. So try to understand one more thing. Try to understand one more thing. There is something called as first law of thermodynamics. There is something called as first law of thermodynamics. First law of thermodynamics. What this first law of thermodynamics is all about? First thing, it is the energy conservation principle. It is the energy conservation principle. It is the energy conservation principle. Point number 1. Point number 2. Point number 2. When the state of the system changes, when the state of the system changes, there will be change in its internal energy. There will be change in its internal energy. which can be brought about, guys, can you write it? I'll dictate. Which can be brought about in two ways. Which can be brought about in two ways. Number one, when heat is absorbed or released by the system. When heat is absorbed or released by the system. Number two, when work is done by or on the system. When work is done by or on the system. What does it mean? Let's try to decode all these things, right? Let's try to decode all these things mathematically. And mathematical interpretation is just important. Nothing else with the definitions and stuff. Okay? See guys, try to understand now properly what I'm going to say. For example, this is the container. For example, this is the container. And this container, let's imagine that it contains an ideal gas. It contains an ideal gas. This is the piston fitted at the top, right? Let's assume the gas is right now present at its initial state. Let's assume that the gas is present at its initial state. Let's assume that the total energy present in the system right now is U1. U1 stands for total energy present in the system. Yeah? Total energy present in the system, which is called as internal. So internal energy, when the system is present at initial state, is U1. Now, what exactly we will be doing? For example, I am supplying Q amount of heat to this gas. For example, I'm supplying Q amount of heat to this gas. For example, I'm supplying Q amount of heat to this gas. My dear students, when you supply Q amount of heat to this gas, can you tell me what will be the total energy possessed by the gas now? Initially, the total energy of the gas was U1. Now it's going to be U1 plus Q. This is the total energy possessed by the gas now. This is the total energy possessed by the gas. Correct? For example, let's assume that W amount of work is done on the system. And when W amount of work is done on the system, what will happen? Let's assume W amount of work is now done on the system. So let me tell you, whatever work was done on the system, let's assume that entire work is stored in the gas in the form of its internal energy. Initially, you had the gas whose internal energy was U1. Now you supplied Q amount of heat. Now its internal energy, total energy is U1 plus Q. Now I'm bringing the piston down. That means compression is happening. Work is done on the system. And whatever work is done on the system, that work is stored in the gas in the form of its internal energy. So can you tell me now what will be the total internal energy of the gas? It has to be U1 plus Q, and W amount of work was done on the gas. Right? I'm assuming this is the final state of the gas. So this whole term, it has to be the final internal energy of the gas. Right? If I take U1 on that side, so it's going to be U2 minus U1. U2 minus U1 is nothing, that's delta U. So delta U has to be equal to Q plus W. This is the mathematical formulation of your first law of thermodynamics, which you have to remember. This is your mathematical formulation of first law of thermodynamics, which you have to remember. Be careful with one thing. Whenever heat is absorbed by the system, you have to take the value of Q as positive. Whenever heat is released by the system, you have to take the value of Q as negative. Right? Let's exactly see what kind of questions are asked. Right now, only basic questions will be asked. Okay? Because we have just derived this relation. Okay? When we check the thermodynamic processes, there it becomes good. Right now, only basic questions will be there. For example, again, I'm telling you, be careful with these terminologies. Be careful with the sign conventions. When heat is absorbed, Q value positive. Heat is released, Q value negative. Right? This is the first question on the screen. Based on first law of thermodynamics, a very simple basic question. Let's try to solve this. The question is, a system expands from 5 liter to 10 liter. A system expands from, system means ideal gas. So ideal gas is showing expansion from 5 liters to 10 liters. So I would say initial volume of the gas is 5 liters. Final volume of the ideal gas, that is 10 liters. Correct? The gas is showing expansion against a constant external pressure. Against a constant external pressure of 2 atm. Right? The gas is showing expansion against the constant external pressure of 2 atm. Right? See, you already know it. For example, this is the container, this is the piston, right? This is the gas inside. Perfect. This is pressure of gas, and this is external pressure. If there is expansion, that means the piston is going out. Piston is going out. Expansion is happening. Work is done by the system. Work is done by the system against what? Against this external pressure, right? So it's mentioned that the system is expanding from 5 liters to 10 liters against a constant external pressure of 2 atm. If it absorbs 800 joules of heat, during the expansion, system is absorbing 800 joules of heat. And when heat is absorbed by the system, Q value is taken to be positive. So it's plus 800 joules. Calculate the value of delta U in joules. Calculate the internal energy change during the process. Calculate the internal energy change during the process. Delta U you have to calculate. Can you give it a try? It's simple. First of all, it's mentioned that during the expansion is happening against constant external pressure. Now you tell me, if external pressure is constant, should the process be reversible or irreversible? You tell me that. Tell me in the chats quickly. Should the process be reversible or irreversible? Quickly. Should the process be reversible and irreversible? If external pressure is constant, I have told you in the beginning, when I discussed work, it has to be irreversible because external pressure is constant, right? So, I have to calculate delta U. What is delta U all about? It's Q plus W as per first law of thermodynamics, correct? Since the process is irreversible, so I'm writing W irreversible. Yeah, simple. I need to calculate delta U in joules. That means Q has to be in joules and W at the same time has to be in joules as well. Well, Q is already given in joules, right? W irreversible. How do you calculate W irreversible? We have discussed it. It's minus P external delta V, which is V2 minus V1. So dear students, minus P external is how much? 2 atm. V2 minus V1. Final volume minus initial volume. So 10 minus 5 is 5. So pressure is in atm, volume in liters. So its units are supposed to be in atm liter. Pressure volume, atm liter, right? So it's going to be minus 10 atm liter. But my dear students, whether I need to take W in atm liters? No, I have to take W in joules. So minus 10. 1 atm liter is 101.3 joules. The value comes out to be minus 1013 joules. This is the value of W. This is the value of W, right? This minus signifies that expansion is happening. So I was supposed to calculate delta U is equal. Q value is 800 joules plus W is minus 1013 joules. So the final value will come out to be minus 213 joules. So this is the value of delta U which you are supposed to calculate. Is this clear? Is this clear, guys? All the things were mentioned, right? Dear students, whatever I'll be mentioning on the screen, please take a note of every single thing because every single thing is really very important. Okay? Perfect. Let's get going. So my dear students, let's try to understand this particular term, enthalpy function. How this particular term, enthalpy function, was introduced. Yeah? How this term was introduced and why this term was introduced and where do we use this particular term. It is again one important term in thermodynamics. Let's get to know all about this enthalpy function. So dear students, first of all, imagine that you have got a container. Imagine that you have got a container, right? And this container, for example, it contains the ideal gas. This container, it contains the ideal gas. So what does that mean? That means there will be ideal gas molecules present in this particular container. Absolutely. So this particular ideal gas, which is right now under thermodynamic investigation, so this ideal gas is my system right now. Yeah, so this ideal gas, it's my system right now. It is under thermodynamic investigation. At the same time, if I use first law of thermodynamics for this particular ideal gas, how do we write the mathematical formulation of first law of thermodynamics? You already know it. Delta U is equal to Q plus W, right? As per first law of thermodynamics, delta U has to be equal to Q plus W, correct? Now, my dear students, what is this delta U? It is the change in the internal energy of the system, which is going to be equal to U final minus U initial. So U2 minus U1 has to be equal to Q plus W. And W, as you all must be knowing, W is equal to minus P delta V. I hope this is something which everybody knows. Yeah. Now, people, if I write the same equation, at constant pressure, what does that mean? If I assume that this particular gas, let's say it's at constant pressure. First of all, I'm writing this particular equation for this particular ideal gas, which is there in the container. Now, I'm assuming that the ideal gas is kept at constant pressure. So, at constant pressure, I would say U2 minus U1, it has to be equal to, instead of Q, I'll be writing QP, and this is going to be minus P V2 minus V1. Correct? What is Q? Q is the heat absorbed or the heat released by the system at constant pressure. The heat absorbed or heat released by the gas at constant pressure. Yeah? Let's try to simplify this a bit. It's going to be U2 minus U1 is equal to QP minus PV2 plus PV1. Right? So, my dear students, these two terms I'm going to take on the left side. So, it's going to be U2 plus PV2. U2 plus PV2 minus U1 plus PV1. It has to be equal to QP. It has to be equal to QP. Yeah? It has to be equal to QP. Now, if you look at this particular equation, in this particular equation, you are getting a common term basically. Over here, you are getting U plus PV. Here also, you are getting U plus PV, right? You are getting U plus PV here as well as U plus PV here. Perfect. Now, my dear students, instead of U plus PV, just to reduce the calculations and all, instead of U plus PV, I'll be writing H. So, this U plus PV which I got over here, I'm calling this U plus PV as H. Now, you tell me one thing. This is U plus PV2. Should I be calling this as H2? Absolutely. U plus PV1. Should I be calling this as H1? And it has to be equal to QP. It has to be equal to QP. Right? Now, people, H2 minus H1. What is H? H stands for enthalpy. H stands for enthalpy, which is basically equal to U plus PV. So, what is H2? It is the final enthalpy of the system. What is H1? It is the initial enthalpy of the system. Correct? So, H2 minus H1, I'll be writing it as delta H. So, delta H came out to be equal to QP. This is something which is an amazing result, my dear students. Now, what does it mean? What does it mean? What is delta H? Delta H stands for enthalpy change. Delta H stands for enthalpy change. What is QP? QP is the amount of heat absorbed or released by the system at constant pressure. So, my dear students, can't we define enthalpy change from here? Absolutely, we can do that. We can say enthalpy change is defined as the heat absorbed or released. The heat absorbed or released by the system at constant pressure. So, my dear students, whatever heat will be absorbed or released by this ideal gas, at constant pressure, that gives me the enthalpy change of the system basically. That gives me the enthalpy change. For example, if I say this gas is absorbing 50 joules of heat at constant pressure, so I'll say enthalpy change of this gas is 50 joules. If I say this gas is releasing 100 joules of heat at constant pressure, I'll say enthalpy change of the system, that is again 100 joules. So what is enthalpy change? Enthalpy change of the system is nothing. It is just the amount of heat absorbed or released by the system kept at constant pressure. Yeah? Perfect. Now, my dear students, how do we define the term enthalpy? See, what did we do here? We defined the enthalpy change. How do you define enthalpy? Enthalpy H, it is just defined as the sum of internal energy of the system and its pressure volume work, nothing else. So what is enthalpy? What is enthalpy? So do remember this from now onwards. Enthalpy is the sum of internal energy. It is the sum of internal energy of the system and its pressure volume work. Now, if you ask me what kind of information this enthalpy gives us about the system, let me tell you that as well. My dear students, enthalpy, it gives us the idea about the heat content present in the system. It gives us the idea about the heat content present in the system. This is one more important point. From enthalpy, you get to know the amount of heat content. You get the information about the heat content which will be present in the system. Yeah? Right? Now, people, understand few more things. If I talk about enthalpy, let me tell you enthalpy, which is denoted by H. It is an extensive property. Right? So its value changes on changing the amount of substance present in the system. One more important point. This enthalpy, it is a state function. If enthalpy is a state function, therefore we should be calculating change in enthalpy, and change in enthalpy is nothing. It is H final minus H initial, right? H final minus H initial. And at the same time, people, if I talk about enthalpy, let me tell you, enthalpy change for a cyclic process, that has to be equal to 0, which we discussed in the last session. Change in the value of a state function for a cyclic process. That's always equal to what? That's always equal to 0. I hope all these things are clear till here. Right? I hope all these things are clear till here. Now, dear students, there are few important things about enthalpy. Enthalpy, it is basically the function of pressure and temperature. For which gas? For a real gas. For a real gas, enthalpy depends on two parameters. It depends on pressure as well as temperature. But when we talk about the ideal gas, for the ideal gas, enthalpy is just the function of temperature. For what? For the ideal gas. For the real gas, enthalpy depends on two parameters, pressure and temperature. For the ideal gas, enthalpy depends on one parameter, that's temperature. Same like your internal energy. Internal energy for real gas, it used to depend on volume and temperature. But internal energy of the ideal gas, it used to depend upon temperature only. I hope you remember that. Now, my dear students, something interesting is going to come up now. First of all, as I told you, for real gas, enthalpy is the function of pressure and temperature. For a real gas. Right? So what does that mean? That means if you change the temperature of the real gas, the enthalpy will change. If you change the pressure of the real gas, enthalpy will change. Now the point is, how do we calculate that change in enthalpy of the real gas? How do we calculate the change in the enthalpy of the real gas when you change the pressure of the real gas or when you change the temperature of the real gas? Right? How we are going to do it? See, enthalpy depends on two parameters. So in order to get the change in enthalpy, we have to use the partial differentiation, which I showed you in the last session. Hope you remember that. I hope you remember that. Now, people, what exactly I'm going to do? Understand. Understand properly. First of all, I'll keep the pressure of the gas constant. I'll keep the pressure of the gas constant. I'll just change the temperature of the gas. And when I change the temperature of the gas, enthalpy of the gas will automatically change. Correct? So what exactly I'm doing? I'm keeping pressure constant. I'm changing the temperature. On changing the temperature, there will be change in enthalpy. So that change in enthalpy due to change in temperature. That change in enthalpy due to change in temperature. How do you represent it? It's going to be change in enthalpy due to change in temperature. Keeping what constant? Keeping pressure constant. So from this particular term, can't we get the value of dH? dH has to be equal to dou H upon dou T at constant pressure multiplied by dt. Now what has to be my second step, people? What has to be my second step? I'll keep the temperature constant. I'll change the pressure of the gas. I'll keep the temperature of the gas constant. I'll change the pressure of the gas. And when I change the pressure of the gas, enthalpy will automatically change. So now I'll be calculating change in enthalpy due to change in pressure, which is change in enthalpy due to change in pressure, keeping temperature constant. So I would say dH from this equation is coming out to be dou H upon dou P at constant temperature multiplied by dt. Now tell me the meaning of these terms over here. This term gives me the enthalpy change in enthalpy of the gas due to change in temperature, keeping pressure constant. This term gives me change in enthalpy of the gas due to change in pressure, keeping temperature constant. So both the things are basically giving me the change in enthalpy only. So if I want to write the total change in enthalpy will be the sum of these two changes. So it has to be dou H upon dou T at constant pressure multiplied by dt plus dou H upon dou P at constant temperature multiplied by dP. This is the equation which I would want every one of you to remember from now onwards, right? Similar equation, my dear students, we got for internal energy, if you remember, similar type of equation, right? So what is the significance of this equation? This equation is going to let me know the enthalpy change on changing temperature, keeping pressure constant. Then on changing pressure, keeping temperature constant, right? Let me know once in the chats with the thumbs ups if this equation is clear. If you got to know how this equation came, quickly in the chats, everyone. Quickly. Now, people, understand few more important things. So, as I told you, this particular equation, it gives me the enthalpy change due to change in temperature, keeping pressure constant. Due to change in pressure, keeping temperature constant, right? Now, if I talk about the ideal gas, for an ideal gas, let me tell you, for an ideal gas, as I told you, for an ideal gas, enthalpy only depends on temperature. Yeah, for an ideal gas, enthalpy only depends on temperature. If enthalpy only depends on temperature, so if you change the pressure of the ideal gas, will there be change in enthalpy? So can I say for the ideal gas, this particular term has to be 0? This particular term has to be 0 for the ideal gas. So for the ideal gas, dou H upon dou P, change in enthalpy due to change in pressure, keeping temperature constant. This particular term has to be 0. If this term is 0 for the ideal gas, then I must say dH, change in enthalpy for the ideal gas, and has to be equal to dou H upon dou T at constant pressure multiplied by dt. And this particular equation, let me tell you, this particular equation is valid for 1 mole of ideal gas. It is valid for 1 mole of ideal gas. Okay? Right? Now, my dear students, try to understand one thing. This dou H upon dou T at constant pressure. dou H upon dou T at constant pressure. This is what you call as Cp, molar heat capacity at constant volume, which we discussed already, right? This is called as Cp. So it is Cp multiplied by dt. And this equation is also valid for 1 mole of ideal gas. For 2 moles of ideal gas, dH has to be equal to 2 times Cp dt. For 3 moles of ideal gas, dH has to be equal to 3 times Cp dt. For n moles of ideal gas, dH has to be equal to n Cp dt, my dear students. dH has to be equal to n Cp dt. And this particular equation, it is valid for n moles of ideal gas. So first of all, when we talk about the ideal gas, enthalpy of ideal gas only depends on temperature. When you change the temperature, enthalpy of ideal gas will change. Okay? And this equation is particularly valid for n moles of ideal gas. So, if you have got n moles of ideal gas in the container, if you change the temperature of n moles of ideal gas by dt units, there will be change in the enthalpy of the ideal gas as well, which is represented by dH. Yeah? So, dH represents small change in the enthalpy of the ideal gas on changing its temperature by dt units. Imagine that you have got n moles of ideal gas and you are changing its temperature from T1 to T2. Imagine that you have got n moles of ideal gas and you are changing its temperature from T1 to T2. There will be change in its enthalpy. So what will be the total change in enthalpy? What will be the total change in enthalpy when you are changing the temperature of n moles of ideal gas from T1 to T2? In order to get the total enthalpy change, I'll be integrating with respect to temperature, which is changing from T1 to T2. Correct? Now, dear students, integral of dH, that has to be delta H. If Cp is constant, it will come out, n will come out. So n comes out, Cp comes out. Integral of dt is T, upper limit, lower limit. So it has to be T2 minus T1. This is the equation which I would want every one of you to remember from now on. Delta H for the ideal gas is equal to NCP T2 minus T1. So you can write it finally like this. Delta H for the ideal gas is equal to NCP delta T. But do remember, this particular equation is only valid for n moles of ideal gas. So let me tell you the significance of this particular equation. Whenever you'll be having some moles of ideal gas in the container and you'll change its temperature, there will be change in its enthalpy. And that change in enthalpy due to change in temperature is calculated with the help of this particular result. Yeah? Okay, that is calculated with the help of this particular result. I hope this is also clear to you. Right? So dear students, try to understand one more thing. Few minutes back, I defined delta H. I told you delta H is equal to QP. Right? And delta H for the ideal gas, now I got to know it's equal to NCP delta T. So sometimes they might confuse you in the questions. They'll ask you either directly calculate the delta H for the ideal gas, or they'll ask you to calculate the heat absorbed or heat released by the ideal gas at constant pressure. They might confuse you. They'll directly ask, calculate the enthalpy change of the ideal gas, or they'll ask, calculate the heat absorbed or heat released by the ideal gas at constant pressure. Right? And heat absorbed or heat released at constant pressure, that's delta H. And delta H you already know, that's NCP delta T, nothing else. Yeah? Now, my dear students, one more thing. Tell me one thing. If an ideal gas undergoes isothermal process, what does that mean? That means temperature of the gas is remaining constant. If temperature is remaining constant, change in temperature has to be 0. Delta H, which is equal to NCP delta T. If delta T is 0, that means delta H for the ideal gas will be also 0. If an ideal gas undergoes isothermal process, what does that mean? That means the temperature of the gas, the temperature of ideal gas is not changing. And if the temperature of ideal gas is not changing, if it is remaining constant, if the temperature of the ideal gas is not changing, so its enthalpy won't change. So change in enthalpy has to be 0 for the ideal gas. Very simple and basic, right? One more thing which I would want to share with you. One more thing which I would want to share with you, people. Try to understand that as well. Based on the sign of delta H. Based on the sign of delta H, we get two things over here. If you have studied somewhere, any process whose delta H is negative, or any process can have delta H positive. Process can have either delta H negative or delta H positive, right? Now, people, any process whose delta H is negative, that's what we call as exothermic process. And any process whose delta H is positive, that's what you call as endothermic process, right? Now, you tell me one simple thing over here. Delta H negative, what does that mean? That means NCpT2 minus T1. That will come out to be negative. When is that possible? That's only possible when T2 will be less than T1. When T2 will be less than T1. So what can we conclude from here? What is T2? T2 is the final temperature of the system. T1 is the initial temperature of the system. So in case of exothermic process, temperature increase or decreases, T2 is coming out to be less than T1, right? Perfect. And at the same time, if delta H is positive for the ideal gas, that means NCpT2 minus T1 will come out to be positive, which clearly tells you T2 has to be greater than T1. I hope this is clear, right? There is one more important thing, my dear students, which I would want all of you to remember and understand. A few minutes back, I gave you one important result. I told you dH is equal to NCpdt. dH is equal to NCpdt. And this equation is valid for n moles of ideal gas, right? This equation is valid for n mole of ideal gas. Now you tell me one thing. If you will be, for example, having 1 mole of ideal gas. Let's say we have got 1 mole of ideal gas. Means n value is 1. If n value is 1, I would say dH is equal to Cp dt. Or I will say Cp is equal to dH upon dt. Now, can you let me know the significance of this equation? Cp is equal to dH upon dt. What does that mean? What does that mean? dH upon dt, it represents the slope of the tangent. It represents the slope of the tangent. The slope of the tangent on enthalpy versus temperature curve. The slope of the tangent on enthalpy versus temperature curve. Why is it important? Why is it important? Because we can frame a question on this particular statement. And what kind of question can be framed? Let's say I'm giving you one simple question like this. Let me see if you can solve this or not. For example, one hypothetical question I'm giving you. One hypothetical question I'm giving you. This is enthalpy versus temperature. Let's say the graph is like this. Let's assume the graph is like this. And this graph is, for example, valid for 1 mole of ideal gas. 1 mole of ideal gas. Now, my dear students, I'm marking 2 points here. This is point A and this is point B. And I would want you guys to let me know where the Cp value will be more. Will Cp at A be more than that of Cp at B? Will they be equal? Will they be less? What is going to be the relation? Can you let me know in the chats? Can you let me know in the chats? Quickly. Quickly, people. Quickly in the chats. Give it a try. Give it a try. Give it a try. Quickly. You can. Where is the Cp value more? Have a look, people. What I'll be doing? I'll be drawing a tangent at point A. Then I'll be drawing a tangent at point B. Now try to understand. It is making theta A here. It is making theta B here. Where is the theta value more? I would say theta A is greater than theta B. If theta A is more, does that mean tan of theta A will be more than tan of theta B? Absolutely. If theta A is more than that of theta B, that means tan of theta A should be also greater than that of tan of theta B. Yeah? What is tan of theta A? It is slope of tangent at point A that has to be greater than slope of tangent at point B. And wherever slope of the tangent is more, CP value is absolutely going to be more. So I would say CP at A will be greater than CP at B. Right? I would say CP at A will be more than that of CP at B. I hope this is absolutely clear to everyone. Right? So this was all about your enthalpy. Okay, this was all about your enthalpy. And people are asking what kind of questions are asked out of this. Guys, simple and basic things. Have a look. Have a look. I'm writing a question over. Let's say question is 10 decimeter cube of helium gas at STP is heated to 100 degrees centigrade. Is heated to 100 degrees centigrade. Calculate the enthalpy change of the system of the gas in joules, assuming ideal gas conditions. Assuming ideal gas condition. For example, this is the question. Will you be able to solve this? Will you be able to solve this? Kishore, whatever I have taught in solid state, you have to study that much only. I keep on telling you all the time, you should know what to study and what not to study, right? Don't use your brain in between, like what to study. Keep that on us, okay? So whatever I've taught in solid state, you're not going to do anything extra from that. Yeah? Rest, it's your choice. So 10 decimeter cube of helium at STP is heated to 100 degrees centigrade. Calculate delta H in joules, assuming ideal gas condition. Now, my dear students, understand what is given to us. First of all, 10 decimeter cube of helium means 10 liter of helium. Because 1 decimeter cube is 1 liter, right? So 10 decimeter cube is 10 liter. So we have got 10 liters of gas. 10 liter of gas is present at STP. So temperature of the gas is 0 degrees centigrade. Pressure of the gas is 1 atm. Right? Because the gas is present at STP. So you have got 10 liters of helium, which is present at STP. Now, my dear students, you are heating this gas. You are heating this gas. Initially, the temperature of the gas was 0 degree. Now, the final temperature of the gas is 100 degree. Correct? You are heating this gas. You are changing its temperature, basically. And you know, if this was the ideal gas, if you change its temperature, will its enthalpy change? Of course, right? Because enthalpy of an ideal gas, it depends only on temperature. Right? If you change the temperature, enthalpy of the ideal gas will change. Now we have to calculate that change in enthalpy of the gas. So my dear students, try to understand what I'm going to say. So we have got 10 liters of helium at STP. 10 liters of helium means how many moles? 10 liters of helium means 10 divided by 22.4. So these many moles of helium we have. Now people, what do we need to calculate delta H? Enthalpy change. So delta H for the ideal gas, as I told you, it's NCP T2 minus T1. Correct? So delta H will be equal to N value. N is nothing, it's 10 divided by 22.4. CP value. Since helium, it's a monoatomic gas. Do you remember CP value for the monoatomic gas? You should be knowing it. CP for the monoatomic gas, it's pi by 2R. T2 minus T1. T2 minus T1. So change in temperature is 100. Perfect. Since we have to calculate delta H in joules, so which value of R you guys are going to use? Since we have to calculate delta H in joules, so we'll be using the value of 8.314 joules per Kelvin per mole multiplied by 100. So it's a matter of calculation now. Just solve it and get the value of delta H in joules. That's all. Yeah, that's all. So this kind of the question is asked. Or they might change the language of the question. They'll ask you, calculate the heat absorbed or released by the gas at constant pressure. If they ask you calculate the heat absorbed or released by the gas at constant pressure, that means they're asking you the value of QP. And QP for the ideal gas. What is that? That's nothing. That's delta H. And delta H for the ideal gas. That's nothing. That's NCP delta T. So they just can change the language of the question, nothing else. I hope you're getting it properly. Right? Is it clear? Say yes or no in the chat quickly. And I can see not everyone has liked the session yet. This is not done. Perfect? Perfect, people? So two things which you have to remember from now onwards. Either in the question they'll ask you the heat absorbed or released, which in short I'm writing as heat exchanged between system and surroundings at constant pressure. They can ask you this term, or they can ask you the heat exchanged between the system and the surroundings at constant volume. At constant volume. At constant volume. So basically, this term is nothing, that's QP. This term is nothing, it's QV. And QP is nothing, that's delta H. QV is nothing, that's delta U. And for the ideal gas, delta H is equal to NCP delta T. For the ideal gas, delta U is equal to NCB delta T. So they can just change the language of the question, but the concepts will remain same. Yeah? Perfect, people. Thank you. Attractive status. Love you from Jannat-e-Kashmir. Wow. So these two things they'll ask, okay? Now, since you got to know what this delta H is all about, what this delta U is all about, how they are calculated for the ideal gas, now, my dear students, it is the time to get the relation between delta H and delta U. It is the time to get the relation between delta H and delta U. And that concept is really very important because a lot of questions will be framed. A lot of questions can be asked from the topic relation between delta H and delta U. So try to understand it carefully. So I'm marking the heading over here as relation between. I'm marking the heading as a relation between delta H and delta U. Correct? A relation between delta H and delta U. This is one very, very, very important topic. Yeah. So people try to understand. How did we define enthalpy? Enthalpy H, that was equal to U plus PV. Correct? That was equal to U plus PV basically. Enthalpy of the system, it is the sum of internal energy of the system and the pressure volume work. So if I multiply this equation throughout by D, so it becomes DH, this becomes DU, this becomes D of PV. I multiplied this equation throughout by D. Let me just integrate this equation. Let me just integrate this equation. Integral of DH will be delta H. Integral of DU will be delta U. Integral of D will be delta. Delta of what? Delta of PV. So first of all, this is the general equation. This is the general equation. This is the general equation for the relation between delta H and delta U. This is the main equation. This is the actual equation. Now from this particular equation, we are going to derive many more equations. And what are those equations? Let's have a look. My dear students, if you write this equation at constant pressure, if you write this equation when the gas is kept at constant pressure, so how exactly you're going to write it? Delta H is equal to delta U plus. Since if pressure is constant for the gas, so P will come out, it becomes P delta V. This is the equation which we shall be using in the questions when the system is kept at constant pressure. Now, my dear students, when the system is kept at constant volume, when the system is kept at constant volume, I would say delta H will be equal to delta U plus constant volume. V constant, take it out. So it's going to be V delta P. And this particular equation we are going to use at constant volume. When the system is present at constant volume, this is how you write the equation, you write the relation between delta H and delta U. Now at the same time, at the same time. If pressure as well as volume will be changing, if pressure as well as volume of the system will be changing, how you are going to write this equation? You are going to write this equation like this. Delta H is equal to delta U plus, it's simply going to be P2 V2 minus P1 V1. This is the equation which we shall be using in the questions, wherein it will be mentioned that the pressure as well as temperature, pressure as well as volume of the gas is changing. Okay. Now there is one last result which you need to remember. I'm writing for a gaseous phase reaction. For a gaseous phase reaction carried out at constant temperature. For a gaseous phase reaction carried out at constant temperature. For example, you have got the reaction like this: N1A gas plus N2B gas. Let's say it gives N3C gas plus N4D gas. Perfect. How do you write the relation between delta H and delta U for a gaseous phase reaction which is carried out at constant temperature? So my dear students, do remember delta H is equal to delta U plus delta NGRT. Now you must be thinking what this delta NG is all about. You must be thinking what this delta NG is all about, right? You must be thinking what this delta NG is all about. So dear students, delta NG, it is equal to number of moles of gaseous products minus number of moles of gaseous reactants. So delta NG will be equal to number of moles of gaseous products, number of moles of gaseous products. So you have to take only those products which are in gaseous state. This is in gaseous state, this is in gaseous state. N3 moles of this, N4 moles of this. So number of moles of gaseous products is going to be N3 plus N4 minus number of moles of gaseous reactants. This is a gaseous reactant, this is a gaseous reactant. Its moles are N1, its moles are N2. So it's going to be minus N1 plus N2. So this is how you get delta Ng for the reactant. Number of moles of gaseous products minus number of moles of gaseous reactant. Right? Yes? Perfect. So my dear students, try to understand one important thing now. The general relation between enthalpy change and internal energy change of the system, that's always equal. Delta H is equal to delta U plus delta of PV. Now, depending on the parameters, whether pressure is kept constant in the equation, whether volume is kept constant, whether pressure and volume of the system both are changing, whether you have got a gaseous phase reaction carried out at constant temperature, accordingly, you have to use a result and try to solve the equation, right? Let's try to solve the equations so that all these concepts, whichever we have discussed till now, so that they will properly become clear to you. Just a second, guys. Just a second. This is the first question which we shall be doing. Look at the question carefully. Look at the question carefully. 1 mole of ideal gas undergoes a change in state. 1 mole of the ideal gas undergoes a change in state. So when the ideal gas was present at initial state, its pressure was 2 atm, volume was 3 liters. Now you are changing the state of the gas. Now you are changing the state of the gas. And when the gas reaches the final state, where its pressure is 2 atm, volume 7 liters, internal energy change of the gas is 30 atm liter, the change in enthalpy. Try to understand what the question says. Okay? Have a look, people. As far as the question is concerned, we have got 1 mole of ideal gas, right? So initially, the pressure of the gas was kept 2 atm and the volume of the gas was kept 3 liters. I'm assuming this was the initial state of the gas. Now, as per the question, you're changing the state of the gas. You're changing the state of the gas. And how I understood the state of the gas has been changed? How I understood that the state of the gas is changed? I told you in the last session. When you change the value of state parameters, right? The state of the system automatically changes. If you minimum change one state parameter, the state of the system will automatically change. Now, which parameter have you changed? You have changed the volume parameter. You have changed volume parameter. Are you changing the pressure? You're not changing the pressure. So pressure of the gas is remaining constant, right? Pressure of the gas is remaining constant. So I got to know pressure of the system is kept constant. And if the pressure of the system is kept constant, which relation I'll be using? Delta H is equal to delta U plus P delta V. P delta V, right? Now, as per the question, delta H we have to calculate. We have to calculate it in ATM liter. So, delta U has to be in ATM liter, which is given 30 ATM liter. And my dear students, this whole term has to be in ATM liter as well. That means pressure has to be in ATM and volume has to be taken in liters. So, pressure is to ATM, V2 minus V1. Final volume minus initial volume. 7 minus 3 is 4, right? So, first of all, pressure is to ATM multiplied by change in volume is 4. So, it's going to be an ATM liter too. Perfect. So, from here, you're exactly getting the value of delta H, which is 38 ATM liter. Is this something which we were supposed to calculate? Is this something which we were supposed to calculate? Quickly. We were supposed to calculate the value of delta H, which we did. This is the value of delta H for the gas. Right? I hope you got to know how I exactly dealt with it. Quickly, people, quickly in the chats. Is everything clear till here? Is everything clear till here? Quickly. So, as per the question, you have to see which parameter is kept constant. Accordingly, you have to use the relation. Let's try to solve one more question. Let's try to solve one more question. This is one more question. Look at the question carefully and try to solve this. It is one nice question basically. Which of the following is correct for the following exothermic reaction carried out at constant pressure? Right? Carried out at constant pressure. So as far as the question is concerned, we have to check whether delta U is equal to delta H, whether delta U is greater than delta H, whether W is less than 0, whether Q is greater than 0. We have to check all these parameters. And how you are going to do that? Understand? Understand, guys. First thing, it's mentioned in the question that the reaction is exothermic in nature. If the reaction is exothermic, heat is released by the system. Heat is released by the system. And whenever heat is released by the system, Q value is taken as negative. Whenever heat is released by the system, Q value has to be negative. Over here, it's mentioning that Q is positive, so this cannot be done. Right? This is wrong, it's not right. This is wrong, it's not right. Okay? Now, one more thing. See, first of all the reactions, they take place at constant temperature. All the reactions, generally, they take place at constant temperature. And apart from that, this particular reaction, it's taking place at constant pressure as well. Apart from that, this particular reaction, it's taking place at constant pressure as well. Yeah? Now, guys, if you remember the ideal gas equation, PV is equal to nRT. PV is equal to nRT. Pressure is constant, temperature constant, R constant. So volume is directly proportional to moles. If moles are increased, volume will be increasing. If moles will be decreasing, volume will be decreasing, right? Now try to look at the question on reactant side, how many moles we have? How many gaseous moles we have? 3 plus 1, 4. How many gaseous moles we have on product side? 1 plus 1, 2. When the process happens, when this reaction takes place, are the total moles increasing or decreasing? Total moles are decreasing. Total gaseous moles are decreasing. And if the moles will be decreasing, volume of the system will be decreasing as well. If the moles are decreasing, that means volume of the system will be decreasing. Decrease in the volume of the system is something which you call as compression. And you know, whenever there is compression, W value, as per sign convention, is it taken as positive or negative? W value, as per sign convention, in chemistry is taken as positive. But over here, they have mentioned that W is negative, so this cannot be the answer. Okay. Now the last thing. Get the relation between delta H and delta U. My dear students, you have got a gaseous phase reaction carried out at constant temperature. The relation has to be delta H is equal to delta U plus delta NGRT here, right? Now, first of all, get the value of delta Ng. Delta Ng is equal to number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactants, which is 3 plus 1, 4. The value is minus 2. Put the value here in the equation. So you can say delta H is equal to delta U minus 2 times RT. Or you can say delta U is equal to delta H plus 2 times RT. Now look at this particular equation. Look at this particular equation. He's mentioning that delta U is equal to delta H plus. So delta U is equal to delta H plus. What does that mean? That means delta U is equal to delta H plus 2 times RT. So delta U is becoming equal to delta H only when you add a term on this side. When you add this term on this side. What does that mean? That means delta U is greater than delta H. Delta U is greater than delta H by this much of amount. So this particular thing has to be correct. So this automatically becomes incorrect. Right? Perfect. So it's option B, which is the correct answer of the question. I hope you can easily solve them from now on. Basically, this question had 3 concepts in it, right? It was a good question. I hope a lot of things got revised through this particular question. Let's try to solve one more. Let's try to solve one more. Look at this question, guys. Look at this particular question carefully. Calculate delta U when 2 moles of liquid water vaporizes at 100 degrees centigrade. The heat of vaporization of water is given. See what is given and what are we supposed to calculate. As far as the question is concerned, H2O liquid is being converted into H2O gas. H2O liquid is being converted into H2O gas. This is the process of vaporization basically. Liquid is being converted into gas, right? Temperature is kept as 100 degrees centigrade, means 373 Kelvin. Delta H for the process, enthalpy of vaporization for the process is given to me as 40.66 kilojoules. What do we have to calculate? We have to calculate the value of delta U. Try to understand what exactly I'm going to do. Try to understand what exactly I'm going to do. I'm giving you the reaction. Tell me the relation between delta H and delta U. Delta H is equal to delta U plus delta NGRT. Okay. Now, my dear students, I need to calculate delta U. I need to calculate delta U in kilojoules. If delta U is to be calculated in kilojoules, that means delta H has to be in kilojoules minus. And this delta NGRT, this particular whole term, it has to be in kilojoules as well. Correct? Yes. If this is in kilojoules, this has to be in kilojoules, even this has to be in kilojoules. Now you tell me one thing. What about the delta Ng for the reaction? What about the delta Ng for the reaction? Number of moles of gaseous products, that's 1. Minus number of moles of gaseous reactant. There is no gaseous reactant, so delta Ng is 1. So we have calculated delta Ng. So I can write delta U is equal to delta H. Delta H is 40.66 kilojoules minus delta Ng is 1. R value is 8.314 joules per Kelvin per mole. Joules per Kelvin per mole. Temperature is 373 Kelvin. Since this is joules per Kelvin per mole, right? But I need this whole term in kilojoules. But I've used the value of R in joules. So I'll be dividing it with 1000. Then only this term will be also in kilojoules. When you solve this particular equation, you'll be getting the value exactly as 37.5 kilojoules. This is the value of delta U. But if you ask me whether this is the correct answer or not, this is not the correct answer. This is the value of delta U for the vaporization of 1 mole of liquid water. This is the value of delta U for the vaporization of 1 mole of liquid water. But as per the question, are we vaporizing only 1 mole of liquid water? No, we are vaporizing 2 moles of liquid water. Delta U for the vaporization of 1 mole of liquid water is this much. So delta U for the vaporization of 2 moles of liquid water has to be equal to 37.5 multiplied by 2. The value has to be 75.1 kilojoules. Majority of the students, they solve the question till here. They mark the answer as well. But that's wrong, right? You have to be careful with the things. You have to see how many moles of liquid what you are vaporizing exactly. Accordingly, you have to give your answer. Yeah? So what is the correct answer then? It has to be option B. Correct, people? Is it clear to everyone? Quickly. One more question. One more question on the screen. Look at the question. Try to understand the language of the question. See, guys, why thermodynamics is tough? Why it's considered to be tough as per students' perspective? Because you are unable to understand the language of the question. If you are able to understand the language, you are done. You're sorted. So try to understand the language of the question. See, guys, I'm giving the reaction. I'm doing the combustion of benzoic acid. I'm doing the combustion of benzoic acid. Temperature is given as 300 Kelvin and pressure is given as 1 atm. So this reaction is being carried out at constant pressure and temperature. This reaction is being carried out at constant pressure and temperature. It is mentioned that heat released is 300 kilojoules. Heat released is 300 kilojoules. So he's mentioning that heat is being released. Heat is being released. During this process, heat is being released. When heat is released, Q value is taken to be negative, right? So Q has to be equal to minus 300 kilojoules. If you try to understand one more thing, in the question, since the reaction is carried out at constant pressure, so this is basically heat released at constant pressure, and heat released at constant pressure is represented by QP. And QP, we already know, that is basically delta H. So indirectly, they are giving you the value of delta H. Indirectly, they are giving you the value of delta H. And what are we supposed to calculate? Calculate the heat released at constant volume. Heat released at constant volume is QV. QV is equal to delta U. So basically, delta H is given, delta U is to be calculated. Done? Done and dusted? What you'll be doing? You'll be calculating delta Ng for this reaction, which will be equal to number of moles of gaseous products, which is 7, minus number of moles of gaseous reactant, which is 15 by 2. The value is minus 1 by 2. So this is delta Ng for the reaction. This is delta Ng for the reaction. If this is delta Ng, the equation is done. Use the relation delta H is equal to delta U plus delta Ng RT, right? Or you can say delta U is equal to delta H minus delta Ng RT. If delta U is to be calculated in kilojoules, that means this term has to be in kilojoules. Even this whole term has to be in kilojoules as well, right? Now put the values, kill it. Yeah. So I can say your delta U will be equal to delta H, that's given, minus 300 kilojoules, minus time. Delta Ng is minus 1 by 2. R value 8.314 joules per Kelvin per mole. And temperature is 300 Kelvin. I've used the value of R as joules per Kelvin per mole. I have to calculate delta N in kilojoules. So this has to be in kilojoules. Even this term has to be in kilojoules. But right now this term is in joules. So I'll be dividing it with 1000. Then only this term will also come in kilojoules. Now it is just the matter of calculation. Calculate it and kill it. Get the value of delta U. Isn't it simple, my dear students? Isn't it simple? Quickly in the chats. Will you be able to solve different types of questions based on this concept? Quickly, say in the chats, will you be able to solve different types of questions based on these equations which I gave you? Yes? Wonderful. Perfect. Let me give you one last question on the same topic, then we can move on to the next topic, right? The question is like this. The question is 2 times carbon monoxide gas plus O2 gas. It gives 2 times carbon dioxide. This is the reaction. Delta H is given to me as minus 560 kilojoules. In the question, it's mentioned that in 10-liter rigid vessel, at 500 Kelvin, the initial pressure is 70 atm, and after the reaction, it becomes 40 atm. Calculate delta U in kilojoules. Will you be able to solve this question? Say yes or no in the chats. Will you be able to solve this question? Say yes or no in the chats. Quickly. Quickly, my dear students. There is one thing which you have to decode basically. It's mentioned that in a 10-liter rigid vessel, that means volume of the vessel does not change. Volume of the vessel does not change means volume of the system does not change. So this process is happening at constant volume, right? Which kind of relation do we use at constant volume? Do you remember? At constant volume, we use this relation. Delta H is equal delta U plus V delta P. This is the relation which we use. Yeah, this is the relation which we use. Now what is given? Delta H is given and delta U has to be calculated. So delta U has to be equal delta H minus V delta P. Delta U has to be calculated in kilojoules. So delta H has to be taken in kilojoules. And this whole term also has to be taken in kilojoules. Volume is 10 liters multiplied by change in pressure. Final pressure minus initial pressure. Final pressure is 40 atm. Initial is 70. So final minus initial. The value comes out to be minus 30 liters. This is atm, this is liter. So the unit of this particular term is atm liter. The unit of this particular term right now is atm liter. But if this has to be calculated in kilojoules, this should be also kilojoules, even this should be kilojoules, right? You know, 1 atm liter is equal to 101.3 joules. Now this term is in joules, but I do not want in joules, I want in kilojoules. So divide simultaneously with 1000, then only this will be in kilojoules. Now again, it's a matter of calculation. Do the calculation and kill it. Yeah? I hope all the basic, I'm telling you all the things wherein a student can commit a mistake. All the things I'm telling you. At which a student can do a mistake. And I want you guys to avoid these things. One question on the same concept, which I'm giving you as a homework. I would want you guys to let me know its answer in the comment section. This is also one nice question. This is your homework question from the same concept. Just let me know once in the chats. Will you be able to solve it, or you want me to solve it right now? If you say yes, solve it right now, I'll do it here only. Quickly. Let me know. Till then, I can have some water. Quickly, everyone. Let me know quickly in the chats, people. Do you want me to solve it, yes or no? I think you guys have slept. Good. Good going. Let me know in the chats quickly. Why are the chats so slow? Jyota, 1 atm liter is equal to 101.3. That is 1 bar liter. 1 bar liter is 100 joules. 1 atm liter is 101.3 joules. Let me solve it. You won't be able to solve this. You might get some confusion or something because we have not solved this type of equation yet. Okay, so let's try to do it. As far as the equation is concerned, we are given with a reaction, and the reaction is N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. This is the reaction. Yeah. Delta H for this reaction is given minus 600 kilojoules. This is delta H. Calculate the change in internal energy when 6 moles each of reactants are allowed to react at 300 Kelvin. Temperature is given. We have to calculate basically the value of what? We have to calculate the value of delta. Delta what? Delta U. Delta U has to be calculated. Delta U has to be calculated. Try to understand how exactly I'm going to approach to this question. See, first of all, let me calculate delta Ng for this particular reaction. What is delta Ng for this reaction? Number of moles of gaseous product, that's 2, minus number of moles of gaseous reactant, that's 4. So 2 minus 4 comes out to be minus 2. So delta Ng is minus 2, correct? Now use the relation. Relation is delta H is equal delta U plus delta NGRT, correct? Now we will understand. Delta U has to be calculated, which will be equal to delta H minus delta NGRT. So if I want to calculate delta U in kilojoules, that means delta H has to be in kilojoules, which is minus 600 minus times. Delta Ng value, that's minus 2, minus plus, this is 2. R value, 8.314 joules per Kelvin per mole. Temperature is given to me as 300 Kelvin. Since we have taken the value of R as 8.314 joules per Kelvin per mole, so I'll be dividing it with 1000 so that this term also comes in kilojoules. Can you just solve this part and let me know what is the value coming out to be? Can you just solve it right now? Can you solve it right now and let me know what is the value of delta U coming from here, from this equation? Quickly, I'll be waiting for your answers. Let me know in the chats. The equation is not done yet. I'll tell you what is the twist here. I want you guys to solve this equation. Let me know the value of delta U. Well, Priyanka is saying it's minus 595. Yeah? Okay. So it is minus 595. Minus 595 kilojoules. This is the value of what? This is the value of delta U. But my dear students, try to understand. I did not use this particular term yet. I got the value of delta U directly for this particular reaction. Through this particular reaction, how many moles of NH3 are formed? 2 moles of NH3 are formed. So this is the value of delta U for the formation of 2 moles of NH3. Yeah? This is the value of delta U for the formation of 2 moles of NH3. So I should know, first of all, if I start with 6 moles each of reactants, I should know, first of all, how many moles of product will be formed. Then accordingly, you'll get the value of delta U. Understand now? So we are starting with 6 moles each of reactants, right? 6 moles each of reactants. Which concept I'll be using? I'm given with the amounts of all the reactants. I'm given with the moles of all the reactants. I'll be using the concept of limiting reagent. How do I identify the limiting reagent? Divide the given moles by the respective stoichiometric coefficients. The one whose value comes out to be lesser, that has to be limiting reagent. So 6 by 1 is 6, 6 by 3 is 2. So H2 is your limiting reagent. If H2 is limiting reagent, it would have got completely consumed, right? And when H2 would have consumed, the reaction would have stopped, right? Now you tell me, entire product formation is decided by the limiting reagent. Now as you can see, 3 moles of limiting reagent gives 2 moles of NH3. 3 moles of limiting reagent gives 2 moles of NH3. So 1 mole of limiting reagent gives 2 by 3 moles of NH3. So 6 moles of limiting reagent gives 2 by 3 multiplied by 6. The value is 4 moles of NH3. So you got to know at the end of the reaction, 4 moles of NH3 has got formed. This is the value of delta U for the formation of 2 moles of NH3. This is the value of delta U for the formation of 2 moles of NH3. So I'll say delta U for the formation of 2 moles of NH3 is equal to how much? Minus 595 kilojoules. So delta U for the formation of 1 mole of NH3, use the unitary method. So divide by 2. So delta U for the formation of 4 moles of NH3 will be equal to, this is going to be the final answer. This is going to be the final answer. I hope you got to know how to deal with this sort of equation. Say yes or no in the chats. Darshan, that's completely okay. You can study here also. Platform does not matter. It's okay. What is important? Whether I'm teaching right now or not, I'm teaching, right? So quickly, people, can you solve this sort of question from now on? You should be able to do this. Now, let me tell you honestly, all the types of questions which can be asked from delta H delta U relation, I've showed you them. All those questions are discussed. All those types are discussed. There's not a single question which is left. Okay? Perfecto. Let's then move on. Let's then move on to reversible and irreversible process. Something wherein majority of the students will have doubt. Okay, but we'll be exactly starting from the basics. I'll try to cover all your doubts here. Okay, just give me a second and we shall be starting. Just give me a second and we shall be starting. This is something important. A reversible and irreversible process. I'm going to write few things first of all. On this side, I'm writing reversible. On the other side, I'm writing irreversible. Reversible, irreversible. Okay? Try to understand few things. First of all, okay, let me write few things first of all, then I'll make you understand. Reversible processes, these are slow processes. Number one. Number two, driving force is greater than the opposing force by a small amount. Number three, P gas is almost equal to P external. Number four, system and surroundings, they are always at equilibrium. Always at equilibrium. Number five, these are the imaginary processes. Number six, calculation of work in reversible process is equal to minus integral V1 to V2. This is P gas multiplied by dV. I'll make you understand all these points one by one. First, you write down things. Irreversible processes. Fast, driving force far, far, far greater than the opposing force. External pressure is kept constant. System and surroundings are at equilibrium, only at initial and final state. System and surroundings are at equilibrium, only at initial and final state. These are the real processes. Work done in case of irreversible process is equal to minus P external delta V. Minus P external V2 minus V. Try to understand what all these things exactly are all about. Okay? I hope you took a note of all these. I hope you took a note of all these things. Now let's try to analyze these reversible, irreversible processes. Let's get to know one by one what these things are all about. Okay? So have a look what these things are all about. My dear students, first of all, I'll be giving you one analogy so that you can relate it a bit. For example, I need to lift this marker up. I'm lifting this marker up. When I'm lifting this marker up, can you let me know how many forces are acting on this marker? When I'm lifting this marker up, how many forces are acting on this marker? One force which I am giving, due to which it's going in upward direction. One force which gravity is pulling it towards itself. So two forces are acting on this marker basically when I'm taking this up. One force I'm giving, due to which it's going up. Another force, gravity is pulling it. That force which I am giving, due to which it's going upwards, that is the driving force. That is the driving force. And the force which gravity is pulling it towards itself, that is the opposing force. So one is driving force, due to which it's going upwards. One is opposing force, due to which it should go downwards. It should go downwards. So two forces act on this marker when it goes upwards. Now there are two ways by means of which I can lift the marker. Either I can lift the marker fastly or I can lift the same marker slowly. When I lift the marker fastly, and I say at that time, driving force is far greater than the opposing force. Absolutely, driving force at that point of time is far greater than the opposing force. Was the process slow or fast? The process was fast. Yeah? Correct? So the process was irreversible in nature. Now, I'm lifting this marker slowly. If I'm lifting this marker slowly, what does that mean? That means driving force is greater than the opposing force, but only by a small amount. That's why I'm lifting this marker slowly. Driving force is greater than opposing force, but only by a small amount. Okay? That's why I'm lifting this marker slowly. Driving force is greater than opposing force, but only by a small amount. That's why the process is slow. I hope you got the analogy of reversible, irreversible. Whenever from now onwards you hear the word reversible, get one thing in mind, that it has to be slow process. Whenever you hear the word irreversible, remember, it has to be fast process. It has to be fast process. Okay? Now, let's try to relate it with thermodynamics. Let's try to relate and let's try to get these other things clear as well. Okay? So, dear students, try to understand what exactly I'm going to say. Try to understand properly. I'm going to take two containers. These are two containers. This is the piston. This is the piston as well. These are the gas molecules here. Even these are the gas molecules here. Perfect. Now, my dear students, I'm keeping sand particles over here at the top. These are the sand particles present at the top of the piston. Right? And over here, you do not have sand particles. You've got an object. You've got a block. Now, dear students, first of all, I'm assuming that this piston is not moving. It's neither going downwards nor upwards. What does that mean? Okay, before talking about that, tell me one thing. If I talk about this piston, can you let me know how many pressures are acting on this piston? How many pressures are acting on this piston? First of all, these internal gas molecules are colliding with the piston. So in this direction, you have got P gas, which is what you call as internal pressure, right? From top to bottom, there will be one more pressure. That's what you call as external pressure. Can I say external pressure? External pressure is due to atmosphere and the sand. This external pressure, it is due to atmospheric and sand. Correct? Let's say pressure due to sand is 4 Newton per meter square and pressure due to atmosphere, for example, is 1 Newton per meter square. Just giving the values so that you can understand it. P external is due to sand and atmospheric pressure. Due to sand, it's for example 4 Newton per meter square. Due to atmosphere, it's 1 Newton per meter square. So that means this P external, this external pressure will be in total 5 Newton per meter square. How many forces are acting on this piston? Two forces, in this direction and in this direction. I'm assuming piston is not moving. If the piston is not moving, what does that mean? That means right now, P gas is equal to P external. Right now, P gas is equal to P external. That's why piston is not moving. That's why piston is not moving. Right? Perfect. So P external was 5 Newton per meter square. That means P gas will be also equal to 5 Newton per meter square. That's why the piston is not moving right now. Okay. Now, imagine it like this. Imagine that you took one of the sand particle away. You took one of the sand particle away. What happened to the external pressure? External pressure due to sand, it is decreasing. Now, initially it was 4. Now, after removing one sand particle, for example, it is 3.99. It is 3.99. So, does that mean external pressure is decreasing a bit? External pressure is decreasing. I removed a sand particle. That means external pressure is decreasing a bit. My dear students, if external pressure decreases a bit, internal pressure is still the same, 5. External pressure now is 4.99. Can I say a pressure difference got created between internal and external? Right? Can I say the piston will start moving upwards a bit? Since external pressure decreased a bit. So, if external pressure is decreasing a bit, internal pressure is same. The piston will go slightly upwards. The piston will go upwards till the pressure of the gas also reaches 4.99. Yeah? And when the piston will go slowly upwards, it will again stop. Because when the piston stops, at that point of time, again internal and external pressure would have become equalized. Now, the internal and external pressure will be both 4.99. That's why the piston has stopped. Remove one more sand particle. External pressure again is decreasing. Internal pressure is 4.99. External pressure, for example, is 4.98. The piston will again go a little upwards. Right? Perfect. And when the piston will go upwards, it will again stop. When the piston will stop, again external internal pressure will become equal. That means internal pressure now reaches 4.98. Again take one more sand particle. Piston will again slowly go upwards. Again internal and external pressure become equal. So is this process a slow process or fast process? What do you think? Is this slow or fast? It's a very slow process, first of all. It's a very slow process. This expansion of the gas, it's slow, number one. Number two, what is happening to the pressure of the gas? Is the pressure of the gas changing? Yes, the pressure of the gas is changing. Initially it was 5, then 4.99, 4.98, right? So, P gas, it is fixed or variable? It's variable. It's changing with time, right? At the same time, piston is going upwards, stopping. That means system surrounding again in equilibrium. Again little upwards, stops. Again system surrounding equilibrium. Piston goes upwards, stops. Again system surrounding equilibrium. So can I say system and surroundings are at equilibrium at every point of time? System surroundings are at equilibrium at every point of time, right? Perfect. Can I say at every point of time, P gas is almost equal to P external? No doubt, they are not exactly equal, but they're almost equal. And how do you calculate work done? How do you calculate work done? What was the general expression? General expression was minus integral V1 to V2 P external dV. So if P external is almost equal to P gas, so the formula has to be integral V1 to V2. It has to be P gas multiplied by dV. So from a reversible process, what you have to understand? First, slow process. Pressure of the gas keeps on changing. Right? Number 3, P gas is variable. System surrounding at every point of time, they'll be at equilibrium. P gas is almost equal to P external. This is the formula by means of which you calculate work done in reversible process. And this is something which is imaginary. Who takes sand particle one by one? Nobody, right? I'm not going to do that. So it's imaginary basically. It's not a real process. Now what happens here in this case, in the second case? The first case was reversible. Now look at the second case. My dear students, in the second case, it's a quite interesting thing here. Okay. First of all, on the piston, there will be two pressures. One will be internal pressure, pressure of gas. One will be external pressure. External pressure will be due to atmospheric pressure and due to block. Let's say the pressure due to block is 4 Newton per meter square and atmospheric pressure, for example, is 1 Newton per meter square. So the total external pressure is 5 Newton per meter square. I'm assuming the piston is not moving right now. That means external pressure will be equal to P gas. That's why piston is not moving right now. External pressure, internal pressure, they're equal. That's why the piston is not moving. Okay. Now what I'm going to do? Suddenly just remove the block. Suddenly just remove the block. What is going to happen? If you're suddenly removing the block, that means this pressure you're cancelling. This pressure won't be there. You're suddenly removing it. This pressure won't be there. Now external pressure will be only the atmospheric pressure, which is 1 Newton per meter square. Internal pressure is 5 Newton per meter square. Can I say a greater pressure difference got created? Due to which the piston will fastly, abruptly move upwards. Yeah? Piston will abruptly move upwards. So can I say the piston is moving upwards? The piston is moving upwards against what? Against only atmospheric pressure, which is constant. Which is constant. So first of all, the process fast. Second, expansion of the system is happening against what? Against constant external pressure. Against constant. You remove the block. Now the piston is going upwards. Against what? Against only the atmospheric pressure, which is constant. Perfect. The process fast. Right? Now, since it's a fast process, do you see at every point of time system and surrounding at equilibrium? No. Piston will go upwards suddenly and will stop somewhere. So initially and finally, system and surroundings will be at equilibrium. System surrounding, they'll be only at equilibrium at initial and final state. Okay. Now, how do we calculate work? What is the general expression? Minus integral P external dV. Since P external is constant, so P external will come out. Integral of dV is V, upper limit, lower limit. So this is the formula by means of which you calculate work done in irreversible process. This is the formula by means of which you can calculate work done in reversible process. Say, tell me in the chats whether all these things are absolutely clear to you or not. Quickly, people. Quickly, everyone. Everyone. Isn't this amazing? Isn't this amazing, guys? I find this amazing. Now understand a few more important things. Let's try to relate it a bit more with thermodynamics. For example, this is the container. Let's say this is the container. And this is the piston here at point A, for example. This is the ideal gas in the container. Okay. On this piston, there'll be two pressures. One is P gas, one will be P external. Correct? For example, the piston has to go from point A to point B. When the piston moves from point A to point B, will there be increase in the volume? Yes, there will be increase in the volume of the gas. Right? There will be increase in the volume. Piston is going from A to B. That means increase in the volume of the gas is happening. The molecules are going far. Right? Increase in the volume is what we call as expansion. So basically, what I'm doing right now, I'm doing expansion. Expansion of gases. Now, this expansion of gas can happen in two ways. It can happen in two ways. Either the piston will be slowly going up outwards, or the piston will be abruptly going outwards. If the piston goes outwards slowly, you will be calling this expansion as a reversible expansion. When the piston goes outwards abruptly, you'll be calling it as irreversible expansion. And you already know, in reversible expansion, P gas, or leave all these things. I hope this point is clear to you. If this point is clear, I'll have to tell you one more important thing. This was the case of expansion. Same can be the case of compression as well. If the piston has to come inwards, there are two ways by which piston can come inwards, either abruptly or slowly. Abruptly means irreversible compression. Slowly means reversible compression. There are two statements which I'm going to mention, which I'm going to write, then I'll explain you those two statements. Take a note of them. Take a note of them. I'm writing a statement. For the same amount of expansion, magnitude of work done in reversible process is greater than that of magnitude of work done in irreversible process. Point number one. Point number two. For the same amount of compression, magnitude of work done in irreversible process is greater than that of magnitude of work done in reversible process. So two statements are mentioned. Let's try to decode these two statements. Let's try to understand these two statements. Because if you understand these two statements, all the other things will be absolutely fine. Before making you understand these two particular statements, there is one more thing which I would say every one of you would be remembering. What is that? Area under PV curve. If you'll be having a PV curve, do you know area under PV curve, it gives us the magnitude of work. For example, you've got a PV curve like this. This is pressure. This is volume, right? The curve is, for example, like this. Right? The curve is, for example, like this. If I calculate area under this curve, that means I'm talking about this particular area. Whatever will be the area under this curve, that is going to give you the magnitude of work which is done during this process. During the process AB, for example. This is something which I assume that you know. Area under PV curve, that gives you the magnitude of work. Okay? Now people, try to analyze and understand what exactly I'm going to convey. What exactly I'm going to tell you. Okay, guys. Understand properly what I'm going to say. This is the container which I'm taking. This is the piston right here at point A. And when the piston is at point A, I'm assuming pressure of the gas is 10 atm, volume of the gas is 2 liters. For example, when the piston is at point A. Now the piston has to go from point A to point B. And when the piston reaches at point B, let's assume that volume of the gas reaches 10 liters and pressure of the gas reaches 2 atm. Correct? Piston was at point A first. Now it's going to point B. Right? So volume of the system is increasing, volume of the gas is increasing, pressure of the gas is decreasing automatically. There are two ways by means of which the piston can go from A to B. There are two ways. I'm going to plot it on the curve. There are two ways by which a piston can go from A to B. Either the piston will go outwards slowly or it can go outwards fastly. Those are the two ways. Let's assume this pointer represents 2 liter volume. This pointer represents 10 liter volume. This pointer represents 2 atm pressure. This pointer represents 10 atm pressure. Correct? When the piston was at point A, volume of the gas was 2 liter, pressure was 10 atm. Volume of the gas was 2 liter, pressure was 10 atm. That means the point will be somewhere here. The point is somewhere here, point A. Finally, the piston is reaching at point B, where pressure is 2 atm, volume 10 liters. Volume 10 liters, pressure 2 atm. Volume 10 liters, pressure 2 atm. That means the point will be somewhere here. Point B. Right? So basically, the piston is going from A to B. Imagine that the piston is slowly going from A to B. From A to B, is the pressure decreasing? Yes. Is the volume of the gas increasing? Yes. So can I say pressure of the gas will be, if the piston is slowly going outwards, Can I say pressure of the gas will be slowly decreasing and volume of the gas will be slowly increasing? Pressure of the gas will be decreasing. Volume of the gas will be increasing, but slowly. So the nature of the graph will be like this. This process is very slow. This is how it's happening. This is how it's happening. This is how it's happening. So this particular graph, what does it remember? What does it represent? It represents the reversible path. I've got two paths for this expansion. One is reversible, one is irreversible. First, I'm making this piston to move slowly. So pressure of the gas is slowly decreasing and volume of the gas is slowly increasing. Now there is one more way of doing the same. The piston, if it abruptly goes outwards, what will happen? I'll say pressure of the gas will suddenly drop and volume of the gas will suddenly increase. Pressure of the gas will suddenly drop from 10 atm to 2 atm and volume of the gas will suddenly increase from 2 liters to 10 liters. Pressure is suddenly dropping and volume of the gas is suddenly increasing. It looks like a two-step process, but it's not two-step process. It happens in one step only. It happens in one step only, right? It happens in one step only. It looks like two here, but it's a single stage expansion. Now try to understand. This particular path, which path this is this reversible or irreversible path? This is irreversible path. I was doing the expansion of how many liters? Initial volume was 2 liters, final volume is 10 liters. So I'm doing the expansion of 8 liters. And this expansion of 8 liters was done in two ways. First, it was done reversibly. Second, it was done irreversibly. Reversibly, irreversibly. This is the reversible path. This is the irreversible path. What is the area under the curve through reversible path? Through reversible path, what is the area under the curve? This is the area under the curve through reversible path. Through irreversible path, what is the area under the curve? Area under the curve is this much through irreversible path. So, in which path area under the curve is more? In which path area under the curve is more? So, can I say area under reversible curve is greater than that of area under irreversible curve in case of expansion, right? And if area under curve is more, area under the curve, it gives me the magnitude of work. So can I say magnitude of work done during reversible expansion will be greater than that of magnitude of work done in case of irreversible expansion? What does that mean? Try to understand. For example, you have to do X liter of expansion. X liter, let's keep it as 5 liter. Let's say you have to do 5 liter expansion of a gas. Let's say you have to do 5 liter expansion. This expansion can be done in two ways, either slowly or fastly. Slowly means reversibly, fastly means irreversibly. In both the ways, the volume of the gas is increasing. Either it will increase slowly or it will increase fastly. In both the ways, the volume of the gas is increasing. Increasing the volume of the gas is expansion. Whenever there is expansion, work is done by the system. Now, where the work done by the system will be more? When the process is done reversibly, work done by the system will be more as that of irreversible. I hope this is clear to everyone. That's what you wrote over here. For the same amount of expansion, magnitude of work done by the system is greater than that of magnitude of work done by the system when done through irreversible path. Say yes or no? Similarly, if you talk about compression, whenever there is compression, work is done on the system. So either compression will happen fastly or slowly, reversibly or irreversibly. In both the ways, work will be done on the gas. But magnitude of work done on the gas during irreversible compression will be greater than that of magnitude of work done on the gas during reversible compression. During reversible compression. So, let me summarize it like this. For example, I have to do the expansion of 5 liters. This expansion can be done reversibly as well as irreversibly. In both the ways, work is done by the system. In both the ways, work is done by the system. Whether done reversibly or irreversibly, in both the ways, work is done by the system. But where is the magnitude of work done by the system more? Magnitude of work done by the system is more in reversible Then comes your irreversible. Now, similarly, for example, I'm doing 5 liters of compression. This 5 liters of compression can be done in 2 ways. Reversibly, irreversibly. In both the ways, since it's the case of compression, in both the ways, work is done on the system. In both the ways, work is done on the system. Because in both the ways, compression is happening, work is done on the system. But do remember, magnitude of work done during irreversible compression will be greater than that of magnitude of work done on the gas during reversible compression. These are the two statements which I would want you guys to remember. Say yes or no in the chats if you got them. Till then, I can have some water. Is it clear? Is it clear, guys? Quickly. Quickly, everyone. I want everyone to say it, yeah. I want everyone to say it. Yes or no? Yes or no? If this is clear, then let's try to move on. Let's try to move on. One basic thing. What is that? That is isochoric process. Isochoric process. So this is the first process which we have to discuss. And there is nothing in it. There is nothing in it. You know it. When do we say that the system undergoes isochoric process? When do we say that? When do we say that the system is undergoing isochoric process? Whenever I'll be changing the state of the system by changing the value of state parameter. But I'm making sure that I am not changing the volume of the system. I'm changing other state parameters, for example. I can categorically say, if my system is ideal gas, then I can say, whenever a system undergoes a change in state, whenever a system undergoes a change in state, but during the change in state, during this change in state, volume of the system does not change. Volume remains constant. Volume remains constant. We say that system is undergoing isochoric process. We say the system is undergoing isochoric process. So finally, in short, in isochoric process, volume is kept constant. If volume is constant, delta V, change in volume, that has to be 0. That has to be 0. If change in volume is 0, work minus P delta V. If delta V is 0, work is 0. So in case of when the ideal gas undergoes isochoric process, there will be no exchange of system and surroundings. Sorry, there'll be no exchange of energy. There'll be no exchange of energy in the form of work. Right? There'll be no exchange of energy in the form of work. Guys, just a second. Guys, just give me a second, okay? Just a second, guys. Okay, so what I was telling is, whenever the system undergoes isochoric process, there'll be no exchange of energy between system and surroundings in the form of work, right? What is work? It is the mode of transfer of energy between system and surroundings. If work is zero, that means energy between system and surroundings, it is not being exchanged in the form of work. W is zero. That's all you have to remember. If you want to plot a graph between pressure and volume, how does isochoric process look like? Isochoric process, volume has to be kept constant. Volume has to be kept constant. This graph over here represents isochoric process. I'm not changing the volume. Volume is kept constant. Okay, perfect. If I use first law of thermodynamics, as per first law of thermodynamics, delta U is equal to Q plus W. If I use first law of thermodynamics for an ideal gas, delta U is equal to Q plus W. And if I write the same equation at constant volume, imagine that the gas is kept at constant volume. If the gas is kept at constant volume, so delta U will be equal to Q, because W value will become 0 when the gas is kept at constant volume. Now, should I be calling this as Q or QV? QV. And for the ideal gas, delta U is nothing, that's NCV delta T. So this is something which we already discussed, right? Heat absorbed or released by the system at constant volume, that's basically delta U. And delta U, as per the formula for the ideal gas, has to be NCV delta T. That's all. Correct? Correct? Already we have discussed this. So there is nothing basically in isochoric process, right? Actual process are isothermal and adiabatic. But before that, let's try to do these simple things which do not have many things in. Second process is what you call as isobaric process. When do we say that the ideal gas undergoes isobaric process? Whenever an ideal gas undergoes a change in the state, but during the change in the state, if the pressure of the gas remains constant, we say the gas undergoes isobaric process. If pressure is constant, delta P has to be 0. Delta P has to be 0. Use the first law. Delta U is equal to Q plus W. If I write the same equation at constant pressure, then delta U has to be equal to QP plus W, and W is minus P delta V. That means QP will be equal to delta U plus P delta V. Do you remember? Delta U plus P delta V, that was basically delta H at constant pressure. Have we discussed this relation already? And delta H for the ideal gas is nothing, it is NCP delta T. So all the relations which we have discussed, all the relations are coming again basically, using first law. Yeah? Right? All these relations are coming again. This was first law. First law at constant pressure. The gas is at constant pressure. Again, all the results which we have discussed, all the results are coming correct only. Perfect. Now, people, if I need to show it graphically, how do I show it graphically? This is pressure, this is volume. Isobaric process. Pressure has to be constant. This is the graph, which represents isobar. So this particular line, it represents isobaric process. It represents isobaric process. Yeah, it represents isobaric process. Perfect. One more thing, guys. In your isochoric process, this was the graph. Do you see any area under this graph? Area under the graph is 0. Area under the curve is 0. It's a straight line. Area under this particular straight line is 0. So work is 0. Because you know, area under the curve, that gives you the magnitude of work. Yeah. Now, how do you calculate work in case of isobaric process? Simple, minus P delta V. Minus P delta V. This is how you calculate work done in case of isobaric process. There is one particular type of question which is asked. What is that? I'm writing it over here. For a gaseous phase reaction. For a gaseous phase reaction carried out in an open container. For a gaseous phase reaction carried out in an open container. How do we calculate work? What does this mean? First of all, for example, you have got a container which is open on one side. Now, for example, there is a reaction taking place here in this container. And the reaction is, for example, like this. N1A gas plus N2B gas. For example, it gives N3C gas plus N4D gas. Let's say this particular reaction is being carried out in an open vessel. During the process, energy will be exchanged between system and surroundings in the form of work. How do you calculate that work? Right here. That work is calculated by this result, minus delta NGRT. So whenever in a question you say that some reaction is carried out in an open vessel, use this particular result to calculate the work. In case of isobaric processes where pressure is constant, this is the formula by means of which work is calculated. This is the formula. If they ask you calculate the heat absorbed or heat released in an isobaric process, heat absorbed or heat released by the system at constant pressure, right? That's delta H. For the ideal gas, that's NCP delta T. Let's try to use all these equations in the questions. Then only we can go ahead and talk about a few more interesting stuff. Okay, 3 equations I'm going to do over here, which will make you understand all these things. Umar, what you're talking about? Which formula you're talking about? Okay, we'll talk about whatever you're saying afterwards. Let's try to solve this question first. As far as the question is concerned, 1 mole of aluminium is dropped in an aqueous solution in an open container containing HCl at 300 calories. If 95 calories of heat is released during the process, calculate W, delta U, delta H. So first of all, is it based on open vessel concept? Yes, it's based on open vessel concept. And in case of your open vessel concept, do remember, pressure you'll be always keeping constant. As far as your open vessel concept is concerned, you'll be considering the process to be isobaric, right? Perfect. There are 2 ways by means of which you can calculate work, minus P delta V or minus delta NGRT. Since there is a reaction happening, so you'll be using minus delta NGRT, right? Right, people? Now try to understand what I'm going to say. First of all, what do I have to do? I have to calculate W, I have to calculate delta U, I have to calculate delta H. Perfect. The reaction is taking place in an open vessel. And whenever any process takes place in an open vessel, we have to use the open vessel concept. And as far as the open vessel concept is concerned, we have to keep the pressure of the system constant. Pressure is kept constant, right? Pressure is kept constant. So you have to take the process as isobaric. You have to consider the process as isobaric. Now this is an isobaric process. The pressure is constant. It is mentioned that 95 calories of heat is released. Heat released means minus 95. Is this heat released at constant pressure? Absolutely. Heat released at constant pressure. That's something which you call as delta H. So first parameter is done. First part of the equation is done. Delta H is calculated. Now, calculate work. How do you calculate work here? Minus delta NG RT. Calculate delta NG first of all. Delta NG is number of moles of gaseous products, which is 3/2. Minus number of moles of gaseous reactant. There is no gaseous reactant. Take R value in calories, because you have to calculate everything in calories. Take R value in calories, 2 calories per Kelvin per mole. Temperature is mentioned in the equation as 300. The value comes out to be 2 cancelled. The value comes out to be minus 900 calories. Minus 900 calories. So my dear students, what did we calculate? We calculated Q, we calculated W. Q is done. W is done. I mean delta H is done. W is done. Now calculate delta U. Delta U is equal to Q plus W as per first law. Since the process is isobaric, so pressure is constant. At constant pressure, you do not write Q, you write QP, right? So what is the value of QP? Value of QP is minus 95 and the value of W is minus 900. The value will come out to be minus 995 calories. This is the value of the delta U as well. Agreed? Is this clear? Yes, it should be. It should be, guys. Let's try to solve one more question. Let's try to solve this question. Calculate the work done in the complete decomposition of 5 moles of PCl5 in calories at 300 Kelvin and mention in an open container. In an open container, do mention it. In an open vessel. In an open vessel. So first of all, it's again the open vessel concept. And as far as the open vessel concept is concerned, I'm going to keep pressure of the system constant. I'm going to keep pressure of the system constant, right? So first of all, what do I need to do? I need to calculate W. W is equal to minus delta Ng RT. Calculate the value of delta Ng. Number of moles of gaseous product, which is 1 plus 1, 2. 2 minus 1 is 1. So delta Ng is 1. Take R value as 2 calories, right? 2 calories per Kelvin per mole. Temperature is 300. The value will come out to be minus 600. It is minus 600 calories. W value is coming out to be minus 600 calories. So this is this supposed to be the answer? This cannot be the answer. Why is that? Because this is the value of W during the decomposition of 1 mole of PCl5. This is the value of W during the decomposition of 1 mole of PCl5. But as per the question, we have to do the decomposition of 5 moles of PCl5. So W for the decomposition of 1 mole of PCl5 is minus 600 calories. So W for the decomposition of 5 moles of PCl5 has to be equal to minus 600 multiplied by 5. So the answer is minus 3000 calories. This has to be the value of W during the decomposition of 5 moles of PCl. Yeah? Right? Right, people? One more question. Calculate work done in calories. Assume that the reaction is taking place in an open vessel again. Assume that the reaction is taking place in an open vessel. If the reaction is taking place in an open vessel, pressure is kept constant. How do we calculate work? In the open vessel concept, minus delta Ng RT. Calculate delta Ng. Number of moles of gaseous product, 4 plus 1, 5. Right? There is no gaseous reactant, so delta Ng is 5. R value is 2. Temperature is 300 Kelvin. So the value comes out to be minus 3000 calories. Is this the answer? Is this the answer? Can you let me know in the chats? Is this the answer? Minus 3000 calories? This cannot be the answer. This cannot be the answer. This is the value of W when 3 moles of N2H4 undergoes dissociation. When 3 moles of N2H4 undergoes dissociation, the value of W is minus 3000 calories. When 1 mole of N2H4 undergoes dissociation, the value of W has to be minus 3000 by 3 calories. As per the question, when 5 moles of N2H4 undergoes dissociation, the value of W will be, this will be 1000 multiplied by 5. The final answer will be minus 5000 calories. This is the value of W during the decomposition of 5 moles of N2H4. Yes. Is this clear, my dear students? Let's start with something called as isothermal process. This is important, from which question frequently comes, right? So what is an isothermal process and what all different types of results do we have in the process? How to calculate work, etc. All these things shall be discussed in this particular process. Perfect. So my dear students, first of all, how do we define the isothermal process? When do we say that the ideal gas is undergoing isothermal process? When do we say that? When do we say that the ideal gas undergoes isothermal process? My dear students, during the change in the state, of the system here is your ideal gas, right? During the change in the state of the system, if the temperature if the temperature of the system remains unchanged. Remains unchanged. What does that mean? My dear students, is a very simple thing. Imagine that you have got a gas in the container. You have got an ideal gas in the container, for example, right? Now, this ideal gas is undergoing expansion. The volume of the gas is increasing. If during the expansion or compression of the ideal gas, the temperature of the gas does not change. If during the expansion or compression of the ideal gas, temperature of the gas does not change, then at that point of time, we say that the ideal gas is undergoing isothermal process. So basically, in case of isothermal processes, I must say in short that the temperature of the system remains constant. And if the temperature of the system remains constant, delta T, change in temperature, has to be 0. Point number 1. Point number 2. How do we calculate delta U for an ideal gas? Delta U for an ideal gas is equal to NCV delta T. And my dear students, we know when the ideal gas undergoes isothermal process, delta T is 0. And if delta T is 0, that makes delta U 0 as well. That makes delta U 0 as well, right? Similarly, how do we calculate delta H for an ideal gas? It is NCP delta T. Since the ideal gas is undergoing isothermal process, so during the expansion or compression, the temperature of the gas is not changing. So delta T has to be 0. Therefore, delta H for the gas will be 0 as well. Yeah. And my dear students, if this is clear to everyone, as per first law of thermodynamics, delta U is equal to Q plus W, right? Now, delta U for the ideal gas, which undergoes isothermal process, is 0. Therefore, Q is equal to minus W. This particular result is only valid for what? It is valid for ideal gases undergoing isothermal process. I want you guys to remember all these things. Okay? So, whenever during the expansion or compression, the temperature of the gas does not change, the temperature of the system does not change, we at that point of time say that the system is undergoing isothermal process. And if the system is undergoing isothermal process, temperature remains constant, delta T is 0, delta U for the gas is 0, delta H for the ideal gas is 0, and Q will be equal to minus W for the ideal gas which undergoes isothermal process. Yeah? Because in our syllabus, we only have to discuss the thermodynamics of ideal gases. That's why whenever I talk about system, that means the system is our ideal gas, which is under investigation. Let's try to understand a few more things. Since in case of isothermal processes, Q is equal to minus W. Q is equal to minus W. Now, my dear students, let's try to understand a few things. Few important things. First of all, this particular result, it is valid for an ideal gas, which is undergoing isothermal process. Perfect. First of all, if the value of W is negative, for example, the value of W is negative. W value negative means it is a case of expansion. My dear students, if W value is negative, so negative makes it positive, therefore Q value comes out to be positive. What does this particular statement mean? Q value is positive means heat is absorbed by the system. Heat is absorbed by the system, and the system is your ideal gas. Heat is absorbed by the system. What it means exactly, you'll get the idea in some time. Similarly, the value of W can be positive as well. And when the value of W is positive, that is the case of compression. And if by chance the value of W is positive, negative makes it negative, so Q value will be negative. And when the value of Q comes out to be negative, we always say heat is released by the system. Heat is released by the system. So my dear students, from these two particular things, I can generalize two important statements. Statement number one. Statement number one says, during the isothermal expansion, of an ideal gas, heat is absorbed. Heat is absorbed by the gas. Heat is absorbed by the gas. Point number two, during isothermal compression. During isothermal compression of an ideal gas, heat is released by the gas. Heat is released by the gas. Now, these two statements we can understand, right? We can understand. I mean, we can interpret, we can have its physical significance as well. Let's try to understand these two statements carefully, what they exactly mean. For example, this is the container which we have. Try to understand this carefully. Let's say the piston is at point A. This is the ideal gas which is present in the container, right? Now, my dear students, on this piston, I must say two pressures will be acting. This will be P gas, and from this side, it's going to be P external. For example, the piston has to come from point A to point B. The piston has to go from point A to point B. And when the piston goes from point A to point B, it is going to be the case of expansion. Right? It is going to be the case of expansion. So I must say the ideal gas is undergoing expansion. And during the expansion, I'm assuming that temperature of the gas is not changing. So I will say the ideal gas is undergoing isothermal expansion. The ideal gas is undergoing isothermal expansion. Now understand, people. Understand what I'm going to say. Since when the piston will be going from A to B, volume of the gas is increasing. Increasing the volume is what we call as expansion. Whenever there is expansion, work is done by the system. So during the expansion, work is done by the system, work is done by the gas. Work is done by the gas against what? Against this external pressure. Work is done by the gas against what? Against external pressure. My dear students, since system is doing work, the gas is doing work during the expansion. If the gas is doing work, what will happen? Try to understand what I'm going to say. My dear students, since during the expansion, the gas is doing the work. Work is done by the gas against this external pressure. Now, I must say the gas will be doing work against external pressure on the cost of internal energy. Right? Since the gas has to do work. So, in order to perform work, the gas will be consuming its internal energy. Right? What should happen due to that? So, during the expansion, the gas is using its internal energy and doing work. So, during the expansion, is the internal energy of the gas increasing or decreasing? It has to decrease. Yeah, it has to decrease. Wow. If the internal energy of the gas is decreasing, that means temperature of the gas has to decrease, right? Because internal energy is directly proportional to temperature. Temperature of the gas during the expansion should decrease. But do we have to let the temperature of the gas to change? Do we have to let the temperature of the gas to decrease? No. So for that purpose, what should we do? We should continuously supply heat. So that temperature remains the same and internal energy remains the same. It does not change. So can I say during isothermal expansion of an ideal gas, it is absorbed by the gas to keep the temperature constant, to maintain the temperature, to maintain the internal energy of the gas. Right? I hope this is clear to everyone. I hope this is clear to everyone. Yeah? So that's what I mentioned over here. During isothermal expansion of an ideal gas, heat is absorbed by the gas just to keep the temperature of the gas constant. Because if we do not supply heat to the gas, if heat is not absorbed by the gas during the expansion, what will happen? Gas will do work. And in order to do work, gas will use its internal energy. And if the internal energy is used by the gas, so with the time, during the expansion, internal energy of the gas will decrease, due to which temperature of the gas will decrease. And if during the expansion temperature of the gas is decreasing, then it cannot be the isothermal process. Because in isothermal processes, temperature has to be constant. Hope this particular statement is clear. Similarly, the next statement. During compression. During compression, what happens? During compression, work is done on the system. Okay? I'm talking about isothermal compression. During compression, work is done on the system. And whatever work is done on the system, that work should be stored in the gas in the form of its internal energy. During the compression, work is done on the gas. So during compression, if work is done on the gas, that work should be stored in the gas in the form of its internal energy. Due to which internal energy of the gas should increase during compression. And if internal energy of the gas should increase, that means temperature of the gas should increase. But do we have to let the temperature of the gas to increase? No. So for that purpose, the gas should continuously release heat, then only the temperature of the gas will remain maintained, then only the internal energy of the gas will remain maintained. Right? That's what I mentioned here also. During the isothermal compression of an ideal gas, heat is released by the gas just to maintain the temperature, just to keep the internal energy of the gas constant. Yeah? Is this clear? Say yes or no in the chats quickly. I hope this is clear. So do remember, whenever an ideal gas undergoes isothermal expansion, heat is absorbed by the gas so that to remain its temperature constant, to keep its temperature constant. Whenever the ideal gas undergoes isothermal compression, heat is released by the gas so as to keep its temperature constant. Otherwise, the temperature of the gas will increase if heat is not released. Right? I hope this point is clear to you. Now, my dear students, there are few things. There are few things which you need to know. So first of all, on one side, I'm writing a reversible isothermal process. A reversible isothermal process. On another side, I'm writing irreversible isothermal process. Irreversible isothermal process. The point is, how do we calculate work in case of reversible and irreversible isothermal processes? Reversible means slow expansion compression. Irreversible, abrupt expansion compression. Right? That's something which we have discussed. What is a reversible process? What is an irreversible process? Perfect. Imagine that this container, the piston was going from A to B. This was the case of expansion. This expansion can happen either slowly or fastly. Right? If it is happening slowly, that means it is the example of reversible isothermal expansion. If it is happening fastly, it's going to be the example of irreversible isothermal expansion. Right? Perfect. Right, guys? Perfect. Now the point is, how do we calculate work done in reversible isothermal processes? So, my dear students, imagine that you have taken a container. Imagine that you have taken a container in which the piston is at point A. When the piston is at point A, let's assume that the volume of the gas is V1. The piston has to go, for example, from A to B. And when the piston reaches at B, volume of the container is V2. Volume of the gas is V2. And during the expansion, let the temperature of the gas not change. So it is isothermal expansion. It's isothermal expansion. And I'm assuming this expansion to be very, very, very slow. So this is a reversible isothermal expansion. So how do we calculate work done in the reversible isothermal processes? That is the point. If you remember, how do we calculate work done in reversible process? I've already told you, minus integral V1 to V2 It's going to be P gas multiplied by dV, right? So work done in reversible isothermal process is equal to minus integral V1 to V2. P gas, pressure of the gas, will be equal to nRT divided by V, right? Multiplied by what? Multiplied by dV. So my dear students, what you will have to do, you will take minus nRT common, out of the integral. Integral of dV by V is the ln of V, right? Use the limits from V1 to V2. So my final expression becomes W reversible is equal to minus nRT. It's going to be ln of V2 divided by V1. This is one of the expressions which you guys will be remembering to calculate the work done in case of reversible isothermal process. First expression. Second expression is going to be like this. W reversible is equal to minus. Convert this ln into log. So it's going to be 2.303 nRT and it's going to be log of V2 divided by V1. This is the second expression which you guys are going to remember to calculate work done. One in terms of ln, another one in terms of log. Yeah. Well, there is one more expression which you can do. Instead of V2 by V1, you can write P1 by P2. Why? Because the gas is undergoing isothermal process. During the expansion compression, temperature does not change. So the gas has to follow the Boyle's law. And as per Boyle's law, P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. Therefore, V2 divided by V1 will be equal to P1 by P2. So instead of V2 by V1, you can write P1 by P2. Yeah. So one more expression I'm writing here. Work done in reversible isothermal process is equal to, it's going to be minus nRT ln of P1 by P2. This will be one more expression. This will be one more expression. Or you can write it in terms of log as well. W reversible is equal to minus 2.303 nRT. It's going to be log of P1 by P2. This is one more expression. So now depending on what all parameters are given to us, accordingly we are going to use the results. That's all. So these are four expressions by means of which you can calculate the work done in case of a reversible isothermal process. Now my dear students, how do we calculate work done in irreversible isothermal process? It is simple. Since in irreversible processes, external pressure is constant, right? So it's minus P external delta V, already discussed. Yeah. So this is one of the expressions to calculate work done in case of irreversible isothermal. Or you can just do one thing. You can write minus P external as such. Instead of V2, you can write nRT divided by P2. And instead of V1, you can write nRT divided by P1 by using the ideal gas equation. Nothing else, right? Take nRT out. When you take nRT out, it's going to be minus P external nRT. And this is going to be 1 divided by P2. And this is going to be 1 divided by P1. So this is one more expression which you'll be remembering to calculate the work done in case of irreversible isothermal processes. Okay, right? And already we know in case of irreversible isothermal processes, Q is equal to minus W. If you get W in isothermal processes, that means Q automatically you will calculate by just changing this sign. Let's do some questions so that you can understand it. Let's do some questions so that you can understand it properly. See guys, one simple and basic question. Try to analyze this, try to understand. Calculate Q, W, delta U and delta H when 2 moles of ideal gas, are expanded reversibly and isothermally, from 10 atm to 5 atm, keeping temperature 27 degrees centigrade, that means 300 Kelvin. So basically you have taken an ideal gas. You are doing the expansion of this ideal gas. And it's mentioned in the question that the expansion is reversible and isothermal. So it is the reversible isothermal process, right? The ideal gas is undergoing a reversible isothermal process. And to be more precise, the ideal gas is undergoing a reversible isothermal expansion. Perfect. Now, how do we calculate work? Isn't it simple? Before calculating work, the ideal gas is undergoing isothermal process, and we know when the ideal gas undergoes isothermal process, delta U as well as delta H, both the terms will be 0. Perfect. Delta U as well as delta H, both the things will be 0. Number 1. Number 2, calculate the work now. Work done during the process will be equal to minus nRT is going to be ln of P1 divided by P2. So minus as such, n value is 2, right? We have to calculate all the things in calories. So R value has to be 2 calories per Kelvin per mole. Temperature is 300 Kelvin. Ln of P1 by P2, 10 by 5, that is 2. It is mentioned that ln 2 is 0.7. So solve it, get the value exactly as minus 840 calories. This is the value of W which you got. This is the value of W which you got. So you got 3 terms, delta U you got, delta H you got, W you got. Now, since the ideal gas is undergoing isothermal process, therefore, Q has to be equal to minus W as per first law. So W is minus 840, minus make it plus, so it's plus 840 calories. Yes, students, you can understand one important thing here. W sign is coming out to be negative. That means this is the case of expansion. Ideal gas is undergoing expansion. Which expansion it is? Isothermal expansion. Q value is coming out to be positive. That means heat is absorbed by the system. I've told you already that. Whenever the ideal gas undergoes isothermal expansion, heat is absorbed by the gas. Then only the temperature of the gas remains maintained. Right? Perfect. So this was first type of question. Second type of question. Look at this carefully. 2 liters of N2 gas. So we have got 2 liters of N2 gas at 0 degree centigrade. And 5 atm pressure. Are exploded isothermally, right? Against a constant external pressure of 1 atm. So basically, you have got a container which contains 2 liters of N2 gas. Now this gas is undergoing expansion. Expansion is happening against a constant external pressure, right? Now you tell me, when the external pressure is constant, is the process supposed to be reversible or irreversible? It has to be irreversible process, because expansion is happening against constant external pressure. So the process has to be irreversible, because external pressure is kept constant only in irreversible processes. I hope you remember that. Now tell me one thing. Initial pressure of the gas was 5 atm. Now the gas is undergoing expansion. The gas is undergoing expansion till the final pressure becomes 1 atm. Till the final pressure of the gas reaches 1 atm. Perfect. Till the final pressure reaches 1 atm. And the gas is undergoing expansion against 1 atm external pressure, right? Let's assume the final volume of the gas is V2. What do we have to calculate? Calculate how much heat will be absorbed or released. So we have got basically 2 liters of ideal gas which is undergoing irreversible isothermal expansion, right? So we have to calculate how much heat will be absorbed during this isothermal expansion. So dear students, we know already. In case of isothermal processes, Q is equal to minus W. So in order to calculate Q, I would need W. And is this W reversible or W irreversible? This has to be W irreversible. How do we calculate W irreversible? Work done in irreversible isothermal processes. It is minus P external V2 minus V1, right? P external is given, V1 is given. V2 we do not know. Since it is the isothermal process, so it has to follow the Boyle's law. The gas has to follow the Boyle's law. P1 V1 is equal to P2 V2. P1 is 5 atm. V1 is 2 liters. P2 is 1 atm. And V2 you can calculate. The final volume of the gas came out to be 10 liters, right? So V2 is equal to 10 liters. So calculate the work done in this irreversible process. It is minus P external 1 atm. V2 minus V1. 10 minus 2 comes out to be 8. So it's going to be minus 8 and its units are going to be in atm liter, because pressure in atm, volume in liters. But do we have to calculate everything in joules or liters? I assume that we have to calculate everything in joules. You know, 1 atm liter is equal to 101.3 joules. So approximately the value will be minus 808 joules. So this is the value of W. If you got the value of W, then Q has to be equal to minus W. If this is minus, so this will come out to be plus. So it's plus 808 joules. So this much amount of heat will be absorbed by the gas during the process. Is this clear? Is this clear to you? Quickly in the charts. Yeah? Is this clear to you, people? Let me know in the charts quickly. Perfect. Question was very simple. Expansion of the gas was happening. So by the way, how you got to know this is the case of expansion? Because the initial pressure of the gas was 5 atm and the final pressure of the gas is 1 atm. So pressure of the gas is decreasing from 5 to 1. If the pressure is decreasing, volume will be automatically increasing. This pressure is inversely proportional to volume at constant temperature, right? So pressure is decreasing, that means volume of the gas is increasing. So this is the case of expansion. Expansion is happening against constant external pressure. So it's irreversible expansion. And during the expansion, temperature is remaining constant. So it is irreversible isothermal expansion. Yeah? All right. This is one more question. Can you solve this one? Just say yes or no. Just say yes or no in the chats. You have got 6 moles of ideal gas. It expands isothermally from 1 liter to 10 liters at 300 Kelvin. Calculate the maximum work done by the gas. Calculate the maximum work done by the gas. First of all, it's mentioned that the initial volume of the gas is 1 liter. The final volume of the gas is 10 liters. So there is increase in the volume of the gas. That's something which I call as expansion. And during the expansion, the temperature of the system is remaining constant, 300 Kelvin. So it is the case of isothermal expansion. It is the case of isothermal expansion. Now the point is, if this is the case of isothermal expansion, it is not mentioned whether it is reversible or irreversible. So what should I consider? Should I consider it reversible or irreversible? What do you think? We are supposed to calculate maximum work. Do you remember when I taught you reversible, irreversible processes? I told you for the same amount of expansion, work done by the gas in reversible expansion will be greater than that of work done by the gas in irreversible expansion. Right? Perfect. So if this process will be happening reversibly, then only work done by the gas will be maximum. So I have to take this process as a reversible in nature. Then only we can calculate maximum work. There are 2 ways basically. Either the gas will be undergoing reversible expansion or irreversible expansion, right? But we have already discussed for the same amount of expansion, work done by the gas in reversible process is greater than that of work done by the gas in irreversible process. So I have to consider the process to be reversible, then only we can calculate the maximum work, because maximum work happens during reversible expansion, not in irreversible expansion. Right? So which result I'll be using? Work done in reversible process will be equal to minus 2.303 nRT, and it's going to be log of V2 divided by V1, right? So now we can do the calculation. Minus 2.303, N value, number of moles, 6, right? Let's say we have to calculate work in joules. If work has to be calculated in joules, then R value has to be 8.314. Temperature is given to us as 300 Kelvin, and it's log of V2 divided by V1. V2 is 10, V1 is 1. So log of 10 comes out to be 1, right? Solve this part and get the answer in joules. So this is going to be the maximum work done by the gas, right? Perfect. Is it clear? Is this concept clear to you? Quickly in the chats. Is this concept clear to everyone? Quickly, people, in the chats. Go for Navasti NEET. All right, guys, moving on. Now, there is something called as adiabatic process. What do you think are adiabatic processes? What happens in adiabatic processes? In case of adiabatic processes, there is no heat exchange between system and surroundings. Imagine that you have taken a gas in the container, right? The gas is undergoing expansion or compression, right? The gas is undergoing expansion or compression. During the expansion or compression, if there will be no heat exchange between system and surroundings, if during expansion or compression, there will be no heat exchange between system and surroundings, we'll say that the gas is undergoing adiabatic process. So when do we say the gas is undergoing adiabatic process? When there is no heat exchange between system and surroundings during the change in state. Okay? So Q value is 0 first of all. If Q is 0, Q is the first law of thermodynamics. Delta U is equal to Q plus W. And we know in case of adiabatic processes, Q value has to be 0. So delta U will be simply equal to W. And this particular result is only valid for what? It is valid for adiabatic processes. It is valid for adiabatic processes. So for adiabatic processes, delta U is always equal to W. Right? Now try to understand few important things. Since we got to know delta U is equal to W in case of adiabatic processes, right? Now, my dear students, W can have two values. W can have two values. Either the value of W will be negative or the value of W will be positive. Correct? If the value of W is negative, that represents the gas is undergoing expansion. This represents the gas is undergoing compression. Right? Now, if W is negative, that means delta U will come out to be negative. That means delta U will come out to be negative. What is delta U all about? Delta U is nothing, that is NCV T2 minus T1 for an ideal gas. So this term has to be negative. When will be this term negative? This term will only come out to be negative when T2 will be less than T1. When T2 will be less than T1. What is T2? Final temperature. What is T1? Initial temperature. What does that mean? That means when the ideal gas undergoes adiabatic expansion, temperature of the system decreases. Temperature of the system decreases. When the ideal gas undergoes adiabatic expansion, temperature of the system that decreases. And if the temperature of the system decreases, that means cooling of the system occurs. Cooling of the system occurs. How to talk about its physical interpretation? You'll get the idea in some time. But before that, let me complete one more statement. If the value of W is positive, that means this is a case of compression. If W is positive, that means delta U has to be positive. Delta U has to be positive. If delta U is positive, that means NCVT2 minus T1 has to be positive. Right? And when will be this term positive? This term will only be positive if T2 will be greater than T1. T2 is final temperature of the gas. T1 is the initial temperature of the gas. What does that mean? That means temperature of the gas, temperature of the system, it increases. If the temperature of the system increases, what does that mean? That means heating of the system occurs. Heating of the system occurs. So two statements we got over here. During adiabatic expansion of an ideal gas, temperature of the system decreases. During adiabatic compression of an ideal gas, temperature of the system increases. Now the point is why? Why it happens? Before talking about why, let me write these two statements. During adiabatic expansion of an ideal gas. During adiabatic expansion of an ideal gas, temperature of the gas decreases. That is, cooling of the gas takes place. Cooling of the gas takes place. Similarly, during adiabatic compression of an ideal gas. During adiabatic compression of an ideal gas, temperature of the gas increases, or we can say heating of gas occurs. Heating of gas occurs. Try to understand these two statements in detail. Understand what I'm going to say. Imagine that this is the container which we have. Imagine that this is the container which we have. And this is the piston right here at point A. We have got an ideal gas in the container. This is the ideal gas in the container, right? Now, my dear students, on the piston, there'll be two pressures. This is P gas, this is P external, right? Let's assume that the piston has to move from A to B. If the piston has to move from A to B, this has to be the case of expansion. And I'm assuming during the expansion, there'll be no heat exchange between system and surroundings. The system should neither absorb heat during the expansion, nor the system should release heat during the expansion, right? Then only I can call this expansion as adiabatic expansion. Then only I can call it as the adiabatic expansion. Now guys, try to understand one thing. When the gas will undergo expansion, during the expansion, work is done by the gas. So during the expansion, the gas is performing work. During the expansion, the gas is doing work. And how gas will be doing work basically? Gas will be utilizing its internal energy to perform this work, right? So during the expansion, the gas is doing work. The gas is consuming its internal energy to perform work. And I can say if the gas is consuming its internal energy during the expansion, so can I say the internal energy of the gas will decrease during the expansion? Yes, it will happen. The internal energy of the gas will decrease. And if the internal energy of the gas is decreasing during the expansion, since internal energy is directly proportional to temperature, so temperature of the gas will decrease too. So during the adiabatic expansion, temperature as well as internal energy of the gas decreases because the gas performs work which is happening on the cost of its internal energy, right? That's what you wrote here. During adiabatic expansion of the ideal gas, temperature of the gas decreases. So cooling of the gas occurs, right? Similarly, my dear students, just understand what will happen due to compression. What will happen during compression? During compression, work is done on the gas. During compression, work is done on the gas. And during compression, whatever work is done on the gas, that work is stored in the gas in the form of its internal energy. And if the work is stored in the gas in the form of its internal energy during compression, so does that mean during the compression, internal energy of the gas will increase, right? And if internal energy of the gas increases during the compression, does that mean temperature of the gas will increase? Absolutely, right? And if the temperature of the gas increases, does that mean heating of the gas occurs? Absolutely, heating of the gas occurs. That is the second statement which I wrote. During adiabatic compression of an ideal gas, temperature of the gas increases. That means system undergoes heating. The gas undergoes heating, right? Let me know once in the chats if it is clear. Quickly. Let me know once in the chats if it's clear. Quickly, guys. Everyone. Everyone. Yeah? Perfect. Now comes one more statement. That's important. I'm writing the statement for the same amount of expansion. For the same amount of expansion. For the same amount of expansion. Or let me first of all make you understand this statement, then I'll write it. See guys. For example, this is the initial position of the piston, right? This has to be the final position of the piston. The piston has to go from A to B. So it is absolutely the case of expansion. During the expansion, the gas should neither absorb heat nor release heat. So this has to be the case of adiabatic expansion. Let's say we are doing the expansion of 10 liters. Okay. Now, dear students, this adiabatic expansion can happen in two ways. There are two ways by which adiabatic expansion can happen. First is going to be a reversible adiabatic expansion. Second one is going to be irreversible adiabatic expansion. Whenever there is expansion, either reversible or irreversible, work is done by the gas. And we already know magnitude of work done by the gas in reversible expansion will be greater than that of magnitude of work done by the gas in irreversible expansion. Right? So, this expansion can happen in two ways, reversible or irreversible. Magnitude of work done by the gas in reversible expansion is more. If the magnitude of work done in reversible expansion is more, what does that mean? That means the gas will be consuming, the gas will be utilizing more energy during the reversible expansion, right? During the reversible expansion, the gas will be utilizing its more energy. Due to which, during the reversible expansion, the temperature of the gas during the reversible expansion will decrease more than that of decrease in the temperature through irreversible process. See, it's very clear. The expansion I'm doing in two ways. This adiabatic expansion, it can happen either reversibly or irreversibly. But right here, work done by the gas is more. If work done by the gas is more in reversible process, if work done by the gas is more in reversible process, that means the gas will be utilizing its internal energy more during this process. If the gas is utilizing its internal energy more, that means internal energy will be decreased more in reversible expansion. And if internal energy is decreased more in reversible expansion, temperature of the gas will decrease more in reversible expansion. Right? Perfect. So, if the final temperature of the gas is Tf here and Tf dash here, can you let me know where will be the final temperature less? Which value will be less, Tf or Tf dash? What do you think? Tf or Tf dash? What do you think? Which final, this is the final temperature, right? Which final temperature will be less? Where do you see the final temperature less? Quickly. So here the gas is doing more work, more utilization of internal energy, right? More decrease in temperature. So final temperature of the gas here will be less than that of final temperature of the gas in irreversible process. I hope this is clear. Right? I hope this is clear. So what we can understand from here, from this statement? This statement is telling me only one thing. Let's assume that you have to do the expansion of 10 liters, right? And the expansion has to be adiabatic. This adiabatic expansion can be done either reversibly or irreversibly, right? The same expansion can be done either reversibly or irreversibly. But final temperature in both the processes are different, right? The final temperature of the gas, right, in the reversible adiabatic expansion will be less than that of final temperature of the gas in case of irreversible adiabatic expansion. I hope this is clear. If this is clear, tell me one more. For example, this is the piston at point A. The piston has to come from point A to point B, right? So this is the case of compression. During the compression, there should be no heat exchange between system and surrounding. So this is the case of adiabatic compression. Let's say we have to do the adiabatic compression of 10 liters. This adiabatic compression can happen in two ways, reversibly and irreversibly. Reversibly and irreversibly. Now, whether the compression is happening reversibly or irreversibly, either ways work is done on the gas. Either ways work is done on the gas. But we know magnitude of work done during irreversible compression is greater than that of magnitude of work done in reversible compression. We have discussed that. So work done on the gas will be more. Work done on the gas will be more in case of irreversible process. If work done on the gas is more in irreversible process, that means, what does that mean? Whatever work is done on the gas, that work is stored in the gas in the form of internal energy. Where would have been the internal energy stored more? The internal energy will be stored more here. If the internal energy is stored more here, that means the temperature would have increased more during irreversible adiabatic compression. So if the final temperature of the gas is Tf here and the final temperature is Tf dash. So which temperature will be more? I'll say Tf dash will be more than that of Tf in case of adiabatic compression, right? Tf dash will be more. See, in these two things, work is done by the gas, whereas in these two things, work is done on the gas, right? Here, the gas was utilizing its internal energy to perform work. What is happening in these two things? These are the case of compression. So work isn't on the gas. Whatever work isn't on the gas, that work is stored in the gas in the form of internal energy, right? So internal energy is stored more, where work done on the gas is more. And wherever internal energy stored is more, there only temperature would have increased more, right? So if the final temperature of the gas here is Tf, here it's Tf dash. So eventually Tf dash should be more than that of Tf. I hope this is clear. Tell me it's clear. Yes or no in the chats? Quickly. Quickly, guys. Quickly in the chats. Yes or no? Perfect. Perfect, guys. Now comes few important things. How do we calculate work done in reversible adiabatic process? And how do we calculate work done in irreversible adiabatic process? Work done in reversible adiabatic and work done in irreversible adiabatic. How do we calculate these work? First of all, in case of reversible adiabatic process, when the ideal gas undergoes a reversible adiabatic process, how do we calculate work? First of all, in case of adiabatic, Q is 0. If Q is 0, that means delta U is equal to W. Or I'll say W reversible is equal to delta U. Delta U for the ideal gas is nothing, that's NCV minus T1. So this is very first result by means of which we can calculate work done. In case of what? In case of reversible adiabatic process. The first result through which you can calculate work done in reversible adiabatic process. First expression. Second expression. W reversible is equal to N, you are writing as such. TV is equal to R divided by gamma minus 1, if you remember. This is T2 and this is T1 here, right? Which you can write directly as NR delta T divided by gamma minus 1. This is one more result through which you can calculate work done in reversible adiabatic process. Similarly, you can convert it in one more form. nRT2 minus nRT1. nRT2 is nothing, that's P2V2. nRT1 is nothing, that's P1V1. So P1V1 divided by gamma minus 1. This is one more expression through which you can calculate work, right? nRT2. nRT2 means P2V2, right? P2V2 is equal to nRT2. Similarly, P1V1 is equal to nRT1 by using the ideal gas equation, that's all, right? So these are some expressions through which you can calculate work done in case of reversible adiabatic processes. Whereas, in case of irreversible adiabatic, we know in case of irreversible processes, how do we calculate work generally? Minus P external, V2 minus V1. So this is going to be my first result here. To calculate work in case of irreversible adiabatic. And you can convert it into different format as well. It will be minus P external. Instead of V2, you can write nRT2 divided by P2. Instead of V1, you can write nRT1 divided by P1. This can be one more result to calculate work done in case of irreversible adiabatic process. Irreversible adiabatic process. Yeah? Clear? My dear students, we have to use these results in the questions. So you have to remember these results. Perfect? Only thing, you have to differentiate whether the process is reversible or irreversible. Whenever in a question it's mentioned that external pressure is constant. So by closing your eyes, you'll consider the process to be irreversible. Whenever it's mentioned in the question that the expansion is single stage, it is a single stage expansion. Single stage expansion also means irreversible, right? Perfect. Now comes few more things. How do we calculate the final temperature of the gas? Final temperature of the gas during a reversible adiabatic process. Reversible adiabatic process. And how do we calculate the final temperature of the gas during irreversible adiabatic process? During irreversible adiabatic process. Correct? Two things we have to do now. Calculation of final temperature in reversible adiabatic and calculation of final temperature in irreversible adiabatic. We saw a few minutes back only during the expansion whether the adiabatic expansion is happening reversibly or irreversibly. In both the cases, final temperature is different, right? Similarly, adiabatic compression when happening reversibly and then irreversibly, in both the cases, the final temperature is different, right? Rahul, gamma is same, that's Cp by Cv, Poisson's ratio. Okay, so how do we calculate these final temperatures? How do we calculate the final temperatures basically? When the gas undergoes reversible adiabatic process or irreversible. My dear students, whenever it's mentioned that the gas is undergoing a reversible adiabatic process, two results you'll be using to calculate the final temperature of the gas. First result, T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. This is the first result which you will be using to calculate the final temperature of the gas T2, right? Final temperature of the gas T2. And assuming the gas is undergoing a reversible adiabatic process. Or you can use this particular result. P1 raised power 1 minus gamma, P1 raised power gamma is equal to P2 raised power 1 minus gamma, T2 raised power gamma. You can use this particular result as well to calculate the final temperature of the gas T2. Right? If the gas is undergoing reversible adiabatic process, then these are the two results which you'll be using to calculate the final temperature. Whereas if the gas is undergoing irreversible adiabatic process, how do we calculate the final temperature? First of all, in case of adiabatic processes, Q is 0. If Q is 0, that means W will be equal to delta U as per first law, right? But this is W irreversible here. W irreversible is nothing, that is minus P external V2 minus V1. Delta U for the ideal gas is NCV T2 minus T1. Either this is going to be the expression which you will be using to calculate the final temperature of the gas when the gas undergoes irreversible adiabatic process, or you can convert it into a different format as well. You can write it as minus P external. Instead of V2, you can write nRT2 divided by P2. Instead of V1, you can write nRT1 divided by P1. And this is going to be what? This is going to be N. CV is R divided by gamma minus 1. And this is going to be T2 minus T1, right? So NR, 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 everywhere gets cancelled out. So the final expression becomes minus P external, T2 divided by P2, minus T1 divided by P1. It will be equal to 1 divided by gamma minus 1. And it's going to be T2 minus T1. This can be one more expression through which you can calculate the final temperature of the gas which undergoes irreversible adiabatic process. Final temperature T2 of the gas which undergoes irreversible adiabatic process. Perfect. So these are two results here which you need to remember. Now let's try to see exactly what kind of questions can be asked, right, from these adiabatic processes. My dear students, the first question which is on your screen. The question is 1 mole of monoatomic gas. So we have got 1 mole of monoatomic gas. If the gas is monoatomic, that means CV will be equal to 3 by 2R, Cp will be equal to 5 by 2R. It's mentioned in the question. So we have got 1 mole of monoatomic gas which expands adiabatically at the initial temperature capital T. The initial temperature of the gas is T. Now, my dear students, the gas is undergoing expansion against constant external pressure. Of 1 atm. That means we have to consider the process to be irreversible. Against the constant external pressure of 1 atm. From 1 liter to 2 liters. So initial volume of the gas was 1 liter and final volume of the gas is 2 liters. Correct? Find the final temperature of the gas. T2 we have to calculate. Can we solve it? We have got 1 mole of monoatomic gas which expands adiabatically at initial temperature capital T. So we have got 1 mole of gas whose initial temperature is capital T. Now the gas is undergoing adiabatic expansion. And this is an irreversible adiabatic expansion. And during the adiabatic expansion, what happens to temperature? Temperature decreases. So if the initial temperature of the gas is capital T, the final temperature of the gas has to be less than capital T. As simple as that. Now, how do we calculate it? The process is irreversible. And in case of irreversible processes, one result I gave you a few minutes back to calculate the final temperature. What was that? That was minus. What was that result which we derived a few minutes back? Okay. So in case of irreversible process, in case of adiabatic process, Q value is 0. So delta U has to be equal to W. Right? W irreversible. So this was NCV T2 minus T1, and this was minus P external V2 minus V1, right? So N value is 1. CV for the gas is 3 by 2R. T2 we have to calculate. T1 is capital T is equal to minus P external. P external is 1 atm. V2 minus V1. V2 minus V1, that comes out to be 1 liter, right? So from this particular equation, T2 will come out to be capital T minus 2 divided by 3R. This is the final temperature of the gas which has undergone irreversible adiabatic expansion. Now, if it was mentioned in the same question that the gas is undergoing a reversible adiabatic expansion, at that point of time, how would you have calculated the final temperature? Then you would have used this result. T1 V1 raised per gamma minus 1. T2 V2 raised per gamma minus 1. T1 is capital T. V1 is 1. 1 raised per anything is 1 only. So T2 V2 was 2 liters raised per gamma minus 1. Gamma for monoatomic gases 5 by 3. So 5 by 3 minus 1 is 2 by 3. So T2 will be equal to capital T divided by 2 raised per 2 by 3. So this will be the final temperature of the gas when the gas undergoes a reversible process, a reversible adiabatic process. But in the question, it was mentioned that the gas is undergoing irreversible adiabatic. So you have to take care of these things. You have to understand basically whether the process is reversible or irreversible. If the process is irreversible, this is how you calculate the final temperature of it. If the process is reversible, then this is how you calculate the final temperature of the gas during the reversible adiabatic process. I hope it's clear. Yeah? Perfect. Okay, guys. So this was the first question. Let's move on to the second question. Let's see what the question says. Look at the question carefully. A sample of fluorocarbon. Fluorocarbon is a gas basically, right? A sample of fluorocarbon was allowed to expand reversibly and adiabatically. So it's mentioned that the process is reversibly adiabatic. It's mentioned in the question only that the process is reversibly adiabatic. A sample of fluorocarbon was allowed to expand reversibly and adiabatically to twice of its volume. If the volume of the gas was initially V, the final volume of the gas has to be 2 times V. During the expansion, the temperature dropped from 400 Kelvin to 100 Kelvin. So initial temperature of the gas was 400 Kelvin. The final temperature of the gas is given to us as 100 Kelvin. Assuming the ideal gas conditions, calculate the CV for the gas. We have to calculate CV for the gas, right? My dear students, CV we have to calculate. Do you know CV is like nothing? It is R divided by gamma minus 1, right? If you get the value of gamma, the question is done. Now the question is the process. The gas is undergoing a reversible adiabatic process. The gas is undergoing a reversible adiabatic process. In case of reversible adiabatic processes, we have studied this result. T1 V1 raised per gamma minus 1 is equal to T2 V2 raised per gamma minus 1. Right? This is one of the results which is valid for reversible adiabatic process. So I can utilize this result. T1 value, that's 400. V1 value, that's V raised per gamma minus, is equal to T2, that's 100. V2 is 2 times V raised per gamma minus. So 00 cancel. V raised per gamma minus 1, V raised per gamma minus 1 cancel. So over here we are left with 4, and on right side we are left with gamma minus 2 raised per gamma minus, right? So 4 you can write as 2 square. So 2 square is equal to 2 raised per gamma minus 1. So from this particular equation, you got to know gamma minus 1 is equal to 2. You got to know gamma minus 1 is equal to 2, right? And if gamma minus 1 is equal to 2, that means CV is equal to R divided by gamma minus 1 is 2. So CV value is nothing, it is R by 2. That's it. CV value is nothing, it's R by 2. I hope it's clear again. Yeah? It is R by 2. Now, now you must be thinking what will be the units of CV. That depends on the units of R. If you use the R value as 8.314 joules per Kelvin per mole, then CV value will come in joules per Kelvin per mole only, right? If you use the value of R as 0.0821 atm liter per Kelvin per mole, then CV value will be atm liter per Kelvin per mole only. Yeah? Perfect. So basically it depends on the value of R now. Whatever value of R you will take, accordingly, you'll be getting the units of CV. Yeah? This was one more question. Okay, let's have a look on this one. What this question says. Have a look on this particular question. A sample of 1 mole of argon at 1 atm pressure and 27 degrees centigrade expands reversibly and adiabatic. Look at the question carefully. We have got 1 mole of argon. We have got 1 mole of argon. Argon is monoatomic, right? A sample of 1 mole of argon at 1 atm pressure. At 1 atm pressure. Right? At 1 atm pressure and 27 degrees centigrade. The gas is kept at 27 degrees centigrade. Expands reversibly and adiabatically. The process is reversibly adiabatic. The process is reversibly adiabatic. From 1.25 liters to 2.5 liters. So V1 is 1.25 liters. V2 is 2.5 liters. So the gas is undergoing a reversible adiabatic expansion. Calculate the enthalpy change during the process. We have to calculate delta H during the process. The gas is undergoing a reversible adiabatic expansion, and during this reversible adiabatic expansion, we have to calculate delta H for the ideal gas. How do you calculate delta H? How do you calculate delta H? Delta H is NCP T2 minus T1. Correct? NCP T2 minus T1. T1 is given. N value is given. CP we can calculate since CV value is equal to 12.48, right? And you know, CP minus CV is equal to R. CP minus CV is equal to R. So CP will be equal to R plus CV. So CP will be equal to R is 8.314 joules per Kelvin per mole and CV is 12.48 joules per Kelvin per mole. So CP value will be approximately 21 joules per Kelvin per mole. Approximate value, right? And this 21 will be approximately equal to 5 divided by 2R. If you take the value of R as 8.314, so 8, 5, 40, 40 by 2 will be approximately 21 only. So CP is basically 5 by 2R. In short, CP is 5 by 2R. So delta H has to be equal. N value is 1. CP is 5 by 2R. 5 by 2R, right? Then you have to write T2 minus T1. T1 is given. T2 we have to calculate. The process is reversible adiabatic. And for reversible adiabatic processes, T1 V1 raised power gamma minus 1, it has to be equal to T2 V2 raised power gamma minus 1. So what is T1? What is T1? Initial temperature of the gas. How much was that? 300 Kelvin, right? That was 300 Kelvin. What is V1? V1 is 1.25 liters. 1.25 liters. Raised power gamma minus 1 is equal to T2 we have to calculate. What is V2? 2.5. Raised power gamma minus 1. So dear students, understand one simple thing. CP value you know. CV value you know. CP value you know. CV value you know. Can you get the gamma? Gamma is CP by CV. CP is equal to 21 and CV is 12.48. The value will be approximately how much? How much it's going to be? CP divided by CV. It's going to be 5 by 3. It's going to be approximately 5 by 3, right? Gamma will be 5 by 3. It's simple. CP value, we got to know it's approximately 21. CV is given. So CP divided by CV, it'll be 5 by 3 only. Absolutely, it'll be 5 by 3 only. Now guys, try to understand what I'm going to say. So 300 will remain as such. I'm going to write 1.25 as such, divided by 2.5. And I'm going to take gamma minus 1 common. This is equal to T2. So 300 multiplied by, this is 0.5. 0.5 raised power gamma minus 1. 0.5 raised power gamma is 5 by 3. 5 by 3 minus 1 is 2 by 3, right? Is equal to T2. Now it's mentioned in the question that this particular value, 0.5 raised power 2 by 3. 0.5 raised power 2 by 3. This value is given to us as 0.6. So T2 will be equal to 300 into 0.6. So T2 will be equal to 300 into 0.6, which comes out to be 180. I got the final temperature of the gas. If final temperature of the gas you got, so delta H has to be equal to 5 by 2 R, and final temperature is 180. Final temperature is 180. Now based on the value of R, you'll be getting the units of delta H. Let's assume that we have to get the delta H in calories. Let's assume that we have to get delta H in calories. That means R value you'll be using as 2 calories per Kelvin per mole. So 2 to cancel. 180 into 5 comes out to be 900 calories. This has to be the delta H value over here. right? Perfect. I hope you got to know how to deal with these sort of questions as well. It is simple. You have to understand first of all which kind of process is it? Is it reversibly adiabatic? Is it irreversibly adiabatic? Accordingly, you have to use the result and solve the question. Yeah. Perfect, guys. Oh wait, this is T2 minus T1. Okay, there is a calculation mistake. T2 is 180. There is minus T1 as well. And how much was T1? T1 was 300. So this won't be 900. This will be T2 minus T1. Now solve it, right? Now solve it and get the answer. Perfect. Agreed. My bad. Okay. I did not look at this T1. Perfect, guys. Okay, let's have a look on one more then. Let's have a look on one more question. Just a second. Just a second. Can you solve this question? Just look at the question and see whether you can solve this or not. Calculate the work done by the system in a single stage. Single stage means irreversible. Expansion of 2 moles of ideal gas whose gamma is given from 10 atm to 1 atm at 300 Kelvin. Can you do it? Work done in case of irreversible process. Work done in case of irreversible process. Can't you do it? Yeah? Can be done? Can be done? Quickly in the chats. You have to calculate work done during irreversible adiabatic expansion. N value is given, P1 is given, P2 is given, gamma is given, right? Only the final temperature is not given. So which relation you will be using to calculate final temperature? P1 raised power 1 minus gamma, T1 raised power gamma is equal to P2 raised power 1 minus gamma, T2 raised power gamma. From there you will calculate final temperature T2. And then you can use it in the formula to calculate work done in irreversible adiabatic process, right? Which is minus P external V2 minus V1, but V1, V2 is not given to us, so you can use the other formula. Other formula was minus P external multiplied by nRT2 divided by P2 minus nRT1 by P1. Correct? I mean, this is a simple question. You don't have to do anything like out of the box here. Okay. Let's have a look on one more question, what this question exactly is. The question is 1 mole of gas A whose CV is given plus 2 moles of gas B whose CV is also given. They are mixed in a container and expanded adiabatically and reversibly from 1 liter to 4 liters, starting at 300 Kelvin. What would be the work done in calories? Understand how this sort of a question is to be solved. As far as the question is concerned, this is a bit lengthy question, okay? It's a bit lengthy question. The question says that you have got a container and this container contains 2 gases, gas 1 and gas 2. Gas 1 and gas 2. Number of moles of gas 1 in the container is 1. Number of moles of gas 2 in the container is 2, right? CV for the gas 1, that's equal to 3R. CV for the gas 2, that's equal to 3 by 2R. Perfect. So basically we have got a mixture of gas. The initial temperature of the mixture is 320 Kelvin. Now, as per the question, this mixture of gas, it is undergoing expansion, reversible adiabatic expansion from 1 liter to 4 liters. So initial volume of the mixture is 1 liter, final volume of the mixture is 4 liters, right? Initial volume of the mixture is 1 liter, final volume of the mixture is 4 liters. So first of all, this mixture, let's assume that there is a piston here. The piston is going up. That means the mixture is undergoing expansion. And whenever the gaseous mixture undergoes expansion, we always say work is done by the gaseous mixture. We have to calculate that work, calculate the work done by the gaseous mixture. Now, my dear students, since this gaseous mixture is undergoing a reversible adiabatic process, and how do we calculate work done in reversible adiabatic processes? It is N CV T2 minus T1. Understand one thing. Since the gaseous mixture is undergoing a reversible process, so N over here, it stands for total moles present in the mixture because the mixture is undergoing expansion. PV is the molar heat capacity at constant volume for the gaseous mixture. T1 is the temperature of the mixture. T2 is the temperature of the mixture. So I have to calculate a lot of terms first of all. The first term which I'll be calculating, what is that? I'll be calculating CV for the mixture. I've told you how to calculate CV for the mixture. It's going to be equal to N1 CV1 plus N2 CV2 divided by N1 plus N2. Correct? Now, dear students, calculate the exact value of CV mixture from here. N1 value, that's 1. CV is 3R. So it's going to be 3R plus N2 is 2. CV2 is 3 by 2R. So 2 cancel. It becomes 3R also. N1 plus N2. N1 plus N2. 2 plus 1, 3. So this is 6R by 3. 6 by 3 is 2. The value is 2R. So CV for the mixture you calculate as 2R. Right? Since you calculate CV mixture, do you remember CP mixture minus CV mixture is R? CP mixture minus CV mixture is R. Do you remember that? So from here, can't you calculate CP for the mixture? Absolutely. CP for the mixture is R plus CV mixture. So R plus 2R makes it 3R. Right? So CP mixture you got. If you got the CP mixture, if you got the CV mixture as well, can't we calculate gamma for the mixture? How do we calculate gamma for the mixture? Gamma for the mixture is going to be CP mixture divided by what? Divided by CV mixture. Correct? This value is 3R. And this value is 2R. The value comes out to be 1.5. So you got the gamma as well. Perfect. If you got the gamma as well, the gaseous mixture is undergoing a reversible adiabatic process. So it has to follow this equation. T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. What is T1? The initial temperature of the mixture is 300. What is V1? Initial volume. Initial volume of the mixture is 1 liter. So 1 raised power anything is 1 is equal to T2. Right? T2. V2 is 4 liters. Raised power gamma minus 1. 1.5 minus 1 makes it 0.5. So 4 raised power 0.5. That means 4 raised power 1 by 2 is 2. 300 by 2 is 150. So T2, final temperature of the gas, came out to be 150 Kelvin. So I calculate final temperature as well. So initial temperature is given, final temperature is given. Final temperature we calculated, CV mixture we calculate, total moles we have. Now calculate work done during this reversible adiabatic process. It has to be equal to, what is N here? Total moles present in the mixture, which is 3. N. CV value. CV value for the mixture is 2R. It is 2R. Then you have got T2 minus T1. T2 minus T1. T2 minus T1. Right? T2 minus T1. How? Wait, this is 320 here, right? So 320 divided by 2 is 160. This is 160 right here. Alright. So T2 minus T1. T2 is 160. T1 is 320. So T2 minus T1 will come out to be minus 160. Perfect. So the final value will come out to be minus 960 R. If, for example, you have to get the answer in calories, put the value of R as 2. So W value over here comes out to be minus 960 multiplied by 2. And the final answer would come in calories. So this is how you calculate work in this particular case. Right? Is this concept clear to all of you? Is this concept clear to all of you? Yes or no in the chats? Yeah? So my dear students, these were some different types of questions which can be asked from what? These are the different types of questions which can be asked from your adiabatic process. Now let's talk about what is free expansion. It's a very simple topic. What is free expansion? How do you define the term free expansion? Free expansion is defined as expansion against zero external pressure. Or you can say expansion in vacuum. Expansion in vacuum. What it means, you'll get the idea in some time. Let me tell you, this process is always irreversible in nature. Work done in case of free expansion, that's always zero. Work done in case of free expansion, that's zero. Why is that? Let's have a look. Imagine that this is the container. Imagine that this is the container, and over here there is a piston. There is a piston over here. Perfect. This particular container, it contains, for example, an ideal gas. There's the ideal gas in the container, right? Now, my dear students, on this piston, how many pressures will be acting? Two pressure. This is P gas and this is P external, right? If by chance P gas and P external are equal, if by chance P gas and P external are equal, the piston won't show any moment at all. If, for example, P external starts to decrease, if P external starts to decrease, the piston will start go outwards. So there will be expansion. If suddenly P external approach towards zero, if suddenly vacuum got created from outside, if suddenly external pressure became zero, that means the piston will suddenly move outwards. So the process has to be fast. The process is fast. It's irreversible. It's irreversible. Right? So what I'm trying to say over here is, initially P gas and P external, they were equal. So the piston was not moving at all. Now suddenly P external dropped to zero. If P external dropped to zero, suddenly piston started moving outwards. So what happened to the volume of the gas? Volume of the gas increased. Volume of the gas increased. Increase in the volume of the gas is what you call as expansion. And expansion against zero external pressure, that's called as free expansion. So in free expansion, P external is zero. If P external is zero, what is W? W is equal to minus P external delta V. If P external is zero, W is zero. If P external is zero, W is zero. Right? If P external is zero, that means W value in case of free expansion, that has to be zero as well. Right? These are the only two things which you need to remember. Whenever you find a term mentioned in the question that the gas undergoes free expansion, that means expansion of the gas is happening against zero external pressure. There is no external pressure. Right? So work done will be zero in case of free expansion. Right? Now this particular free expansion, we can divide it into categories. We can divide it into categories. Right? We can divide it into categories. The first one I'll be calling as isothermal free expansion of an ideal gas. You can call it as the isothermal free expansion of an ideal gas. The second one I'll be calling as adiabatic free expansion of an ideal gas. Adiabatic free expansion of an ideal gas. Right? First of all, isothermal free expansion of an ideal gas. If it is a free expansion, W has to be zero. It is isothermal. That means ideal gas is undergoing isothermal process. If isothermal process is there, that means temperature is constant. If temperature is constant, delta T has to be zero. Whenever the ideal gas undergoes isothermal process, delta U has to be zero as well. Right? If delta U is zero, W is zero, use the first law. Delta U is equal to Q plus W. If delta U is zero, W is zero. Delta is zero, W is zero. So Q value will come out to be zero. Q value coming out to be zero. What does that mean? That simply tells you an isothermal free expansion. An isothermal free expansion of an ideal gas is adiabatic as well. An isothermal free expansion of an ideal gas is adiabatic as well. Right? It's particularly valid for ideal gas. Yeah. Similarly, you can talk about this adiabatic free expansion of ideal gas as well. How come? First of all, it's a free expansion. In free expansion, W is zero. The process is adiabatic, so Q has to be zero. W 0, Q 0. Use the first law. Delta U is equal to Q plus W. So delta U has to be zero. Delta U 0 means NCV delta T is equal to zero. That means delta T is zero. Delta T is zero means temperature is constant. What do we call that process in which temperature is constant? That is isothermal. Right? I can say an adiabatic free expansion of an ideal gas. An adiabatic free expansion of an ideal gas. Is isothermal as well. Is isothermal as well. This is one more statement. Free expansion means W0. Adiabatic means Q0. So delta U has to be 0 as per first law. That means NCV delta T has to be 0, right? So temperature will be constant. So if temperature is constant, the process has to be isothermal as well, right? So these are the two important statements which I would want you guys to remember from now onwards, right? My dear students, I think this much is enough for today. There is one session that is required, right? One session is required in this chapter, which will happen on Thursday, right? Which will happen on Thursday, day after tomorrow. Day after tomorrow, we'll have one more session at 5 p.m. So 5 to 9, 4 hours, we'll complete this chapter, right? There is a cyclic process left, entropy is left, Gibbs free energy is left. Okay, with that, your thermodynamics part will come to an end. Then thermochemistry, that's a different chapter, like heats of reactions, heat of formation, heat of combustion, etc., etc. Right? So with this, I'll be taking a leave. It was nice meeting you. Yeah. I'll see you guys again tomorrow. Not tomorrow, sorry, day after tomorrow. So day after tomorrow, we are going to have part 3 of thermodynamics and we'll be completing this chapter, right? And on Saturday, 5 p.m., we'll have chemical equilibrium in one shot. See guys, I could have finished this particular chapter in one session only. The point is, I do not want to miss anything basically, because we have got a lot of time, right? Time is there. We have got around 9 months till the examination, right? So we are not supposed to skip anything over here. That's why everything I'm teaching in detail, all the types of questions I'm doing, right? Just one thing you have to do, you just have to revise the notes and follow any practice problem book. That's all. That's all what you have to do. Nothing else. I hope you get it. Nothing else. I mean, I'm giving you the detailed content. You can check the entire YouTube, right? You won't be getting this much detailed content anywhere. Yeah, you can check it out. Perfect. Hello, I'll take a leave with this. I'll see you guys. Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, quickly just let me know if all of you can hear me, if I'm perfectly audible and visible to everyone. Quickly let me know in the chats with the thumbs ups. With the thumbs ups. Quickly let me know in the chats. Quickly, people. Good evening and welcome back. Good evening and welcome back, guys. Good evening and welcome back. Welcome back. Perfect. So, my dear students, do you remember till what topic did we discuss in the last session? Well, first of all, let me tell you, till now we are done with 2 sessions of thermodynamics. And today, it's going to be the last session of the chapter thermodynamics. We are going to discuss something really very important. Some topics from which questions are frequently asked in your NEET as well as JEE examination. All those topics I'll be covering in the today's session, right? And the session duration will be maximum for 3 hours. So we are not going to take any break in between. So 3 hours straight and let's finish the chapter off. And my dear students, on Saturday at 5 p.m. On Saturday at 5 p.m., we are going to have the one-shot session of the chapter Chemical Equilibrium, right? Shravan, thermochemistry will be dealt. That's a separate chapter basically, thermochemistry. Right now I'm talking about thermodynamics, right? Thermochemistry will be done after this. Perfect. So today we'll be completing thermodynamics part. On Saturday we shall be completing chemical equilibrium in one shot, right? And in the upcoming week we shall be completing the thermochemistry part as well. Okay? Yes, absolutely. They are more than sufficient. Perfect. So if you remember in the last session, we discussed till the free expansion. Free expansion was the last topic which we discussed in the last session, right? So right now we are going to start with the topic that is cyclic process. One of the important topics of the chapter, right? And my dear students, this particular topic is in your physics as well. And a lot of questions are asked from this topic in physics as well. So I'll try to make sure that after discussing the cyclic process, you should be able to solve all the questions in physics thermodynamics as well from the same topic. Yeah? Perfect. So are you guys ready for it? Are you guys ready for it? Quickly, let me know in the chats. Are you guys ready for it? Give me some thumbs up. Let me see the Josh of the session first. Quickly, people, in the chats. Everyone in the chats. Are you ready for the session? Are you all ready for the session? Say yes or no in the chats quickly. Perfect, guys. Perfect. So let's get going then. So before discussing the topic cyclic process, there are a few basic things which I would want to share with you. And what are those basic things? Let's have a look. My dear students, over here, I'm going to make a pressure volume curve. I'm going to make a pressure volume curve over here. Along y-axis, I'm plotting pressure of the gas. Along x-axis, I'm plotting volume of the gas. For example, I'm selecting 2 points over here. This is point A, and right here, this is point B. Okay, I'm selecting 2 points, point A, point B. For example, when the gas was at point A, when the gas in the container was at point A, let's assume volume of the gas was V1. And when the gas reached the point B, volume of the gas, for example, is V2, right? And over here, what exactly I'm going to do? I'm going to draw a straight line. And I'm showing the arrow towards the right, for example. Perfect. Can you let me know what should I be calling this particular curve as, this straight line? My dear students, do you see at every point on this line, pressure of the gas is remaining constant. Pressure of the gas is not changing, right? At every point on this line over here, at every point on this graph, pressure of the gas is remaining the same. So first of all, should I be calling this particular curve as isobar? Absolutely, I'll be calling this particular curve as isobar. So this AB, it represents isobaric process. It is simply telling you that the gas is undergoing isobaric process, right? It is simply telling you you are changing the state of the gas, but you are making sure on changing the state of the gas, you are not changing the pressure of the gas. Yeah? So point number 1. Point number 2, my dear students. Have a look exactly what I'm going to say. If I draw one more straight line like this, and for example, I'm showing arrow downwards or for example, arrow upwards, whatever, right? Leave the arrow aside. I'm drawing one straight line over here. Can you let me know this straight line over here, this graph, which thermodynamic process it represents? Can I say it represents basically your isobaric process, isochoric process? It represents your isochoric process. Perfect. Take any point on this graph. At every point on this graph, volume of the gas is remaining constant. Volume of the gas is not changing. So this particular line over here, it is simply telling you that the gas is undergoing isochoric process. What does that mean? That means you are changing the state of the gas, but you are making sure the volume of the gas does not change, right? You are changing the state of the gas, but you are making sure that the volume of the gas does not change. Perfect. So this line over here, it represents isochoric process. At the same time, my dear students, if I draw two curves like this, if I draw one hyperbola and for example, one more hyperbola, I'm showing arrow towards right. I've drawn two hyperbolas over here, right? If you remember, I had told you in the last session, place your thumb at the common point, curl your fingers in the clockwise direction. That curve which touches your fingers first, that has to be the isothermal. That has to be the isothermal curve, and the other one automatically it becomes the adiabatic curve. The other one automatically it becomes the adiabatic curve. This is something which I told you in the last session. Perfect. So my dear students, the first line which I've drawn over here, in which pressure of the gas is remaining constant, you're simply saying the gas is undergoing isobaric process. Similarly, this green colored line, the gas is undergoing isochoric process. The gas is undergoing isothermal process. The gas is undergoing adiabatic. I hope this is something which every one of you must be knowing now. Yeah? Perfect, clear? Now, after this, we are going to start with something called a cyclic process. Let's get to know exactly what this cyclic process exactly is all about. My dear students, I'm going to start exactly from the basics so that you can understand it properly, okay? First of all, as far as the definition of cyclic process is concerned, it is defined as that thermodynamic process in which system returns to its initial state. In which system returns to its initial state. That thermodynamic process in which the system returns to its initial state after going through a lot of steps. Okay, after going through a lot of steps. Now, what does that mean? For example, again, I'm going to plot a PV curve over here. This axis represents the pressure axis. This axis over here represents, for example, the volume axis. Now, my dear students, for example, I'm starting from point A. Let's assume that, first of all, I'm going from point A to point B, right? Then, for example, I'm going from point B to point C, right? And from C, I'm again coming back to A. So what has happened exactly? Can I say the system is returning to its initial state after going through a lot of steps? The first step which the gas is following, that is AB step. The second step is BC step. The third step is CA step, right? So I would categorically say the gas, which is my system, the system is returning to its initial state after going through a lot of steps, right? Whenever you see this kind of the process, this kind of the thermodynamic process in which system returns to its initial state after going through a lot of steps, you will say that your gas is undergoing, your system is undergoing a cyclic process, right? Can I say in case of the cyclic process, the initial state and the final state of the system is same, right? Initial state and final state of the system is same. See, we started from A and finally we reached to A as well, right? So whatever was my initial state, same is going to be my final state. So I would categorically say, in case of cyclic process, the initial state and final state of the system is same, right? At the same time, if you remember, I have told you categorically, change in the value of a state function. Change in the value of a state function for a cyclic process, that's always 0. What is the state function? State function depends only on initial and final state of the system. If the initial state and final state of the system is same, I must say change in the value of state function will be absolutely 0. Because the initial value of state function and final value of state function, that will be obviously same. Therefore, change in the value of state function for a cyclic process is 0. What does that mean? That means delta U net, or I'll say change in internal energy for the cyclic process, that has to be equal to 0. Enthalpy change during the cyclic process, delta H cyclic, that has to be 0, right? For example, delta G for the cyclic process, this will be 0. Similarly, delta S for the cyclic process, this absolutely again will be 0. What are these U, H, G, and S? U stands for internal energy, H stands for enthalpy, G stands for Gibbs free energy, S stands for entropy. All are state functions basically. And we already know change in the value of a state function for a cyclic process, that's always taken to be 0. Perfect. My dear students, if these points are clear to you, let's try to analyze them a bit more in detail. Let's try to understand few important things. Have a look what I'm going to say. Since I told you delta U net internal energy change during the cyclic process, that's always 0. Absolutely. Perfect. Now delta U net is simply going to be equal. It is simply going to be equal as per the first law of thermodynamics. Delta U is equal to Q plus W. So I would say delta U is equal to Q net plus W net. So Q net plus W net, it has to be 0 in case of the cyclic process. Or you can say Q net has to be equal to minus times W net for a cyclic process. This particular statement is valid for a cyclic process. Q net is always equal to minus times W net for a cyclic process. Perfect. I simply use the first law of thermodynamics. We know delta U for the cyclic process, that's 0. Delta U is nothing, that's Q plus W. If delta U net for the cyclic process is 0, therefore Q net plus W net has to be 0, or you can say Q net is equal to minus times the W net, right? This is one statement. One more statement. Few minutes back, if you remember, we have drawn a cyclic process like this. This was your pressure. This was your volume. You started from point A. From point A, you reached to point B. From point B, you reached to point C. From point C, you again reached to point A. So this was my cyclic process. Can I say this particular cyclic process actually contains 3 steps? First, the gas is following the process AB. Then the gas is following the process BC. Then the gas is following the process CA. So my dear students, as I told you, delta U net, net internal energy during the cyclic process, that has to be 0. What is this net internal energy change during the process? It simply is change in internal energy for the gas during the process AB plus change in the internal energy of the gas during the process BC plus change in the internal energy of the gas during the process CA. This whole term has to be 0. Point number 1, right? Similarly, point number 2. If I ask you what is Q net basically, what is Q net? Q net is basically net heat absorbed or released by the gas during the cyclic process, right? What is delta U? Delta U is the net change in internal energy, total change in internal energy of the gas during the cyclic process. That has to be 0. If I ask you Q net is total heat absorbed or released by the gas during the cyclic process. That also has to be equal to QAB plus QBC plus QCA. QCA. What is Q net? Total heat absorbed or released by the gas during the cyclic process. That has to be equal to heat absorbed or released by the gas during the process AB plus heat absorbed or released by the gas during the process BC plus heat absorbed or released by the gas during the process CA. Perfect. Similarly, if I ask you, what about W net? What about W net? Net work done during the cyclic process. Net work done during the cyclic process. It is also going to be equal to work done during the process AB plus work done during the process BC plus work done during the process CA. I hope all these terms are absolutely clear to everyone. Yeah. Now, my dear students, there are a few more things which I would want to share with you. And what are those things? Let's have a look. Let's have a look. First of all, let me tell you, area enclosed by the loop. Area enclosed by the loop. What is meant by this area enclosed by the loop? This is basically the area which is enclosed by this particular loop. Whenever you'll be calculating the area enclosed by the loop, area enclosed by the loop always gives us the magnitude of work done during the overall process. Whenever you need to calculate the magnitude of work during a cyclic process, what you have to just calculate? You just have to calculate the area which is enclosed by the loop. Whatever area is enclosed by the loop, that's something which is going to give you the magnitude of work done during the cyclic process, right? And my dear students, 2 more things which I would want you guys to remember. Whenever you see the clockwise cycle, whenever you see a clockwise cycle, whenever you see a clockwise cycle, have a look over here. Look at the arrows. First arrow is in this direction, then it goes downwards, then it goes in this direction. So it's a clockwise cycle basically. It's a clockwise cycle. During clockwise cycle, the value of W net, it comes out to be negative. During clockwise cycle, the value of W net, it comes out to be negative. You'll get the idea in some time. And similarly, during the anti-clockwise cycle, during the anti-clockwise cycle, the value of W net will come out to be positive. Will come out to be positive. So my dear students, whatever points I told you till now related to cyclic processes, all these points will be using in the questions, and I'm 100% sure if you remember all these points, for the cyclic process, you can easily solve all the questions based on the concept, right? So let's have a look exactly what kind of questions are asked and how do we deal with the questions. Yeah. So are you guys ready for the questions based on the cyclic process? Quickly, let me know in the chats. Quickly. This is the first and the basic question. The first and the basic question. Have a look, people. First of all, you are given with the pressure volume graph. This is the pressure volume graph, right? We are starting from point A. When the gas is at point A, its pressure is P1, its volume is V1. Then the gas reached point B, where its pressure is 6 times P1, its volume still is V1, right? Similarly, then the gas undergoes the process BC. Then the gas undergoes the process CA. So can I say the gas is returning to its initial state after going through a lot of steps? Absolutely. So should I be calling this particular process as a cyclic process? Absolutely. So I must say the gas which is there in the consideration, the gas is undergoing the cyclic process. First, the gas is undergoing the process AB, followed by BC, followed by CA, right? One thing. Second thing, my dear students, is the cycle clockwise or anti-clockwise? The cycle is anti-clockwise. Sorry, the cycle is clockwise. If the cycle is clockwise, the sign of W net has to come as negative. Sign of W net, net work done during the cyclic process, it has to be negative, right? Now, if I ask you, what about the magnitude of work done? What about the magnitude of work done during the cyclic process? As I told you, magnitude of work during the cyclic process is equal to area enclosed by the loop. How much area is enclosed by this particular loop? This is the area basically which is enclosed by the loop. It's enclosed by the loop. Do you see it is basically a right angle triangle? Can't we calculate area of the right angle triangle? Absolutely. So net work done is basically equal to area under the loop. Sorry, area enclosed by the loop. Area enclosed by the loop, and the loop is ABCA. Area enclosed by the loop ABCA, right? So I would say magnitude of net work done during the process is equal to half of base into height. What is base? It's going to be equal, see, from here to here it's V1. From here to here it's V1. Then from here to here it is, see, it is V1 from here to here. Then from here to here it is 3V1. So from here to here it's going to be 2 times V1, right? Simple. Perfect. So half of base. Base is going to be 2 times V1. And what about this hypotenuse? What about this hypotenuse? So from here to here it's P1. And from here to here it's 6P1. So hypotenuse has to be 5 times P1. Perfect. So half of base into height. Base is 2 times V1. Hypotenuse is 5 times P1. So 2 got cancelled. The values coming out to be 5 times P1 V1. So this is basically the magnitude of work done during the cyclic process. But am I supposed to calculate magnitude of work, or I'm supposed to calculate the net work? I'm supposed to calculate the net work done during the process. So I would say net work done during the process will be equal to, sign has to be negative. Magnitude is 5 times P1 V1, right? So this is the net work during the cyclic process. Yeah? Is this clear to everyone, people? Quickly in the chats. Is this clear to everyone? Say yes or no in the chats. The value of net work done is coming out to be negative. That means net work is done by the gas, right? Perfect. Say yes or no in the chats quickly. Say yes or no in the chats quickly if this question is clear. It is a very simple and basic question, my dear students, which you can get from the cyclic process, yeah? Right? Perfect. Perfect, guys. Perfect. Moving on to one more question. Let's see if you can solve this or not. See, guys, I hope you can see the graph. Can you see the graph? A second. I think it's not properly visible, but I think you can, right? So you're starting from point A, then you are going from point A to point B. This is the first line, A to B, right? Then from B to C, right? And then from C to A. The arrows are towards, this is the first arrow, this is the second arrow, this is the third arrow, right? And at A, temperature is given, B, temperature is given, C, temperature is given. And we are given with the pressure volume graph over here. First of all, you need to understand, before looking at the question, you need to understand whether the process is cyclic or not. Absolutely, the process is cyclic. The process is cyclic, right? It's a cyclic process. Yeah, number one. Number two, as per the question is concerned, 1 mole of an ideal gas. As far as the question is concerned, we have got 1 mole of ideal gas, which is monoatomic in nature. If the gas is monoatomic, its CV value has to be 3 by 2R. Its CP value has to be 5 by 2R. Now, as per the question, 1 mole of the ideal monoatomic gas is taken through the cycle shown below. Calculate AB and calculate CA. So we have to calculate QAB and then we have to calculate QCA. What is QAB first of all? Just try to understand. What is QAB? QAB is heat absorbed or released by the gas during the process AB. QAB, it is basically the heat absorbed or released by the gas during the process AB. What is this AB process? Is this AB process isochoric? Absolutely, it's isochoric, right? During the process AB, I would say volume of the gas is remaining constant. During the process AB, I would say volume of the gas is remaining constant. So what is QAB then? QAB represents heat released or absorbed by the gas at constant volume. QAB is heat absorbed or released by the gas at constant volume. And for the ideal gas, you know, that has to be equal to NCV delta T, which is T2 minus T1. Perfect. Similarly, we have to calculate QCA. What is QCA? Look at the process CA. Is the CA process isochoric or isobaric? CA process is isobaric. Pressure throughout this process is remaining the same, right? Pressure throughout the process is remaining constant. So this process is isobaric, right? So CA process is happening at constant pressure. So what is QCA then? It is the amount of heat absorbed or released by the gas at constant pressure, QP. And you must be knowing QP, that is basically equal to NCP T2 minus T1 for the ideal gas. I hope this is clear to everyone. Basically, I told you in the last session, heat absorbed or released by the gas at constant volume. That's basically delta U, right? That's basically delta U. So delta U for the process AB. Similarly, QP. QP is basically delta H, right? QP, heat absorbed or released by the gas at constant pressure. That's delta H, right? And delta H for the ideal gas, that's nothing. That's NCP delta T. Now, guys, look at the process AB carefully. Look at the process AB carefully. During the process AB, I would say this is the initial temperature. This is the final temperature. During the process AB, initial temperature, final temperature we calculated. Now, N value is given to us as the equation, that's 1. CV value for the gas is 3 by 2R and it's T2 minus T1. 600 minus 300, that comes out to be 300, right? Perfect. So this is 900 divided by 2, which comes out to be 450. So the value comes out to be 450R. 450R. This is the value of heat. This is the value of heat. And the sign over here is coming out to be positive. If the sign is coming out to be positive, if Q value is coming out to be positive, that means during the process AB, heat is absorbed by the gas. And this much heat is absorbed by the gas during the process AB. Now talk about the process CA. Q for the process CA. That will be calculated through NCP T2 minus T1. Now in the process CA, during the process CA, during the process C to A, I'll say this is the initial temperature and this is the final temperature. Perfect. Now, N value, you know that's 1. CP value, that's 5 by 2R. And it has to be T2 minus T1. This is T2, this is T1. So 300 minus 450. The value comes out to be minus 150. Perfect. So it is going to be 5 into 150 comes out to be minus 750 R divided by 2. This is the value of Q during the process CA. So dear students, is the value of Q coming out to be positive or negative? It's coming out to be negative. If the value of Q during the process CA is negative, that means during the process CA, heat is released by the gas. And this much amount of heat is released by the gas during the process CA. Perfect. For example, you have to calculate QAB and QCA in calories. If it is to be calculated in calories, then put the value of R as 2 calories per Kelvin per mole. Put the value of R as 2 calories per Kelvin per mole, right? So put the value of R as 2, the final answer will come out to be, it's going to be 900 calories. So this much amount of heat is absorbed during the process AB, right? Similarly, it's going to be R value 2, 2 to cancel, the value is going to be minus 750 calories. So 750 calories of heat is released during the process CA. And these were the two things which we were supposed to calculate as far as the question was concerned. So let me know once in the chats if this is super clear to everyone, quickly. Quickly, my dear students, in the chats. Let me know quickly in the chats if all these things are clear. Whatever I told you till now, If all these things are clear, let me know quickly in the chats. Everyone. Everyone. Let me know quickly in the chats. Yeah? Perfectly done? Now, my dear students, look at this particular question and just try to analyze how exactly this sort of a question is to be solved. Let's try to understand. Let's try to understand how this sort of equation is to be solved. As far as this particular question is concerned, we are supposed to calculate Q net, W net, delta U net, and delta H net for this overall cyclic process. It's mentioned in the question that we have to take 1 ATM liter as 100 joules. R value, we have to take 8 joules per Kelvin per mole. And this particular cyclic process, it's valid for 1 mole of monoatomic gas. Try to understand exactly how this sort of equation is to be solved. Now, dear students, first thing, as far as the question is concerned, we are given with 1 mole of ideal gas. And the ideal gas is monoatomic in nature. So CV for the ideal gas is 3 by 2R. And CP for the ideal gas, that's 5 by 2R. Because the gas is monoatomic in nature, right? Now look at the graph carefully. Look at the process carefully. Is it cyclic? Is it cyclic? The initial state and the final state of the system is same. So absolutely it's a cyclic process. Absolutely it's a cyclic process. So whatever parameters we have discussed related to the cyclic process, all these things you can utilize over here in this particular question. Now, first of all, what are we supposed to calculate? If I ask you, what about delta U net for the cyclic process? Net internal energy change during the cyclic process. My dear students, as I told you a few minutes back, change in the value of a state function for a net cyclic process, that's always 0. So delta U net for the cyclic process, that has to be 0. Similarly, delta H net for the cyclic process, this again has to be 0 only. Something which we already discussed. Because U and H, they are the state functions. And change in the value of a state function for a cyclic process, that's always going to be 0. Right? Very simple and basic. Now at the same time, delta U, delta H for the cyclic process we have calculated. Now we have to calculate Q net and W net, right? If I ask you what is Q net, you'll say Q net means total heat absorbed or released by the gas during the cyclic process. Okay, so Q net has to be equal to QAB plus QBC plus QCA. Similarly, W net has to be equal to WAB plus WBC plus WCA. Now you must be thinking, why we have to calculate W net like this? Why can't we calculate area enclosed by the loop? Yes, students, you cannot calculate the area enclosed by the loop because it's not a triangle, it's not a square whose area you can easily calculate, right? Perfect. Now try to understand a few more things. First of all, at point A, the temperature of the gas is 400 Kelvin. Now the gas is changing its state from A to B. During the process AB, is the pressure remaining same? Absolutely, during the process AB, pressure is remaining same. Now, if you use the ideal gas equation, PV is equal to nRT, right? During the process AB, pressure is remaining constant. Number of moles of the gas, those are already constant. R is already constant. So volume has to be directly proportional to temperature. Now, at point A, what is the volume? 16 liters. At point B, what is the volume? 32 liters. That means when we go from A to B, is the volume of the gas doubling basically? Absolutely. And if the volume doubles, the temperature of the gas doubles too. Simple and basic. Yeah? On going from A to B basically, pressure is remaining constant, but the volume of the gas is doubling basically. This is the case of expansion, volume doubles. And if the volume doubles, the temperature automatically doubles, right? Temperature at point A was 400, so at point B, it has to be 800 Kelvin, right? Similarly, when you talk about B to C, during the process B to C, when the gas undergoes the process B to C, what happens exactly? When the gas undergoes the process B to C, what happens? Volume of the gas is constant. If volume is constant and already constant, I can say pressure is directly proportional to temperature. Now, when you move from B to C, what is happening to pressure? At point B, the pressure was 2 atm. At point C, the pressure is 1 atm. So from B to C, the pressure is reduced by half. If the pressure is reduced by half, can I say temperature will automatically reduce by half? Because pressure is directly proportional to temperature when volume is constant. If pressure becomes P by 2, that means temperature also has to become T by 2. So temperature over here was 800 Kelvin. So that means at point C, it has to be 400 Kelvin. Perfect. At point C, it has to be 400 Kelvin. Now, people, I would want you guys to understand few important things now. During the process AB process, it's isobaric because the pressure is remaining constant. BC process, it's isochoric. Volume of the system is not changing. Volume of the gas is not changing, right? During the process CA, at point C, temperature was 400 Kelvin. At point A, the temperature again is 400 Kelvin. That means I'll assume that during this particular process, the temperature of the gas is not changing at all. And that particular process in which the temperature of the gas does not change at all, you'll be calling that as isothermal process. Now the graph is curved, so it has to be a reversible isothermal process. So CA process is reversible isothermal. So first of all, you identify your different processes over here. Okay. Now, dear students, let's try to analyze all these processes one by one. First of all, talking about the process AB. AB process. AB process is isobaric. The amount of heat absorbed or released during the process AB is QAB. This is the amount of heat absorbed or released during the process AB. But AB process, pressure is remaining constant, right? So heat absorbed or released by the process during AB, that will be equal to QP basically. During the process AB, AB is isobaric. Pressure of the gas is not changing. So QAB is basically heat absorbed or released by the gas, constant pressure. That has to be equal to delta H or the process AB, which will be equal to NCP T2 minus T1. Or I'll write final temperature minus initial temperature. Perfect. Now calculate this QAB over here. QAB from this particular equation will come out to be N value is 1. CP value as per the equation. Since it's a monoatomic gas, so CP has to be 5 by 2R. Final temperature minus initial. Final minus initial. So value has to be 400. Value has to be 400. So what is the overall value which we'll be getting from here? 2, 1, 2, 2, 5, 2s are 10. So it's 1000 R. 1000 R. R value we have to take as 8. So it is 8000 joules. So we got to know the value of QAB basically. The value of QAB is coming out to be positive. That means during the process AB, heat is absorbed by the gas. And how much heat is absorbed by the gas? I'll say 8000 joules of heat is absorbed by the gas during the process AB. Perfect. Now similarly, my dear students, since I'm analyzing the process AB, so let's calculate WAB as well. Let's calculate WAB as well. Since the AB process is isobaric, and in case of isobaric processes, how do we calculate work? It's minus P delta V, which is simply V final minus V initial. So I'll start with minus. Pressure of the gas is simply 2 atm. V final minus V initial. V final is 32 liters. V initial is 16 liters. So 32 minus 16 comes out to be 16. The value comes out to be minus 32 atm liter. Now, as per the equation, they are telling you 1 atm liter is equal to 100 joules. So it has to be minus 3200 joules. Minus 3200 joules. This is the value of WAB as well. So you have analyzed the process WAB. Perfect. You have analyzed the process AB in which you have calculated QAB, WAB. Perfect. Now, my dear students, it's time to analyze the process BC. It is time to analyze the process BC. Now, BC process, it's isochoric. It is isochoric. We have already discussed that. That means volume of the gas is remaining constant during the process BC. During the process BC, volume of the gas is remaining constant, right? If volume of the gas is remaining constant during the process BC, so what about WBC? If volume remains constant, WBC has to be 0, right? What about QBC? Heat absorbed or released by the gas during the process BC. Heat absorbed or released by the gas at constant volume. Basically QV. And QV is nothing, that's delta U for the process BC. And delta U for the ideal gas is nothing, it is NCV, T final minus T initial, right? Now calculate this QBC exactly how much it comes. N value 1. CV value for the gas is 3 by 2 R. R value we have to take as 8. T final minus T initial. During the process BC, this is T final, this is T initial. So 400 minus 800 comes out to be minus 400. This is minus 400. Calculate the value. It's 2, 1, 2, 4. 4 3s are 12. 12 4s are 48. So it's minus 4800 joules. So that means during the process BC, heat is released. When the gas is undergoing the process BC, heat is released. How much heat is released? 4800 joules of heat is released during the process BC. So BC process we have analyzed. WBC we have calculated, right? WBC we have calculated since it was isochoric, and QBC again we have calculated. Now there is one process pending, that is CA. Now look at the process CA. Look at the process CA. Is the CA process isothermal? That means during the CA process, whenever the ideal gas undergoes the process C to A, that means the ideal gas is undergoing a reversible isothermal process. And whenever the ideal gas undergoes a reversible isothermal process, or in general, whenever the ideal gas undergoes isothermal process, delta U for the ideal gas during that process, that has to be 0, something which we discussed in the last session. So delta U for the process CA, that has to be 0 because CA process isothermal in nature, right? So delta U CA will be nothing. It will be QCA plus WCA, because delta U is Q plus W. So delta U CA is QCA plus WCA. That has to be 0. So I would say QCA will be equal to minus times WCA. Perfect. So my dear students, just calculate one of the two. Just calculate one of the two. I'll try to calculate work done during the process CA. CA process is reversible isothermal. Do you remember how do we calculate work done in reversible isothermal processes? In the last session, I gave you one result, minus 2.303 nRT. It's log of V final divided by V initial, V2 by V1, if you remember. So WCA has to be equal to minus 2.303, N value is 1, R value is 8, temperature is how much? 400 Kelvin. Perfect. And it's going to be log of V final divided by V initial. V final is 16 liters, V initial, that's 32 liters, so 16 by 32. 16 divided by 32. Now, solve it, get the value of WCA, right? Let's assume that this is approximately, I'm taking as 2. So 8 2s are 16, 16 into 4 is 48. So it's minus 4800 log of 1 by 2. Log of 1 by 2. Log of 1 by 2 you can write as, log of 1 by 2 you can write as log of 1 minus log of 2. Perfect. Log of 1 is 0 and log of 2 is 0.3. So WCA is coming out to be minus plus 4800 multiplied by 0.3, and the answer is going to be in joules. So this is the value of WCA. WCA you got. If you got WCA, that means QCA, you just have to reverse the sign. You just have to reverse the sign, right? So it's going to be minus times 4800 multiplied by 0.3 joules. This is the value of QCA as well. So you have analyzed all the process in detail. AB process you analyzed, BC you analyzed, then CA you analyzed. All the process you analyzed. Perfect. You got the value of QAB. You got the value of QBC, right? You got the value of QCA. Similarly, WAB, WBC, WCA, all the things you got. Now you have to put all these terms in this expression and get the value of QNet, which you were supposed to calculate. Similarly, put all the values of WAB, WBC, WCA in this expression and get the value of WNet, which you were supposed to calculate, right? The equation was a bit lengthy, no doubt, but I hope from this particular equation, you could understand it in a better way. Yeah? So let me know in the chats if all the things are clear till here. Quickly. Quickly, people. So I analyzed all the processes separately. I got QAB, QBC, QCA, then added them up, got the QNet. Similarly, I calculated WAB, WBC, WCA, and then added them up. I got the value of WNet. That's all. Yeah? Perfect, guys. Now there is one more important thing. Just a second. In cyclic process, there is one more small topic, and I would want you guys to clear that as well, right here only. That is efficiency of a cyclic process. How do we calculate the efficiency of a cyclic process? For example, I'm going to plot a graph over here. Pressure volume curve, P versus V. Okay. I'm starting from point A. I'm going from A to B. Then I'm going from B to C. Then, for example, I'm going from C to A. Arrow I'm showing towards right. Clockwise cycle. Perfect. This is the cyclic process. If I ask you to calculate the efficiency of this cyclic process, how do you calculate the efficiency of a cyclic process? Efficiency of the cyclic process is always equal. Efficiency of the cyclic process is calculated by the formula area enclosed by the loop, area enclosed by the loop divided by area under the curve, divided by area under the curve. Now, what is area enclosed by the loop? This is the area enclosed by the loop, right? That means which area I'm talking about? I'm talking about the area ABCA. ABCA, this area I'm talking about. Now, area under the loop, area under the curve, what that is? This is the total area under the curve. Let's say this is A, this is B, let's say this is E, let's say this is F. This whole area is the area under the curve basically, right? So area under the curve will be basically the area ABEF, 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 right? When you divide the two, you need to multiply this with 100 at the end. You'll be getting the efficiency of the cyclic process. Yeah. Now let's do one question so that you'll understand it in a better way. So a percentage efficiency of a cyclic process is always equal to area enclosed by the loop divided by area under the loop, under the curve, multiplied by 100. For example, this is the cyclic process which is given to us. This is the cyclic process which is given to us. Okay. We have to calculate the efficiency of the cyclic process. Efficiency of the cyclic process will be equal. Efficiency of this cyclic process will be equal to area enclosed by the loop. That means this area I'm talking about first of all. Area enclosed by the loop, which is going to be basically area of this particular triangle, which has to be half of base into height. Base is from here to here, which is 4 liters. Height is from here to here, which is 1 atm. So this is area enclosed by the loop divided by area under the curve. Area under curve, it means this whole area, area under this curve. My dear students, this particular diagram, if you see, it is trapezium. How do we calculate area of trapezium? Half of sum of parallel sides, which is 1 plus 2. Half of sum of parallel sides into height. This is the height from here to here, 2 to 6, that means 4. Perfect. And at the end, you need to multiply it with 100. So numerator comes out to be 2, denominator is 2 plus 1, 3, 3, 4, 12, 12 by 2 is 6. So 2 by 6 multiplied by 100. So efficiency of the cyclic process will be approximately 33%, right? So this is basically how you calculate the efficiency of the cyclic process. Area enclosed by the loop divided by area under the curve multiplied by 100. Quickly, let me know in the chats if this is super clear to you. Then only I can start one more topic. Quickly, guys, everyone. Everyone in the chats, quickly. Everyone in the chats. Yeah? The loop was triangular in shape. So area enclosed by the loop was area of triangle. Area under the curve, that was area of the trapezium basically. Right? So area of the triangle divided by area of trapezium multiplied by 100. That's all. Perfect. Let me know, people in the chats, if all the things are clear till here. Let me know quickly in the chats with the thumbs ups, everyone. Everyone in the chats. Everyone in the chats. Yeah? Perfect, guys. So now let's try to discuss one more important topic, from which question again frequently comes. And what is the name of the topic? That's entropy, right? You must have heard about it. Entropy. Entropy is represented by S. One is saying how to remember all these results, the way I have remembered them, by practicing many a times. That's it. Yeah. Make a separate formula sheet. Try to check them up 15 minutes every day. You'll remember all the formulas of the physical chemistry. Just try to make the formula sheets of physical chemistry basically. Okay, so entropy, which is denoted by S. My dear students, basically entropy is defined in two ways. There is first of all a mathematical definition of entropy, which I'll be discussing in some time. And there is one more way of interpreting entropy from its physical significance. There are two ways by means of which you can understand entropy. One way is to define the entropy mathematically. Another way is to understand the concept of entropy from its physical significance. So the second part I'm going to discuss first. Okay, so see, if I talk about entropy, it gives the measure of unavailable energy. It gives the measure of unavailable energy present in the system. Point number one. Point number two. It gives the measure of degree of randomness. It gives the measure of degree of randomness or disorderness present in the system. It gives the measure of degree of randomness or disorderness present in the system. More disordered the system, more disordered, or I'll say more random the system, more is going to be the entropy of the system. These are the 3 points which I would want you guys to remember first of all. What is entropy? It gives the measure of unavailable energy present in the system. So basically, my dear students, for example, this is the gas in the container. For example, just to make you understand, this gas is my system, right? My dear students, in the system, actually, there are two types of energies. There are two types of energies present in the system, basically. One is called as available energy. One is called as unavailable energy. There are two types of energies basically present in the system. One is called as available, one is called as unavailable, right? This available energy, what is the use of this available energy? What is this available energy? I would say this available energy, it is converted into what? It is converted into useful work. Useful work is also called as non-PV work. Useful work is also called as non-PV work. Well, I'm not going to discuss about this right now. I'll be discussing this part, available energy part, I'll be discussing when I'll be teaching you the Gibbs free energy, not now. I'll have to discuss only this part right here, unavailable energy. This available energy I'll be discussing after some time when I'll be discussing Gibbs free energy with you. Okay. So first of all, a system always has two types of energies. One is available, one is unavailable. This available energy, it is converted into what? It is converted into useful work. Useful work is also called as non-PV work. What that is a separate debate, which we shall be discussing afterwards. The other type of energy of the system, that's unavailable. And what this unavailable energy in the system does, this unavailable energy in the system, it tries to increase the disorderness of the system. It tries to increase the randomness of the system. It tries to increase the randomness of the system. And that disorderness, that randomness present in the system is measured by the factor called as entropy. So basically, entropy, it gives the measure of unavailable energy present in the system. And this unavailable energy in the system, it tries to increase what? It tries to increase the disorderness of the system. It tries to increase the randomness of the particles present in the system. And that randomness is measured by the factor called as entropy. So what is entropy? Entropy is just a factor through which you get the idea about the degree of randomness, the degree of disorderness present in the system. Entropy is the factor through which you get the idea about the unavailable energy present in the system. So can I say, more the unavailable energy in the system means more random the system will be, more disordered the system will be, and more the disorderness of the system, you can say more will be the entropy of the system, right? So these 3 points which I discussed over here. More random or disordered the system, more is going to be the entropy of the system. That's all. Yeah. Now, guys, just tell me one thing. For example, if I'll be having solid, liquid, and gas under similar conditions, solid, liquid, and gas. If I ask you to compare their entropies, can you let me know which system will be more random? Is solid, liquid, or gas? Gas particles are more random than liquid, and liquid is more random than solid. More the randomness, more the disorderness, more has to be the entropy. So if solid, liquid, or gas are present at similar conditions, so I must say solid gas will have maximum entropy, followed by liquid, followed by solid. Point number one. Point number two. If I talk about solids in particular, you have got two types of solids basically, right? One is called as crystalline solid, and one is called as amorphous solid. My dear students, do you remember we have discussed this in solid state? Crystalline solids have got ordered arrangement of constituent particles, and amorphous solids, they have got disordered arrangement of constituent particles. So if I compare the two, where is the disorder is more? Crystalline or amorphous? I'll say amorphous has got more disorder. More the disorder, more the entropy. That's all. Simple and basic. Perfect. Now there are a few more things which I would want you guys to remember. What is that? See, whenever during the process entropy of the system increases, let's say during the process entropy of the gas, entropy of the system increases. If entropy of the system increases, that means change in entropy, which is going to be S final minus S initial. Final entropy minus initial entropy. If entropy of the system is increasing, that means final entropy of the system will be more. Initial entropy of the system will be less. So this difference has to come as positive. Perfect. So whenever I say from now onwards that delta S for the system is positive, that means that the entropy of the system is increasing. Whenever I say change in entropy is positive, that means entropy of the system is increasing. And similarly, when the entropy of the system decreases, delta S, change in entropy, S final minus S initial, this value comes out to be negative. So from now onwards, whenever I say that entropy change is negative, that means entropy of the system will be decreasing. If I say entropy change of the system is positive, that means entropy of the system is increasing. One more important point which you have to take a note of. Yeah. Similarly, guys, one more important point. As the number of atoms in a molecule, increases, the structure tries to become complex. The structure becomes complex. And when the structure becomes complex, energy states in the molecule basically increases, due to which disorderness increases. And hence, at the end, I must say, entropy increases. This is one more statement which I would want you guys to remember so that you can solve the questions which are based on the same statement. As the number of atoms in the molecule increases, entropy of the molecule increases because structure tries to become more complex. As complex the structure, more the complexity of the structure, more will be the energy states in the structure basically, right? And more the energy states means more is going to be the entropy, more is going to be the disorder. That's all. And where do I use these concepts? Let's try to understand. See, guys. For example, you have got NO2 and N2O4. More the atoms, more complex the structure, more the entropy. So among these two, which will be having more entropy? N2O4. SO2, SO3. More the atoms in the molecule, more the entropy. CH4, C2H6. C2H6 will have more entropy because more atoms in the molecule. More atoms means more complex the structure, right? Similarly, these are few more questions. These are few more basic questions. What is the sign of delta S in the following reaction? Is the sign of delta S positive or negative? Look at the first example. As far as the first example, H2 gas is getting converted into 2 times H gas. This is my first reaction, in which H2 gas getting converted into 2 times H gas. Right here, the stoichiometric coefficient is 1. Right here, the stoichiometric coefficient is 2. So I'll say this 1 represents, it is 1 mole of H2. It gives 2 moles of H. 1 mole of H2 gives 2 moles of H. So during the process, are the moles increasing or decreasing? During the process, I would say the moles are increasing. If the moles are increasing, can I say the particles are basically increasing? And if particles increase, what will happen to the randomness? Randomness will increase, disorderness will increase, right? And if the randomness or disorderness increases, that means the entropy will increase. And when the entropy increases, delta S sign has to be positive. So in the first process, delta S sign will be positive, right? Talk about the second one. The second one is SO2 gas plus O2 gas. What is it giving me? It's giving me SO3 gas. First of all, write it in the balanced format. Now it's a balanced chemical equation, right? Now guys, have a look. This is 1 over here, this is 1 by 2. So 1 plus 1 by 2 makes it 3 by 2. And on the reactor, on the product side, this is 1. So I'll say 3 by 2 moles are giving us 1 moles. You have got 3 by 2 gaseous moles on reactant side. You have got 1 mole of gaseous products basically. So 3 by 2 is basically 1.5, correct? So 1.5 moles on the reactant side, 1 mole on the product side. So during the process, are the moles increasing or decreasing? The gaseous moles are decreasing basically. The gaseous moles are decreasing. Over here, gaseous moles were increasing. Right here, gaseous moles are decreasing. That means the number of particles will be decreasing, right? Particles will be decreasing. Disorderness will be decreasing. Entropy will be decreasing. That means delta S sign has to be negative. So in this process, the value of delta S has to be negative. Correct? Simple. Look at the third one. This is solid. This is gas. Solid is getting converted into gas. If solid is getting converted into gas, that automatically tells you that disorderness is increasing. If disorderness increases, entropy increases, delta S positive, right? Liquid into solid, delta S negative, entropy decreases, disorderness decreases. Diamond into graphite, diamond into graphite. In case of diamond, every carbon is attached to 4 other carbon atoms. In case of graphite, every carbon is attached to only 3 carbon atoms, right? So where is the randomness, disorderness more? Diamond is ordered, graphite is comparatively disordered. Ordered to disordered, ordered to disordered. That means disorderness is increasing, entropy is increasing. So delta S sign has to be positive, right? Now, on the reactant side, you have got gases. On the product side, you have got solid. On the reactant side, you have got gases. On the product side, you have got solid. So gas is getting converted into solid. If gases are getting converted into solid, gases have got more randomness. Solid, less randomness, less disorderness. So more disorderness towards less disorderness. That means during the process, disorderness is decreasing. Entropy is decreasing. If entropy is decreasing, delta S sign has to be negative. I hope all these things are absolutely clear to you. Yeah? Now, my dear students, you must be thinking, what happens to entropy of the egg when it is boiled? Right? When we boil an egg, what happens to its entropy? Quickly. My dear students, for example, I have got an egg over here and it's in liquid state. Now, what exactly I'm going to do? I'm going to heat it up. When I heat it up, this egg gets converted into solid. So basically, liquid is getting converted into solid. If liquid is getting converted into solid, more disorder to less disorder, right? More disorder to less disorder. That means disorderness is decreasing. Entropy should decrease, right? Entropy should decrease, but it is not happening. Entropy increases during this process. During the boiling of egg, entropy of the egg increases. Well, you know, if you talk about the egg, what is egg basically? It's a protein. What happens when you boil the protein? What happens when you heat the protein up? First of all, when you heat the protein up, the protein unfolds. When you heat it up, the protein unfolds, then refolds, and becomes a tangled structure. Right? That means, is the overall structure becoming complex during the process? During the process, I will say, overall, structure is becoming complex. And more the complexity of the structure, as I told you already, more is going to be the entropy. So during the process, the complexity of the structure is increasing. What does that mean? That means entropy will be increasing during the process. So during this process, entropy is increasing, so delta S sign has to be positive. Correct? When you heat the protein, first of all, it The protein unfolds, then refolds, then becomes the tangled structure. So the complexity overall gets increased, due to which I'll say the disorderness gets increased. And if the disorderness increases, that means the entropy of the system increases. Yeah? All right, if I ask you, what happens to the entropy when you stretch the rubber? When you stretch the rubber, does the entropy increase or decrease? When you stretch the rubber, does the entropy increase or decrease? What do you think? What do you think? For example, on this side, I have got unstretched rubber. I'm taking unstretched rubber. Now I'm going to stretch it. So it becomes stretched rubber. It becomes afterwards stretched rubber. What will be the structure of the unstretched rubber? It will be a coil structure in the form of a coil. This is the structure of your unstretched rubber. When you stretch it, these coils, they get converted into linear shape. They attain the linear shape basically. Now you tell me which structure is complex, coiled or linear? This particular structure is complex. And if this particular structure is complex, more complex the structure, more the disorderness, more the entropy. So on this side entropy is more, on this side entropy is less. So when this process is happening, is the entropy increasing or decreasing? More entropy to less entropy. So I would say entropy of the system decreases. Therefore, delta S sign has to be negative. I hope this is clear to everyone. Yeah? Perfect. Perfect, guys. You have to remember all these things, right? Now, my dear students, there are few important characteristics of entropy which you need to know. Few important characteristics of entropy. The first one. If I talk about entropy, entropy is an extensive property. It is an extensive property. That means when you change the amount of substance present in the system, when you change the amount of substance present in the system, entropy of the system changes, right? Disorderness will change. Of course, when you change the amount of substance in the system, right? Disorderness will change, randomness will change. It will increase, decrease, whatever, right? So I would say entropy, it is that property whose value changes on changing the amount of substance present in the system. So it has to be extensive property. Now it is a state function as well. Entropy is a state function as well. So if you need to calculate change in entropy, how do you calculate it? Final entropy of the system minus initial entropy of the system. For any cyclic process, delta S has to be 0 because entropy is a state function, right? And change in the value of state function for a cyclic process, that always has to be 0. So delta S for the cyclic process, that will be always 0. I hope this is something which is clear to you, right? Right, people? Is it clear till here? All right. Now let me tell you one important thing. If I talk about universe, what is universe made up of basically? Universe is made up of system and surroundings, right? Universe is made up of system and surroundings. For example, if I ask you to calculate the total change in universe, total change in universe is represented by delta ST. Delta S total, it represents the total entropy change in the universe. Whatever will be the entropy change of the universe, that will be due to the entropy change of the system and due to the entropy change of surroundings. So first of all, we will have to calculate the entropy change of the system. Then we have to calculate the entropy change of the surroundings. We need to add them up, and eventually after adding them up, I'll be getting the total entropy change of the universe. So do remember this. These are the three questions which are asked basically. Calculate the entropy change of the system, calculate the entropy change of the surroundings, calculate the total entropy change of the universe, right? Universe is made up of system and surroundings. So whatever will be the entropy change in the universe, that will be due to the entropy change of the system and at the same time, the entropy change due to surroundings. Perfect. So we need to calculate the entropy change of the system first. Then we need to calculate entropy change of the surroundings. We need to add them up and we'll be getting the total entropy change of the universe. I'm telling you everything in a nutshell. You just have to remember all these, you can solve all the questions. Now, where do we use this particular concept? This is important, guys. This particular statement is important. Why is it important? You'll get the idea in some time. Okay, one more thing. Before dealing with this statement, there is one more thing. My dear students, how do you define the entropy change mathematically? How do we define the entropy change mathematically? For example, imagine that this is the container. It contains the ideal gas. It contains the ideal gas, okay? For example, I'm supplying dq amount of heat reversibly to this gas. This dq reversible is, for example, the amount of heat which is supplied to the system when the system is at temperature T. The system is at temperature T, right? This dq reversible I'm supplying to the gas. But do remember, whatever heat I'm supplying, it does not change the temperature of the gas. Whatever heat I'm supplying to the gas, it does not change the temperature of the gas. It is just used, for example, to change the randomness of the system, to change the disorderness of the system. So if I'm supplying heat to the system, there will be entropy change of the system. And that entropy change is represented by ds. And as per mathematical definition, it is always equal to dq reversible divided by T. dq reversible is the amount of heat absorbed or released by the gas reversibly when the gas is kept at a temperature T. This is the mathematical definition of what? Of entropy change. This is how you calculate small change in entropy. If I ask you how do we calculate the total change in entropy, you just need to integrate. Integration of dq reversible divided by T, right? This is how you calculate the total entropy change basically. Total entropy change. If you ask me what are going to be the units of this entropy, units of entropy, see in the numerator it's heat, in the denominator it's temperature. So one of the units can be joules per Kelvin, joules per degree centigrade, joules per whatever, right? Calories per degree centigrade, calories per Kelvin. You can use many units over here, right people? Yeah. Do remember, this is the gas which I took in the container. I'm supplying dq amount of heat to the gas. But the heat which I'm supplying to the gas, I'm supplying it in such a way that the temperature of the gas does not change. Only the heat which I'm supplying, it is just utilized to increase the randomness of the system. So if I need to calculate, due to the supplication, since I'm supplying heat, due to this heat supplying, what is going to happen? The disorderness will increase, right? So entropy will increase basically. And that change in entropy is represented by ds, which is calculated like this, dq reversible upon T, right? So total entropy change, you just have to integrate it. I hope this is clear to everyone. Now people, try to understand a few more things. See, there is something called as spontaneous, non-spontaneous process. Do you know what are spontaneous and non-spontaneous processes? What is a spontaneous process basically? That process which happens on its own. Number one, that process which takes place on its own, or just needs the initiation, That's something which you call as spontaneous, otherwise non-spontaneous. What it means and why am I telling you this right now? Before that, let's try to understand what a spontaneous process is. Any such process which happens on its own, which occurs on its own. For example, this is the object whose temperature is 100 Kelvin. This is one more object whose temperature is 1000 Kelvin, right? Now, for example, if I bring them in contact, what will happen? If I bring these two in contact, what is going to happen? Since there is temperature difference, due to temperature difference, heat will automatically flow from higher temperature to lower temperature. So flow of heat, it is happening on its own, right? Any such process which happens on its own, that's what you call as that's what we call a spontaneous process. For example, flow of heat, right? Flow of heat, it happens on its own. It is a spontaneous process, right? Burning of kerosene. If I define the process, burning of kerosene. My dear students, you have kerosene, for example, right? You just need to give it a flame, right? If you give flame to kerosene, it will automatically burn. So you are just initiating the process. Rest, everything is happening on its own. You're just initiating the process. Rest, everything is happening on its own. So this one is completely happening on its own. This process, it just needs to, we need to initiate the process. Rest, it will happen on its own. And any such process, which either completely happens on its own or needs a proper initiation, right? That's what we call as spontaneous process. Perfect. Now, my dear students, the point is very simple. See what the point is. If entropy is the only criteria, if entropy is the only criteria to check whether the process is spontaneous or not, what do we do at that point of time? If entropy is the only criteria, if entropy is the only criteria to decide whether the process is spontaneous or not, then, my dear students, you have to remember a few things. Do remember, if delta is total, which is the entropy change of the universe, if delta is total due to the process, if it comes out be positive, then we say the process is spontaneous and irreversible. Second point, if delta is total comes out being negative, we say the process is non-spontaneous. And at the same time, if delta is total comes out be 0, we say the process, it is reversible, or you can say system and surroundings are at equilibrium. System and surroundings are at equilibrium. You can say something like this as well. So do remember, if entropy is the criteria to check whether the process is spontaneous or not, you have to calculate delta as total. Change in the entropy of the universe. If it comes out be positive, the process is spontaneous. If it comes out be negative, non-spontaneous. If it comes out be 0, that means it is reversible, or you can say the system and surroundings that are at equilibrium. So these are the 3 conditions which I would want all of you to remember from now on, right? So for reversible processes, delta as total will be 0. For irreversible processes, delta as total is greater than 0. Do remember this particular thing as well. Yeah. Now, guys, entropy, it's not done yet. We have to discuss a few more things about entropy. What is that? Have a look. I'm marking the heading as entropy change. Entropy change when an ideal gas undergoes a change in state. Entropy change when an ideal gas undergoes a change in state. What does it mean? Have a look. For example, you have got ideal gas in the container. Let's say the ideal gas is undergoing expansion. Ideal gas is undergoing compression. Ideal gas is simply undergoing a change in state. During the change in the state, entropy of the gas will change. Now, how do we calculate the change in the entropy of the ideal gas when it undergoes a change in state? That is our topic, basically. Try to understand how exactly I'm going to get the result over here. This is important. This is important. Try to understand this. For example, this is the gas in the container. This is the ideal gas in the container, for example, right? Let's say we are supplying dq amount of heat reversibly to this gas, which is at temperature T. Since we are supplying dq amount of heat to the gas, there will be entropy change of the gas. That entropy change of the gas I'm representing with ds. So ds has to be equal to dq reversible upon temperature, right? Perfect. Now, my dear students, for example, what exactly I'm doing? For example, I have got a gas. This is the gas over here. This is the ideal gas over here. Perfect. For example, the initial volume of the ideal gas is V1. The final volume of the ideal gas is V2. The initial temperature of the ideal gas is T1. The final temperature of the ideal gas is T2. Let's see exactly after changing these parameters, what would have happened to the entropy of the gas, right? Let's get to know on changing the volume, on changing the temperature, right? What happens to the entropy of the gas? So let's try to understand. First of all, we need to calculate the total entropy change of the gas, which undergoes a change in state. So basically, we need to calculate the value of delta S, which is integral dq reversible upon T. Right? We need to calculate the total change in the entropy of the gas, which is undergoing a change in state, whose volume is changing from V1 to V2, whose temperature is, for example, changing from T1 to T2. Now, if I ask you, as per first law of thermodynamics, delta U is equal to Q plus W. So du is equal to dq plus dw. So from this, can't you calculate dq? dq has to be equal to du minus dw. So my dear students, in place of dq, what I'll be writing? In place of dq, I'll be writing du minus dw. Divided by what? Divided by temperature. So I'll say delta S is equal to integral. What is du? Small change in internal energy for the ideal gas. So du is nothing, it is NCV dt divided by temperature. There is a sign minus in between, right? There is a sign minus in between. Integral of. What is dw? dw is minus pdv, minus plus. It is pdv divided by temperature. Something like this. Perfect. Now here you are integrating with respect to temperature. Temperature is changing from T1 to T2. Here you are integrating with respect to volume, right? And volume of the gas is changing from V1 to V2. Correct till here? I hope till here it's clear. Now try to understand what exactly I'm going to say. Just a second. Try to understand what exactly I'm going to say. Right? First of all, dear students, understand properly what I am going to say. I'll write delta S is equal to N I'll take out, CV I'll take out. Integral of dt by t. First of all, it's going to be N CV. Integral of dt by t. It's ln of t. Upper limit, lower limit. So it's going to be ln of T2 divided by T1. In the middle, the sign is positive, right? Now over here, you have got P by T. You know, PV is equal to nRT. PV is equal to nRT. So can I say P divided by T is equal to nR by V? Absolutely, P by T is equal to nR by V. And over here, you have got P by T. So instead of P by T, what you can write? Instead of P by T, you can write nR divided by V, and dV is already there. Yeah. So over here, I'll be getting the final result, which I would want you guys to remember. This NCV ln of T2 divided by T1 plus nR will come out because constant both. Integral of dy by V is ln of V. So upper limit, lower limit. So ln of V2 divided by V1. So my dear students, this is the first expression which I would want you guys to remember. First expression which I would want you guys to remember to calculate the entropy change of the ideal gas which undergoes a change in state. Yeah. This is how you calculate entropy change of the gas, of the ideal gas, which undergoes a change in state. Okay. This is the first expression. Similarly, the second expression. Understand the second expression. My dear students, in states of matter, I had given you one equation, combined gas equation. P1 V1 divided by P2 V2 is equal to N1 T1 divided by N2 T2. Since, if you remember a few minutes back, I took a container in which a gas was present, right? Was there any leakage or something? There was no leakage or something, right? Was I introducing some extra gas in the container? No. So number of moles of the gas were fixed. If the number of moles are fixed, if the number of moles are constant, so remove N1 and N2. So I'll be getting P1 V1 divided by P2 V2 is equal to T1 divided by T2. Perfect. So I'll be getting something like this. P1 divided by P2 multiplied by T2 divided by T1 is equal to V2 divided by V1. Do you agree with this? Right? V2 here, V1 here. So V2 by V1 is this value. And in this particular expression, do you see you have got V2 by V1 here? So instead of V2 by V1, I'm going to introduce few more terms. So delta S gas has to be equal to N CV ln of T2 divided by T1 plus NR ln of, instead of V2 by V1, I'll be writing P1 by P2 multiplied by T2 divided by T1. I hope this is clear. I hope this is clear to you. I hope this part is clear. Yeah. All right. Now it's just a matter of calculation. So I'll say delta S for the gas is equal to NCV ln of T2 divided by T1 plus NR. It is ln of M into N. Ln of M into N, which is ln of M plus ln of N. Perfect. Now, dear students, one more thing which you can do. Say ln of T2 by T1, ln of T2 by T1. You can take common. You can take n common. So delta is gas. Delta is gas is equal. N you have taken common. Ln of T2 by T1 you have taken common. Over here you have got CV, over here you have got R. So CV plus R comes out to be CP. So it's NCP ln of T2 divided by T1 plus NR ln of P1 divided by P2. So this is one more equation which I would want every one of you to remember to calculate the entropy change of the ideal gas which undergoes a change in state. So these are the two expressions which I would want every one of you to remember. NCV ln T2 by T1 plus NR ln V2 by V1. NCP ln T2 by T1 plus NR ln P1 by P2. Right? Now, my dear students, where do we use these expressions? Have a look. For example, an ideal gas. Let's say you have got an ideal gas undergoing isothermal process. If you have got an ideal gas undergoing isothermal process, how do we calculate its entropy change? Entropy change of the ideal gas, which is undergoing isothermal process. In case of isothermal process, temperature is constant. If temperature is constant, T1 will be equal to T2. If T1 is equal to T2, this term becomes 1. Ln of 1 is 0. So this whole term becomes 0. So the formula will be NR ln of V2 by V1. NR ln of V2 divided by V1. So whenever an ideal gas undergoes an isothermal process, this is how you calculate entropy change of the ideal gas. Point number 1. Yeah. Point number 1. Right. Now, my dear students, whenever an ideal gas undergoes isochoric process. Okay, one more result. Wait, one more result. In isothermal, one more result. Isothermal temperature is constant. T1, T2 is same. So this gets cancelled out. Ln of 1 is 0. Right? This term is 0. It can be NR ln of P1 by P2. It can be NR ln of P1 divided by P2. Correct? These are the two expressions which you can remember to calculate entropy change of the gas which undergoes isothermal process. Now, if the ideal gas undergoes isochoric process, so volume is constant, V1 is equal to V2. If V1 is equal to V2, gets cancelled out, ln of 1 is 0, this term is 0, so it's going to be NCV ln T2 by T1. NCV ln T2 divided by T1. This is your delta S gas. When the gas undergoes what? When the gas undergoes isochoric process. Yeah, when the gas undergoes isochoric process. Perfect. When the gas undergoes isochoric process. Now, similarly, if the gas undergoes isobaric process, if the ideal gas undergoes isobaric process, that means pressure is constant. If pressure is constant, that means P1, P2 are same. So this term becomes 0. Finally, it's going to be NCP ln T2 by T1. NCP ln of T2 divided by T1. This is how you calculate entropy change of the gas, entropy change of the ideal gas, which undergoes isobaric process, right? Now, the point is, if the ideal gas undergoes adiabatic process, then you'll be using either this relation or this particular relation completely to calculate the delta S for the ideal gas, which is undergoing adiabatic process, right? Perfect till here? Is this clear till here, people? Quickly. These two results are used for adiabatic process as well. These are the general expressions, okay, which you can utilize for adiabatic processes. I hope all these things are clear. And if all these things are clear, let's try to solve few questions so that it becomes absolutely clear to you. Okay, this is the first question. Try to understand what the question says. 1 mole of ideal monoatomic gas. You have got 1 mole of ideal gas which is monoatomic in nature. So CV is equal to 3 by 2R. That means CP will be equal to 5 by 2R. So 1 mole of ideal monoatomic gas was taken through isochoric heating. So the ideal gas is undergoing isochoric process. Ideal gas is undergoing isochoric process from 100 Kelvin to 1000 Kelvin. Initial temperature of the gas is 100 Kelvin and final temperature of the gas is 1000 Kelvin. Calculate delta S system, delta S surrounding and delta S total if the process is carried out reversibly. Few minutes back I told you, if you remember, delta S total in case of reversible process, that is 0. Delta S total for a reversible process, that is 0. If delta S total is 0, that means delta S system plus delta S surrounding. Delta S system plus delta S surrounding, that has to be 0. So what does that mean? That means delta S system has to be equal to minus times delta S surrounding. Perfect. Delta S system has to be equal to minus times delta S surrounding. See, delta S total you have calculated. Now calculate delta S system. Delta S system means delta S gas. Delta S gas, which undergoes isochoric process. In case of isochoric processes, when the ideal gas undergoes isochoric process, what is the formula? NCV ln T2 by T1. NCV ln T2 by T1. So it's NCV ln of T2 divided by T1. N value is 1. CV value is 3 by 2 R. Let's say we have to calculate everything in calories. So put the value of R as 2. NCV 3 by 2 R. Ln of T2 by T1. 1000 by 100 is 10. Right? And ln of 10 is 2.303. So this got cancelled. So 3 multiplied by 2.303, which comes out to be 6.909. It's going to be calories per Kelvin. So this is the entropy change of the system. This is delta S system, this is delta S gas. If delta S system you calculated, so delta S surrounding. Delta S surrounding has to be equal to minus times 6.909 calories per Kelvin. Delta S system you calculated, delta S surrounding you calculated, and delta S total will be automatically 0, right? This plus this will come out to be 0. It is just their sign is different. Let me know once in the chats if it's clear. Let me know once in the chats if it's clear, quickly. Okay, let's try out one more question. This is one more question. The question is 1 mole of an ideal gas, 1 mole of an ideal gas, which is diatomic in nature. So CV is equal to 5 by 2R, CP is equal to 7 by 2R. So 1 mole of ideal diatomic gas was heated at constant pressure of 1 atm. Was heated at constant pressure of 1 atm to double its temperature. So initial temperature is, for example, T. The final temperature of the gas is 2 times T. Okay. At constant pressure means the process is isobaric in nature. We are heating the ideal gas at constant pressure. If the temperature of the gas initially was 27 degrees centigrade, okay, initial temperature is given as 300 Kelvin. What does that mean? Final temperature will be equal to 600 Kelvin because you are doubling the temperature. Calculate delta S system, delta S surrounding, delta S total, if the process is carried out reversibly, right? Since, dear students, it's again the reversible process. In case of reversible processes, delta S total has to be 0. In case of reversible processes, delta S total has to be 0. What does that mean? That means delta S system, which is basically delta S gas, will be equal to minus times delta S surroundings, right? So delta S system has to be equal to minus times delta S surroundings. Now calculate delta S for the gas which undergoes. Delta S for the system, delta S for the gas, which undergoes isobaric process. What is the formula we use in case of isobaric processes? In case of isobaric processes, this is the formula which we use. NCP ln of T2 by T1. NCP ln of T2 by T1. So NCP ln of T2 divided by T1. Now what is the value of N? That's 1. CP value. CP value, that's 7 by 2R. 7 by 2, take the R value in calories, right? Ln of T2 divided by T1. T2 is 600, T1 is 300. So 600 divided by 300 comes out to be 2, right? Which can be mentioned as 7 ln 2, right? Ln 2 is approximately 0.7. So it comes out to be 4.9 calories per Kelvin. So this is the value of delta S for the gas, which is undergoing isobaric process, which is undergoing reversible isobaric process. Now, what about delta S surroundings? Delta S surroundings has to be equal to minus times delta S system. So it's minus times 4.9 calories per Kelvin, right? This is how you calculate delta S surroundings over here. And my dear students, one thing, I'm only calculating for the reversible process. In your NEET, they do not ask you for the irreversible processes. That's for JE basically, right? For JE, the questions about entropy, they become comparatively difficult when you have to do the entropy calculation for surroundings, for irreversible process, right? That becomes comparatively difficult. But in your NEET, they'll be only asking you about the reversible process, not the irreversible ones, right? Perfect. Someone is asking, sir, how to calculate CV? Wow, I think you're very late. Go and watch the first 2 sessions of thermodynamics. Perfect, guys. Now, there is one more topic related to entropy. What is that? That is entropy change. Entropy change during reversible. Entropy change during reversible heating or cooling. Entropy change during reversible heating or cooling of a solid or a liquid. Of a solid or liquid. This is one more topic related to entropy, and this is simple, right? It's not that lengthy also. See what exactly it means. See what exactly it means. Understand? My dear students, for example, imagine that this is the solid which we have. XS. This X is a solid. Okay? This X is a solid. I'm supplying some heat to the solid. For example, I'm supplying this much of heat. dQ, reversible amount of heat to the solid. Right? Initially, the temperature of the solid is T1. Finally, the temperature of the solid is T2. What am I doing? I'm supplying heat to the solid. Right? But I'm supplying heat to the solid. Okay? But making sure that the state of the substance is not changing. Only the temperature of the substance is changing. I'm supplying, for example, heat to the solid. Okay? Due to which the temperature of this solid is changing. Perfect. Now, since we are supplying heat to the solid, whose temperature is changing from T1 to T2, its entropy will automatically change. How do we calculate that change in entropy? You know it. How do we calculate that change in entropy? Entropy change is generally calculated like this. Integral of dQ reversible upon T. This is the general expression, if you remember. This is the general expression. And my dear students, we are increasing the temperature. We are changing the temperature from T1 to T2. This is the general expression which you'll be using. Right? Now, there are many ways by means of which we can calculate dQ. I have told everything in detail, if you remember. If heat capacity is given, then dQ is equal to C dt. If specific heat capacity is given, then dQ is equal to ms dt. If CV is given, then it's ncv dt. If Cp is given, then dQ is equal to ncp dt. Right? Now, as per question, you just have to place the value of dQ. If in the question they are given with the heat capacity, then instead of dQ, you have to write C dt. Right? Mentioning that if T is given, if heat capacity of the substance is given, perfect, then delta S for the substance has to be equal to integral from T1 to T2. dQ is going to be C dt divided by T, right? By chance, if specific heat capacity of the solid is given, whose temperature you are changing from T1 to T2, then delta S has to be equal to integral T1 to T2. It's going to be ms dt divided by T, right? Similarly, for example, if molar heat capacity at constant volume for the substance is given, then delta S has to be equal to integral T1 to T2. It's going to be n Cv dt divided by T. Similarly, delta S has to be equal to n Cp dt divided by T. So basically, depending on what are the parameters that are given to us as per the question. If C is given, use this particular result. If S is given, use this particular result. If Cv is given, use this particular result. Right? Perfect. But do remember, this is basically how we calculate entropy change of a solid or a liquid whose temperature we are changing from T1 to T2, irrespective of changing their state. Right? All these things are valid for liquid as well. For example, you have got X liquid. You are supplying some heat. It is becoming X liquid only. Only its temperature is changing from T1 to T2. You can use all this procedure for this particular substance as well. Yeah? Let's try to solve one question from this so that we'll get the idea. What kind of question can be asked from this one? Have a look. Understand. For a 1 mole of perfectly crystalline solid. So you have got, for example, 1 mole of X, which is perfectly crystalline solid. Right? For a 1 mole of perfectly crystalline solid, Cp is equal to 80, where A is this. If Cp is equal to 4.2 kilojoules at 10 Kelvin, then calculate the change in entropy when it's heated from 10 Kelvin to 20 Kelvin. So basically, as per question, initial temperature of the solid is 10 Kelvin. Now you are heating it up. You are heating it up. Its temperature now is becoming 20 Kelvin. So you are changing the temperature of the solid from 10 Kelvin to 20 Kelvin. There will be definitely The change in its entropy, right? There will be definitely change in its entropy. So that change in entropy we have to calculate, which has to be integral T1 to T2. dq by dt. dq by dt. Check what is given. Cp is given. So instead of dq, you'll be writing ncp dt divided by t. This is the formula which you have to use. This is the formula which you have to use, number one. Number two, as per the question, it's mentioned that Cp is equal to A times capital T, right? Where A is a constant. And it's mentioned that Cp value is 4.2 when temperature is 10 Kelvin. Cp value is 4.2 when temperature is 10 Kelvin. So you can calculate A from here. So A is coming out to be 0.42. So you calculate A, right? So dear students, the question is almost done. It's from 10 to 20. Number of moles is 1. 1 mole of gas is given. Cp value is given to us as A times capital T. So this is dt divided by T. So T and T got cancelled. So it's going to be integral from 10 to 20, right? A will come out, right? dt will remain as such. So it's going to be A times integral of dt is T, upper limit, lower limit, right? So it's going to be 20 minus 10. Now A value is 0.42 multiplied by 10. So the value has to be 4.2 joules per Kelvin. This is the value of delta S. Correct? Is this question solved? Done and dusted? Simple. Whatever results I'm giving you, I'm utilizing all these results. That's it. Nothing else. I'm doing nothing new here. I'm doing nothing new here. I'm doing nothing new here. Just let me know once in the chats if every single thing is clear to them. Yeah? It is just for solids and liquids we use the integral. When we talk about the gas, when the gas is undergoing expansion, compression, or when the gas is undergoing a change in state, then direct results which I gave you, those 3-4 results for isothermal, isobaric, adiabatic, etc. Yeah? Perfect. And all those results which we gave, which we derived them by doing integration only, right? Let me know once in the chats if all the things are clear till here. The last topic of the chapter, that's Gibbs free energy. It's again one of the important topics. Okay? And it's a bit lengthy as well, but we'll be starting exactly from basics itself. Yeah? Gibbs free energy. Gibbs free energy, or you can call it as Gibbs function, which is denoted by capital G. Gibbs function, Gibbs free energy, which is denoted by capital G. My dear students, first of all, what was the need to introduce this G? What is the need to introduce this new function? Why is that? A few minutes back, I told you, in order to check whether a process is spontaneous or not, what do we have to do? We have to calculate the value of delta ST. If the delta S total is greater than 0, that means the process is spontaneous. What is delta S total? It's delta S system plus delta S surroundings. This has to be greater than 0. Then only I can say the process is spontaneous, right? If entropy is the criteria for spontaneity, then we have to calculate delta S system first. Then we have to calculate delta S surrounding also. Then we have to sum them. We have to add them. If the sum comes out to be greater than 0, then only we can say the process is spontaneous, right? But my dear students, if I keep Gibbs free energy as the criteria for spontaneity, you have got nothing to do with the surroundings. You just have to do the calculation of system. You just have to do the calculations related to system. So over here, if entropy is the criteria for spontaneity, then you have to calculate delta S system, then delta S surrounding, then add them up. Then you can say whether the process is spontaneous or not. So basically, calculations are lengthy here. First delta S system, then delta S surrounding, then add them up, right? So the calculations are lengthy. So in order to reduce these calculations, a new function was introduced, which is what you call as Gibbs function. Which is denoted by G. And G is equal to H minus Ts. H is enthalpy, T is temperature, S is entropy. G is equal to H minus Ts. If you remember, the way we introduced H. H was U plus PV. U plus PV we called as H. And similarly, H minus TS will be directly calling as H minus TS will be calling as G, Gibbs function. Right? So by introducing the Gibbs function, what happens? You have got nothing to do with the surroundings now. If you want to check whether the process is spontaneous or not, you just have to calculate change in the Gibbs free energy of the system. That's all. How exactly you'll get to know in some time. Just wait for it. See, first of all, G is equal to H minus TS, right? So if I multiply throughout by D, it is dG is equal to dH minus d of Ts, right? So you can write it as dG is equal to dH minus, it is TdS minus S dt. If I write the same equation at constant temperature, at constant temperature, change in temperature will be 0. So dG has to be equal to dH minus T ds. Because dt is 0, so this term becomes 0. Perfect. So just integrate all. If you integrate all, it becomes delta G is equal to delta H minus T delta S. This is the equation, first of all, which I would want every one of you to remember for the calculation of delta G. Change in the Gibbs free energy is always equal to delta H, enthalpy change, minus temperature multiplied by delta S, entropy change. This is the first equation which I would want you guys to remember, right? Number one. Number two. This Gibbs function gives free energy. What about its physical significance? What kind of idea it gives us? You'll get the idea in some time. But before that, there is something important. This G is an extensive property. Gibbs free energy, it's extensive property. It's a state function as well. For a cyclic process, change in the value of Gibbs free energy will be 0. For the cyclic process, change in the value of Gibbs free energy, that will be 0. Right? Now comes the point. If Gibbs free energy is the criteria for spontaneity, then do remember, for the process to be spontaneous, delta G for the system at constant pressure and temperature, it has to be negative. Then only I can say the process is spontaneous. Similarly, if delta G for the system at constant pressure and temperature comes out to be greater than 0, we'll be saying the process non-spontaneous. And similarly, if delta G for the system at constant pressure and temperature, if it comes out to be 0, then you will say system and surroundings, they are at equilibrium. So my dear students, understand one thing. If entropy was the criteria for spontaneity, you were supposed to calculate delta S system, then delta S surrounding. But if Gibbs free energy is the criteria of spontaneity, you just have to calculate delta G for the system. By just calculating the delta G for the system, you can check whether the process is spontaneous or not. You do not have to calculate delta G for the surroundings, unlike entropy. Right? In case of entropy, we are supposed to calculate delta S surrounding as well. But here, we just have to calculate delta G for the system at constant pressure and temperature. If you get the delta G for the system at constant pressure and temperature by just having a look at their values, you can get to know whether the process is spontaneous or not. Yeah? Okay, so do remember these three cases. These are really very important. Before talking about the significance of this Gibbs function, before talking about the significance of Gibbs free energy, what is it exactly? Before talking about that, let me give you a few more things. See, I told you delta G is equal to delta H minus T delta S. Correct? This is something which I told you. Delta G is equal to delta H minus T delta S. Now guys, over here I'm mentioning delta H. Right here I'm mentioning delta S. Right here I'm mentioning delta G. Okay? For example, the first case. If you have got a process whose delta H is coming out to be negative, any process whose delta H is negative, delta S is positive. For example, you have got any process whose delta H is negative, delta S is positive. This term is negative. This term is positive. Positive negative is negative. So the overall sign of delta G will come out to be negative. And when delta G comes out to be negative, we'll say the process is spontaneous. It is spontaneous at all temperatures. At all temperatures. Perfect. So basically what it means, delta H negative means exothermic. Energy is released. Energy is released. So during the process, energy is released. The system is going towards low energy. If the energy is released during the process, energy possessed by the system is decreased with time, right? And you know, as far as the energy factor is concerned, system always tries to go in that direction in which the energy decreases, right? Let me write these two statements first of all. System tries to move in a direction in which energy decreases and entropy increases. System always tries to move in a direction in which energy decreases and entropy increases. Now guys, delta H is negative, so energy is released. If energy is released by the system, energy possessed by the system decreases with time. So energy is being decreased. Now similarly, delta S is positive, so entropy of the system is increasing. So energy of the system is decreasing, entropy of the system is increasing. So both the things are favorable here. Both the things are favorable. So automatically the process is going to be spontaneous, right? If you have got a process A to B, let's say we have to check whether this process is spontaneous or not. If during this process energy of the system is decreasing, entropy of the system is increasing, then only you can say the process will happen. Then only you can say the process will happen. The process will be spontaneous, whose delta G will be negative. Anyways, leave that part aside. Not going to talk about it in detail. Second thing, I'm just going to tell you the things which are needed, right, for the question solving. Second thing, if for example, delta H is positive, if for example, delta H is positive and delta S is negative, if this term is positive and this term is negative, negative makes it positive, and over here it was already positive. So this whole term, delta G, is coming out to be positive. And you know, when delta G is positive, I'll say the process will be non-spontaneous under all conditions. Non-spontaneous at all temperature. Okay. Now guys, third case. If for example, delta H is negative, if delta H is negative and delta S is also negative, delta H is negative, delta S is negative, negative is positive. So this term is negative. In the middle, you have got positive. This term is for example negative. In the middle, it's coming out to be positive. So when can be the overall delta G negative? Overall delta G can be only negative if the magnitude of delta H will be greater than that of magnitude of T delta S, which is only possible at low temperatures. At low temperatures. So I would say any such process whose delta H is negative, delta S is negative, the process will be only spontaneous at low temperatures. Okay. Similarly, the fourth case. For example, the first thing is positive and second thing, delta S is also positive. Delta H is positive, right? Delta S is also positive. This is positive, this is positive. Positive, negative is negative. So the overall term, when it will come out to be negative, the overall term delta G will come out to be negative only if the magnitude of T delta S is greater than that of magnitude of delta H, which is only possible at high temperatures. So I must say any such process whose delta H is positive, delta S is positive, the delta H value will only come out to be negative. The process will be only spontaneous at higher temperatures. That's all what you have to remember. That's all what you have to remember. I hope this is clear to everyone, right? I hope this is clear to everyone. My dear students, for example, I'm giving you one small question out of it. Let me see if you can solve this or not. A small question like this. Let's say you have got a process A gives B. Delta H is, for example, minus 80 kilojoules. Delta H is, for example, minus 80 kilojoules. And delta S is, for example, 2 times capital T, joules per Kelvin per mole. We have to check the temperature at which the process will be spontaneous. Calculate the temperature at which the process will be spontaneous. At what temperature the process will be spontaneous? What is the criteria for spontaneity? For the process to be spontaneous, delta G for the system at constant pressure and temperature, it has to be negative. So delta H minus T delta S, this has to be negative, right? What is delta H? Minus 80 kilojoules. So minus 80,000 joules, less than. This T delta S will come on that side. It's T, delta S value is 2 times capital T. Perfect. So what I can say? What I can say over here, just a second. This minus, just a second. So make it positive. Make it positive. So this is plus 80,000 less than. So 80,000 is coming out to be less than 2t square, or you can say 2t square is greater than 80,000, or you can say t square is greater than 40,000, or I can say t is greater than 200 Kelvin. So what is meant by this particular thing? What is meant by this particular thing? Check it out. I gave you one process whose delta H is given, whose delta S is given. I'm telling you to calculate, I'm asking you to calculate the temperature at which the process will be spontaneous. For the process to be spontaneous, delta G for the system at constant pressure and temperature, it has to be negative. So delta H minus T delta S, it has to be negative. When you do the calculation, finally you are getting temperature should be greater than 200 Kelvin. So temperature has to be greater than 200 Kelvin, then only the process will be spontaneous, right? Is this clear to everyone? Is this clear to everyone quickly? We are going to do a few more questions about this, but before that, we have to talk about a few more concepts related to Gibbs free energy so that you can get to know about its physical significance. And before talking about the physical significance, there is one thing which I forgot to tell you related to entropy. What is that? There is one thing which I forgot to tell you related to entropy. So let me just finish that statement. What is that? Have a look. I'm mentioning, first of all, entropy change during the reaction. How do you calculate the entropy change during a reaction? It's a very simple thing. Entropy change during the reaction. Then I'll move to the Gibbs free energy again. Okay, this is something which I skipped in between. I forgot this. For example, you have got the reaction N1A plus N2B. Let's say it gives N3C plus N4D. This is the reaction, for example. I want you guys to calculate the entropy change during the reaction. Entropy change during the reaction is nothing. It is entropy of product minus entropy of reactant. And how you guys are going to write it? Entropy of product. This is my product, this is my product. Stoichiometric coefficient of C is N3. N3 multiplied by entropy of C plus N4 multiplied by entropy of D. So this is your overall entropy of products minus entropy of reactants. Entropy of reactants. Stoichiometric coefficient is N1. N1 multiplied by entropy of A plus N2 multiplied by entropy of B. In the question, if they give you entropy of C, entropy of D, entropy of A, entropy of B, you can easily calculate entropy change of the reaction. Yeah? You can calculate entropy change for the reaction. Perfect? So do remember this particular thing by means of which you can calculate entropy change of the reaction. Perfect? Even you can calculate entropy change under standard conditions as well. Sometimes they'll give you the entropy of A, B, C, D under standard conditions, and they'll ask you to calculate the standard entropy change of the reaction. You can write this in this way. That's all. Okay? You'll see its application as well, but in some time. So what we were discussing basically, we were discussing about Gibbs free energy, right? We were discussing about Gibbs free energy. Now, just a second. Okay. Let's talk about this particular equation. Let's talk about this particular equation. The molar entropy of X2, Y2 and XY3 are 60, 40 and 50 for the reaction this, whose delta H is given. The process will be spontaneous at. For the process to be spontaneous, delta G for the system at constant pressure and temperature has to be less than 0. So delta H minus T delta S has to be less than 0. So delta H has to be less than T delta S. Or I'll say T delta S has to be greater than delta H. Or I'll say temperature should be greater than delta H upon delta S. Temperature should be greater than delta H upon delta S, right? Now, is delta H for the reaction given? Absolutely it's given. But delta S for the reaction is not given. Delta S for the reaction is not given. So let's calculate delta S for the reaction. Entropy of product. So it's 1 multiplied by entropy of XY3 minus entropy of reactant. So it's half of entropy of X2 plus 3 by 2 times entropy of Y2. So delta S for the reaction will be equal. What is the entropy of XY3? Entropy of XY3 is nothing, that's 50 minus. This is half of. Entropy of X2 is 60 plus 3 by 2 times. Entropy of Y2, that is 40. Correct? So entropy change of the reaction has to be equal to 50 minus, this will be 30 plus, this will be 60. So 90 minus 50 comes out to be minus 40. So minus 40 joules per Kelvin. This is the entropy change of the reaction. And we know temperature has to be greater than delta H upon delta S. Delta H is minus 30 kilojoules. So convert it into joules. So minus 30,000 joules. Minus 30,000 joules. Right? Divided by. Minus 30,000 joules divided by delta S. Delta S is minus 40 joules per Kelvin. So minus minus cancel. So temperature has to be greater than 750 Kelvin. Temperature has to be greater than 750 Kelvin. Then only we can say this particular process will be spontaneous. That's something which you were supposed to calculate. Tell me once in the chat if it's clear. Say yes or no in the chat quickly. Simple again. Yeah? Quickly, people. Is this clear? These sort of questions are frequently asked, right? At what temperature the process will be spontaneous, non-spontaneous, etc. So temperature has to be greater than 750 Kelvin, then only I can say the process is going to be spontaneous. Okay? Now, guys, there is one more thing which I would want to discuss with you first of all. What is that? That is, what is that? That is Gibbs free energy. Or let me write it like this. Calculation of delta G for the reaction from Gibbs free energy of formations of reactants and products. This is one more small topic which I would want to discuss with you. It's simple, guys. It's very simple. For example, you have got a reaction like this. N1A plus N2B, it gives N3C plus N4D. Now, for example, I'm asking you to calculate Gibbs free energy change for the reaction. You will say it is going to be equal to Gibbs free energy of formation of products minus Gibbs free energy of formation of reactant. How exactly you are going to write it? Gibbs free energy of formation of products. So these are your products. So start with N3. N3 multiplied by free energy of formation of C plus N4 multiplied by free energy of formation of D. So this is your free energy of formation of products minus free energy of formation of reactants. Reactant is your A and B. So first of all, start with Na. Free energy of formation of A plus N2 multiplied by free energy of formation of B, right? This is how you calculate the free energy change of the reaction, Gibbs free energy change of the reaction. Now, you can write it under standard conditions as well. Standard Gibbs free energy of the reaction is equal to standard free energy formation of C, standard free energy of formation of all these reactants and products, right? And do remember one simple thing. Standard Gibbs free energy of formation of an element which will be present in its standard state, that will be taken as 0. Standard free energy of formation of an element which will be present in its standard state, that will be taken as 0. What is standard state of an element? That state in which element exists in nature. Oxygen in nature exists in the form of O2 gas. Hydrogen exists in the form of H2 gas, right? Perfect. Iron exists in the form of Fe solid. Perfect. So these are the standard states of these elements. So if I write something like this, delta G naught formation of O2 gas. Is O2 gas the standard state of oxygen? Absolutely. So this value has to be 0. right? Similarly, for H2 gas, 0. For Fe solid, 0. And similarly, if you will be having any element which will be existing in the form of allotropes. So this is allotrop 1, this is allotrop 2. Allotrop 1, allotrop 2. That particular allotrop which will be thermodynamically more stable. For example, 2 is more stable than first. That particular allotrop which will be thermodynamically more stable, which will be considered as the standard state of the element. For example, if I talk about carbon, carbon has got two main allotrops. One is diamond and one is graphite. And thermodynamically, graphite is considered to be more stable. If graphite is considered to be more stable, that means if I write carbon like this, carbon graphite, this is going to be the standard state of carbon. And delta G naught for the formation of carbon graphite will be directly taken as 0. I hope this thing you will be remembering from now onwards. Is this clear? Is it clear, guys? Is it clear? See what kind of basic question this is. You are given with a reaction. We need to calculate standard Gibbs free energy change for the reaction, which will be equal to standard Gibbs free energy of formation of products minus reactants. So I'll start with 1 multiplied by delta G naught F of carbon dioxide plus 1 multiplied by delta G naught F of H2. This is the standard Gibbs free energy of products minus standard Gibbs free energy of reactants. So 1 multiplied by delta G naught F of carbon monoxide plus 1 multiplied by delta G naught F of water. Now see if all the parameters are given or not. Delta G naught F of carbon dioxide is given to us minus 400. H2, hydrogen is in standard state. It's going to be 0. This value is given. This value is given. Put all the values and get the answer. That's all. Put all the values and get the answer. That's all. Yeah? Is it clear? You should be able to solve this sort of a question as well. It's very simple and basic. It's very simple and basic. Now, guys, let's talk about the physical significance first of all. What is the physical significance of Gibbs free energy? This is important. Physical significance of Gibbs free energy. Before talking about the physical significance of Gibbs free energy, let me tell you one more thing. When we talk about work is actually of two types. Work is actually of two types. One is called as PV work, pressure volume work. One more is called as non-PV work. Non-PV work. Non-PV work is also called as useful work. And the example of the useful work is, for example, electrical work. It is, for example, electrical work. Now, what all these things means, first of all. For example, this is the container which we have. And in this container, I have kept an ideal gas. This is the ideal gas in the container, right? Now, for example, the piston is moving from A to B against external pressure. The piston is moving from A to B. So this is expansion. You know, whenever there is expansion or compression, in presence of external pressure, what happens? Energy is exchanged between system and surroundings in the form of work. And that work is something which you call as PV work, pressure volume work. So if the piston is moving from A to B, for example, then this is the case of expansion. We always say work is done by the system. But which work? This is the case of PV work, basically. This is the pressure volume work which is happening here. Similarly, during compression, work is done on the gas. Which work is done on the gas? It is the pressure volume work which is done on the gas. So whatever work we were discussing till now, that is basically PV work. That work which happens when the piston moves, right? Except free expansion. Leave free expansion aside. Okay, whenever you see piston moving either outwards or inwards, right? Exchange of energy between system and surroundings takes place in the form of what? Work. And which work that is? That is the pressure volume work which I'm talking about. So this is the pressure volume work which is happening here. So over here, Energy between system and surroundings is exchanged in the form of pressure volume work. Now, what is this non-PV work? What is this useful work? Let's try to understand what this useful work is all about. I'm sure every one of you would have come across the Daniell cell. Do you remember Daniell cell? Your galvanic cell, right? This is your anode, this is your cathode, and they are connected. They are connected from the top, and internally they are connected with the help of salt bridge, right? You must have studied about this. Perfect. What is the function of the Daniell cell basically? What is the function of this galvanic cell? What this Daniell cell does? It generates electricity, it generates current, it produces current. Daniell cell, what does it do? It produces current. How it produces current basically? Basically, in case of Daniell cell, there will be movement of electrons from anode to cathode. There will be movement of electrons. There will be directional movement of electrons from anode to cathode, due to which current is generated in case of Daniell cell, right? In case of Daniell cell, what happens? Electrons move from anode to cathode. So there will be directional movement of electrons from anode to cathode. Absolutely. Yeah. Now, my dear students, first of all, if I ask you in this part of the cell, which work is going on? Can I say electrical work is going on? It is the electrical work which is going on here, right? Electron is being pushed from anode to cathode. Electrical work is going on basically. And electrical work, that is basically the example of what? That is the example of non-PV work. So I would say non-PV work is going on here, right? Non-PV work is going on here. Perfect. Non-PV work is going on here. Similarly, for example, this is an electrolytic cell. For example, I've taken water in the container. This H2O liquid in the container. For example, I'm introducing two rods here in this container. Now, here you have got a battery. What this battery does? It is going to supply current in the water. Battery will supply current in the water, right? So in this part of the cell, what is happening? Electrical work is happening. What is electrical work? Electrical work is the example of non-PV work. It is the example of non-PV work. And when current will go into the water, electrolysis of water will happen. Water will get converted into H2 gas. And you will be getting what? You'll be getting O2 gas as well. During the electrolysis of water, what will happen? Gases will produce. H2 gas will produce, O2 gas will produce. On the reactant side, you have got liquid. On the product side, you have got gas. So liquid is getting converted into gas. Expansion is happening. Which expansion this is? So imagine as if there was a piston here. Imagine as if there is a piston here. Just imagine there is a piston here. Since gases are getting produced, the piston will go up. If the piston will go up, what will happen? Expansion will happen. Due to expansion, what happens? Energy is exchanged between system and surroundings in the form of which work? In the form of PV work. I would say over here non-PV work is happening because electrons are being pushed, right? Non-PV work is happening, electrical work is happening, and right here, due to the expansion, I would say PV work is happening. Did you get the difference between what is PV work and what is non-PV work? I hope you got it. What is PV work and what is non-PV work? What is PV work and what is non-PV work? Try to understand one more thing. For example, I'm again taking the Daniell cell into consideration. This is anode, and over here, this is your cathode. You are connecting them externally. You're connecting them externally. This is your anode and this is your cathode. And internally also you're connecting them. So this is your Daniell cell, for example. Okay. First of all, what happens in the Daniell cell? Electrons are moved from anode to cathode. Right? So in this part, what is happening? What is happening? Electrons are being pushed basically. Electrical work is happening over here. Electrical work is the example of non-PV work. So non-PV work is happening. Non-PV work is happening. Non-PV work is also called as useful work. Through which, so basically electrons are being pushed from anode to cathode. So non-PV work is happening. That's what you call as useful work, right? Now, my dear students, do remember, as I told you in the beginning also, in the system, you'll find two types of energies, available and unavailable. In the system, what you'll find? You'll find two types of energies, available and unavailable. Available and unavailable energy. Available energy, it is that part of the energy which is converted into what? Which is converted into useful work. What kind of useful work is happening here? Basically, electron is being taken from anode to cathode. Electron is taken from anode to cathode. So work is happening, electrical work is happening. In order to take the electron from anode to cathode, system will be using some of its energy. Now, which energy system will be using for this electrical work? It is the available energy which the system will be using to perform this electrical work, to perform this non-PV work. Yeah. Imagine that in the beginning, the system had 80 joules of available energy. After some time, you saw only 60 joules of available energy is present in the system. Initially, for example, 80 joules of available energy was with the system. Now, after some time, only 60 joules of available energy is left with the system. So, has the available energy of the system decreased or increased? It has decreased. By how much amount? Has the available energy of the system increased or decreased? It has decreased by 20 joules. What does that mean? Available energy of the system has decreased. That means some part of available energy has been utilized to perform non-PV work, to send electrons from anode to cathode, right? So can I say decrease in the free energy, decrease in the Gibbs free energy, decrease in the available energy is equal to useful work? Can I say 20 joules of useful work has been done in order to take the electron from anode to cathode? Yeah. So I can simply say one thing, decrease in the Gibbs free energy. Decrease in the Gibbs free energy of the system. Decrease in the Gibbs free energy of the system is equal to useful work, is equal to non-PV work. Right? Perfect. So what is Gibbs free energy now? It is that part of the energy of the system which is converted into what? Which is converted into useful work. Let's try to understand all this mathematically, because without mathematics, this all is useless, right? And then you can understand a bit more in detail. First of all, I'm going to mark an equation. I'm going to write an equation. What is an equation? Equation is, just a second. You know, G is equal to H minus Ts. G is equal to H minus Ts. Try to understand what I'm going to say. G is equal to H minus Ts. If I multiply throughout by D, it becomes dG is equal to dH minus D of Ts. So I can write it like this. dG is equal to dH minus TdS minus SDT. Okay. If I write this equation at constant temperature, my dear students, dt is 0. If dt is 0, I would say dG is equal to dH minus TdS. Perfect. Now, since we know what is H, H is equal to U plus PV, right? If I write dH, dH will be equal to du plus d of PV. So you can write it like this. dH is equal to du of PdV plus VdP. If I write the same equation at constant pressure, I must say dH is equal to du plus PdV, because at constant pressure, dP value is 0, right? So dH is equal to du plus PdV. It's valid at constant pressure. So I can say dG is equal to, instead of dH, I can write du plus PdV. And already there was minus TdS. Now try to understand. This equation we wrote at constant temperature. And this equation we wrote at constant pressure, right? And we are putting the value of dH over here. That means this particular equation. It is valid at constant pressure and temperature. It is valid at, initially, we wrote this particular equation at constant temperature, and this particular equation we wrote at constant pressure. Putting it in this equation, that means the final equation which we are getting, that's valid at constant pressure and temperature. Point number 1. Point number 2. You know, as per first law, du is equal to dq plus dw. I'll write dw net. du is equal to dq plus dw, right? Okay, du is equal to, okay, I'll tell Ambika about that, no issues. du is equal to dq plus dw. For example, we have a system. For example, the system which we have. Let's say that is capable of doing, let's say we have got the system which is capable of doing PV as well as non-PV work. Let's say that we have got a system which is capable of doing PV as well as non-PV work. So what is going to happen? If we have got a system which is capable of doing PV as well as non-PV work, something interesting is going to happen. Try to understand. We'll write dg is equal to, what is du? du is dq plus dw net. dw net. Then what do we have? du is equal to dq plus dw. Then you have got pdv as well. And then you have got tds as well. I told you the system, for example, is capable of performing PV work as well as non-PV work. So instead of dw net, I can write dw PV plus dw non-PV, right? And already there was pdv and tds. So I can say dg is equal dq dw of pv. PV work is equal to minus pdv plus dw of non-PV plus pdv minus tds. So see what all things will get cancelled out. Or one more thing, you know, your ds is equal dq reversible upon temperature. So I can say dq is equal tds. Perfect. So instead of dq, you can write tds minus pdv plus dw non-PV plus pdv minus TDS. See what all parameters will get cancelled out. So this term got cancelled, right? PDV got cancelled. So finally, I'm getting something like this. DG is equal to dw non-PV. DG is equal to dw non-PV. If I integrate on both the sides, I'm getting delta G is equal to non-PV work. Delta G is equal to non-PV work. Is this something which I told you a few minutes back only? Is this something which I told you a few minutes back only? What is this? Delta G is equal to non-PV work. What is the significance of this particular equation? It means some part of Gibbs free energy is used for what? Is converted into useful work, is converted into non-PV work. Yeah? It simply, this equation simply tells you that the part of the Gibbs free energy is utilized for useful work, is converted into useful work, right? Now from this equation, there are few things which you can analyze. I told you delta G is equal to W non-PV. Delta G is equal to W non-PV. Try to understand what all things I'm going to say from here. When I took the galvanic cell, if you remember, when I took the galvanic cell, the electron was moving from anode to cathode, right? So electrical work was happening basically. Yeah, electrical work was happening. That is useful work. That is non-PV work. Now non-PV work was happening. Now, my dear students, I told you, in order to take the electron from anode to cathode, the system will be utilizing some of its energy. Which energy system will be utilizing basically? The system will be utilizing its available energy to send the electron from anode to cathode. So with the time, the available energy of the system will decreasing because some part of it is utilized to send the electron from anode to cathode. So decrease of available energy is happening to send electron from anode to cathode. So non-PV work is done by the system at the cost of its available energy, right? So non-PV work is done by the system at the cost of its available energy. With time, available energy will decrease, due to which non-PV work will be done by the system. Let's try to understand it now. My dear students, for example, the value of W over here comes out to be negative. If the value of W is coming out to be negative, what does that mean? That means non-PV work or useful work is done by the system. Just relate it with the Daniell cell. Just try to relate it with the Daniell cell as if system is sending electrons from anode to cathode. Okay? Non-PV work is done by the system. At the same time, if W non-PV is negative, that means delta G is negative. That means delta G is negative. Delta G negative means free energy of the system is decreasing. So whenever you see free energy of the system decreasing with time, understand at that point of time, non-PV work will be done by the system because some part of the available energy, some part of Gibbs free energy will be converted into useful work. That is the reason why Gibbs free energy will be decreasing with time. I hope this is clear. Similarly, one more statement. If W non-PV is positive, what does that mean? That means the non-PV work is done on the system. Non-PV work is done on the system, right? If W is positive, if W non-PV is positive, what does that mean? That means delta G is positive. If delta G is positive, that means Gibbs free energy of the system increase with time. So whenever you see the Gibbs free energy of the system increasing with time, that means at that time non-PV work is done on the system. Whatever non-PV work is done on the system, that entire non-PV work is stored in the system in the form of its Gibbs free energy. Yeah? Perfect. So do remember these two particular statements. I hope these are super clear to you, right? One last topic is there. First tell me, is this particular thing clear to you? What have I said till now? Is this particular thing clear to you? When non-PE work is done by the system, at that time Gibbs free energy of the system will be decreasing, because some part of Gibbs free energy is converted into useful work. That's the reason why Gibbs free energy decreases. Okay? When? But when non-PE work is done on the system, whatever non-PE work is done on the system, that entire non-PE work is stored in the gas in the form of Gibbs free energy, due to which Gibbs free energy will increase with time. Non-PE work done on the system, Gibbs free energy increases for the system. Non-PE work is done by the system, Gibbs free energy decreases. Perfect? Do remember this particular result, this is important. Sometimes they won't ask you directly to calculate delta G, they'll ask you to calculate non-PE work. They'll ask you to calculate non-PE work. Non-PE work is nothing, that's delta G only. Then use the formula delta H minus T delta S, whatever. Right? Sometimes they can confuse you. Directly, either they'll directly ask you to calculate delta G, or they can ask you to calculate the non-PE work done by the system or on the system. That means indirectly they're asking you to calculate delta G only. I hope this is clear. All right, one last topic, guys. With that, we'll be ending the chapter. And this is important too. I'm writing variation of Gibbs free energy with pressure and temperature. Variation of Gibbs free energy with pressure and temperature. Let's get to know how Gibbs free energy changes on changing pressure, on changing temperature. Let's have a look. Yes, this is a detailed course. Now guys, try to understand. First of all, I'm going to write one equation, which you are going to remember directly from now onwards. dG is equal to VdP minus STT. This is the backbone of the thermodynamics, this particular equation. dG is equal to VdP minus STT. This particular equation you are going to remember directly from now on, right? And let me tell you, this particular equation, it is valid for reversible processes. It is valid for reversible processes. Now understand what exactly I'm going to say. Point number one. For an ideal gas, let's say you have got the ideal gas, which is kept at constant temperature. Let's say you have got the ideal gas whose temperature is kept fixed. We are not changing the temperature of the ideal gas. If temperature is constant, if temperature is fixed, that means dT value will be 0. Change in temperature will be 0. If dT is 0, that means dG will be equal to VdP. dG will be equal to VdP. This particular equation is valid for that ideal gas whose temperature is kept constant, right? Now, my dear students, the ideal gas whose temperature is kept constant, let's say you increase its pressure. If you increase its pressure, what will happen to the dP value? Change in pressure. Will it come out to be positive or negative? If you increase the pressure of this ideal gas, dP, change in pressure, will be positive. If dP is positive, this whole term is positive. And if this whole term is positive, that means dG is positive. And when is dG positive? Change in Gibbs free energy? When G increases. dG is positive only when G is increasing. Right? So what can we conclude from here? On increasing the pressure of the ideal gas, Gibbs free energy of the ideal gas increases. So Gibbs free energy is directly proportional to pressure of the ideal gas, provided temperature of the gas is kept constant. Yeah? Provided the temperature of the gas is kept constant. If you increase the pressure of the gas, Gibbs free energy of the gas will automatically increase, provided the temperature is constant. Now, on changing the pressure, Gibbs free energy increases. how much Gibbs free energy increases on changing the pressure. That is important also. That is important also. For example, I'm changing the pressure of the gas from P1 to P2. Let's say I'm changing the pressure of this gas from P1 to P2, right? Since we know dG is equal to VdP. Since we know dG is equal to what? Since we know dG is equal to VdP for the ideal gas which is kept at constant temperature, right? Now, what are we doing? We are changing the pressure of the ideal gas from P1 to P2. We need to see what is the total Gibbs free energy change. In order to calculate total Gibbs free energy change, we'll be integrating, right? We'll be integrating from P1 to P2. We'll be integrating with respect to pressure since we are changing pressure from P1 to P2, right? So guys, integral of dG is delta G is equal integral from P1 to P2. V is equal to nRT divided by P, and this is dP. So delta G has to be equal to nRT comes out. Integral of dP is ln of P. So upper limit, lower limit. So ln of P2 divided by P1. Or you can write it like this. Delta G is equal to minus 2.303. nRT is going to be log of P2 divided by P1. Right? What equation this is? What equation this is? And when it's used? This equation is used to calculate the Gibbs free energy change of an ideal gas, which is kept at constant temperature, whose pressure we are changing from P1 to P2. Since we got to know on changing the pressure of the ideal gas, Gibbs free energy changes. Now, how do we calculate that change in the Gibbs free energy on changing the pressure at constant temperature? This is the result. If you change the ideal gas pressure from P1 to P2, keeping temperature constant, how do we calculate delta G? Change in the Gibbs free energy of the ideal gas. It has to be equal to 2.303 minus. Wait, is it minus? It's not minus. Why am I writing minus here? It was delta G is equal to nRT ln P1 by P. This is plus, this is not minus. Okay? Perfect. There is nothing like 11th, 12th, right? It is all NEET and JE. Don't get confused, right? Whatever chapters are there in class 11, they're asked in NEET. So it's better if you study NEET. Don't be confused. Don't confuse yourself that you are in class 11th right now. You'll do the NEET coaching afterwards. You have to do the NEET coaching right now. I hope this particular statement is clear to you, right? Now, guys, there is one more thing. There is one more thing. The equation which I gave you in the beginning, that is dG is equal to VdP minus SdT. VdP minus SdT, which is valid for the reversal process, right? Now, imagine that we have got the ideal gas. I'm writing for ideal gas. For ideal gas at constant pressure. Let's say you have got the ideal gas which is kept at constant pressure. Let's assume that we have got the ideal gas which is kept at constant pressure. If the ideal gas is kept at constant pressure, so change in pressure dP has to be 0. If dP is 0, then dG will be equal to minus times S dt. dG will be equal to minus times S dt. Right? So basically, what exactly I'm going to do? What exactly I'm going to do? I'm taking an ideal gas whose pressure I'm maintaining. I'm keeping the pressure constant. So I got to know dG for the ideal gas whose pressure is constant is equal to minus times S dt. Now you tell me one thing. If you increase the temperature of the same ideal gas, change in temperature dt will come out to be positive. If dt is coming out to be positive, positive negative makes it negative. So dG has to be negative. Change in Gibbs free energy is negative. That means Gibbs free energy of the system decreases. What does that mean? What does that mean? That means if you increase the temperature of the ideal gas, the Gibbs free energy of the gas will decrease. So Gibbs free energy is inversely proportional to temperature of the gas. It is inversely proportional to temperature of the gas provided the pressure of the gas is kept constant. Provided the pressure of the gas is kept constant, right? Perfect. Now, you got to know your dG is equal to minus times S dt. Perfect, right? So, what exactly we are going to do? For example, you have got the ideal gas in the container. This is the ideal gas in the container, right? Let's say, okay, do remember it like this only. dG is equal to minus S dt. But do remember this is valid for the ideal gas whose temperature you are changing, keeping pressure constant. Keeping pressure constant. So till now, I was talking about gases, basically, ideal gases. Now, for example, if you have solid or liquid, for solids or liquids, if your system is not the ideal gas, if your system is, for example, solid or liquid, what will happen? For solids and liquids, when you change the pressure of solid and liquid, when you increase or decrease the pressure of solid and liquid, I'm talking about this particular case. This was the case for the ideal gas, which is kept at constant temperature, right? When you increase the pressure of the ideal gas, Gibbs free energy increases, right? But imagine that your system is not the ideal gas. Imagine the system is your solid or liquid. So I'm writing for solids or liquids. For solids or liquids kept at constant temperature. If you change the pressure, first of all, for solids, liquids kept at constant temperature, we know dG is equal to VdP minus SdT. If temperature is constant, this term is 0. So dG has to be equal to VdP, correct? Right? Now guys, imagine that this is a solid or a liquid. Which is kept at constant temperature. Now you are changing its pressure. You are changing the pressure of solid or a liquid. Due to change in pressure, volume of the solid or liquid will not change significantly. There will be negligible change in the volume of solid or liquid. If you have a solid or a liquid in a container, if you change its pressure, there will be negligible change in its volume, right? There will be negligible change in its volume. Imagine this is a solid. Let's assume that you are changing the pressure of the solid from P1 to P2. I need to calculate the total change in Gibbs free energy due to change in pressure of the solid whose pressure you are changing from P1 to P2. In order to get the total Gibbs free energy change, you'll be integrating under the limits P1 to P2. So integral of dG is delta G. Since on changing the pressure, volume of solid or liquid, it does not significantly change. So volume is kept constant, V coming out. Integral of dP is P, upper limit, lower limit. So it has to be P2 minus P1. So delta G is equal to V delta P. But this particular result, it's valid only for solids or liquids, which are kept at constant temperature. So if you'll be having a solid or a liquid, which is kept at a constant temperature, and you're changing its pressure, on changing the pressure, you have to check what will be its change in Gibbs free energy. This is the result which you'll be using to calculate the change in the Gibbs free energy of a solid or a liquid whose pressure you are changing from P1 to P2 at a particular temperature, right? I hope all these results, whichever I told you, I hope you guys are going to remember them. Okay? All right, what do you think about this question? Will you be able to solve this? What is the free energy change when 1 mole of H2O liquid? So you have got 1 mole of H2O liquid at 100 degrees centigrade and 1 atm pressure is converted into steam, is converted into H2O gas at 100 degrees centigrade and 1 atm. So during the process, we have to calculate delta G value. Can you let me know what is the value of delta G during this process? This is your homework question which I'm giving you. You are converting H2O liquid into H2O gas. Temperature is same, pressure is same. Calculate delta G during the process. Or let me tell this question here only. See, are you changing the pressure of the system? No. Are you changing the temperature of the system? No. Neither you are changing pressure nor you are changing temperature. So delta G value has to be 0, right? Or you know, at 1 atm 100 degrees centigrade, can I say liquid and gas, they'll be in equilibrium, right? They'll be in equilibrium. At 100 degrees centigrade, your liquid and vapors, they're at equilibrium. If pressure and temperature on both the sides is equal, temperature is 100, pressure is 1 atm, right? So it is basically the boiling point of water. At boiling point, your liquid and vapors, they are at equilibrium. And at equilibrium, you already know delta G is 0. So like this also you can solve this. Okay, like this also you can solve it. Perfect. One question, which is your homework question. This is something which you guys are going to solve. Again, you are vaporizing 1 mole of liquid water. keeping temperature same, but you are changing pressure from 1 atm to 2 atm. You have to calculate the value of delta G during the process. You have to calculate the value of delta G during the process, right? This is your homework question. You guys will be letting me know the answer of this particular question in the comment section, right? And let me remind you, day after tomorrow, Saturday at 5 p.m., we will be doing your chemical equilibrium in one shot. Chemical equilibrium in one shot will happen on Saturday, 5 p.m., right? So be there on time. Perfect. Is everything clear till here? All clear? All right, guys. So with this, I'll be taking a leave. And at the same time, if you want the handwritten PDF of this particular session, this is the Telegram group, t.me/WASSIMSIRCHEM.
Unacademy. Let's crack it.